welcome to your pedia. So welcome back again. In this marathon, I am going to discuss the most important part in our electrical subjects, that is our basics, network theory questions. The interview questions on network theory. So first of all, how many topics are there in network theory or electrical circuits? So here, in this networks, we are having a DC and also we are having AC circuits. So we are having DC circuits and also we are having a AC circuits. After that, in this DC, we are having the elements R, L, C, and also we will discuss about the voltage sources and current sources. In AC circuits, we will discuss the most important part, why we are going to the AC, differences between DC and AC, and we will discuss theorems, and also we are having a three-phase circuits. After that, we are going for the graph theory. So the most important interview questions on single phase AC as well as the three phase and the applications of theorems is also very important. And two-port networks. What are the applications of two-port networks? That means, what are the applications of Z parameters? What are the applications of Y parameters? Why the ABCD parameters are also called as a transmission line parameters. So why H parameters are used for in an electronic circuits. So these type of questions we will discuss in this marathon. And first of all, so what is meant by DC? What is meant by DC? DC means it is a direct current which does not consisting of a frequency. The frequency of the DC value should be equal to 0. Frequency for DC value is 0. Okay, so first of all, coming to the first question. Now, what is the difference between the circuit and network? So coming to this first most important interview questions. Yes. So difference between circuit and network. So we are having elements R, L, C, and also voltage source and current source is also two terminal elements. Okay, we'll discuss one by one. But what is the meaning of circuit and network? An interconnection of elements. Let us say I am taking a resistor. So an interconnection of elements is called the network. So you can connect in any manner. So here it does not consisting of a closed path, but a circuit means a network should consisting of at least one closed path. We can say that it is a circuit. So all the circuits are networks, but all the networks are not circuits. So this is the basic difference between the circuit and network. So coming to one by one question. So what is meant by charge? So what is meant by charge? Yes. Okay. So charge, and the charge is represented with Q. So in an interview is asking define charge. So I will start the interview questions from level 1 to level 3 questions. And the level 1 is the basic questions, level 2 is the medium questions, and level 3 is somewhat tough questions. Okay, so define charge. If a sodium loses one electron, it attains a positive charge. It attains a positive charge. If a chlorine gains one electron, it attains a negative charge. What is sodium and chlorine? Sodium and chlorine both are called atoms. Yes, the addition of an electron or subtraction of an electron to an atom is called the charge. So addition of electron or subtraction of electron to an atom is called charge. Yes. What is the representation of charge is Q, and it is measured in coulombs. It is measured in coulombs. Okay. Then what is meant by free electrons? What is meant by free electrons? So the free electrons. So what is my free electrons? Yes, if a sodium loses one electron, it attains a positive charge. Chlorine gains one electron, it attains a negative charge. But what is my free electron? Yes, that free electron is only loses or we can add to the atom. So if you take the center of the atom is called the nucleus. Center of the atom is called the nucleus. The electrons revolves in an orbit. So this is the first orbit, second orbit, third orbit like this. The electrons revolves around the nucleus by 2n square. The electrons which are loosely attached to the center of the atom is called the free electron. So coming to the next question. So what is meant by conductors, and what is meant by semiconductors, and what is insulators? How can you classify those three? So based on the availability of free electrons at room temperature, we can divide the materials into three. First one is called the conductors. And second one is semiconductors. So conductors, and the second is semiconductors, and the third is insulators. Yes. In a conductors, the free electrons are available. Large number of free electrons are available at room temperature. So the examples of the conductors in a daily life we are using, that is copper. Yes, copper. After that iron, silver, and aluminium. etc. And copper is the best conductor. You know that Rm cost is more, and silver cost is also more. We can use the copper winding. Copper winding consisting of a low value of resistance, and the aluminum has high resistance, but it is a cheap. Copper is costly when compared to, somewhat costly when compared to aluminum. But these two are we are using in a daily life, copper and as well as the aluminum. And semiconductors means it has few electrons at room temperature. At room temperature. So what are the examples? Is germanium and silicon. If you go for the diode is made up of germanium and the diode is made up of silicon. Okay, and these are the fourth group elements. You know that intrinsic semiconductor and extrinsic semiconductor. What is meant by insulator? So insulator means very few electrons, consisting of a very few electrons at room temperature. Very few electrons at room temperature. So the examples are wood, rubber, and plastic. And these are the examples of the insulators. And based on the availability of free electrons, we can divide the material into three: conductors, semiconductors, and insulators. And these three are very, very important. And now we'll discuss the most important part. So what is mean by electric current? What is meant by electric current? Yes, electric current. Define electric current. So the electric current is represented with I. Electric current is represented with I. And Andrew Mary Ampere, who invented the electric current. Coming to the next interview question. Who invented the current? Andrew Mary Ampere. Who invented the electric current? So based on his name, the current units are ampere. The current units are ampere. Okay. So if I am taking the conductor, which is made up of copper here, and the copper consisting of large number of free electrons at room temperature, and without applying an external source, the electrons are in zigzag manner. Okay. Now you can apply a voltage source here, and this is positive terminal of the supply. Which is represented like this, and the negative terminal of the supply is represented like this. You can apply an external source, and here one switch is provided. Here. You can connect the switch like this. Once the switch is closed, what will happen? Electrons are having which charge? Negative charge or positive charge? Electrons are having a negative charge, and electrons are attracted by the positive terminal of the supply and are repelled by the negative terminal of the supply. Electrons are attracted by the positive terminal of the supply and are repelled by the negative terminal of the supply. Then the electrons are flowing in this direction. Which is from negative terminal of the supply to the positive terminal of the supply. But we are taking the conventional current throughout electrical engineering, throughout electrical circuits. We are taking conventional current, which is exactly 180 degrees to the electron's current, opposite to the electron current. So before invention of electrons current direction, the conventional current, they may thought that the conventional current is flowing from positive terminal of the supply to the negative terminal. Suppose if you are sitting in a moving train, you can see the outside objects. What is your feeling? Tell me. Now, if you are sitting constantly in a train which is moving with a speed of 60 kilometers per hour, if you see the outside objects, you can think that outside objects are moving. Yes or no? Outside objects are moving. Similarly, same way, the electrons are moving in this direction from the negative terminal of the supply to the positive terminal of the supply. During that process, they identified that yes, conventional current is flowing. Yes, current is flowing from positive terminal of the supply to the negative terminal of the supply. Okay, throughout this electrical engineering subjects, that is like electrical circuits or whatever it may be, while you are applying KVL or KCL, whatever it may be, we are taking only conventional current rather than electrons current. Yes, sir, what is meant by V, sir? V is called the EMF, electromotive force. As the coming to the next question is called the electromotive force. Okay, we are not technically speaking the force. See here, the force required to move the electrons in a particular direction is called the electromotive force. Actually, it is not actually so mechanical force. It is an electrical force only. The force required to move the electrons in a particular direction is called the electromotive force. Without this electromotive force, there is no repulsion force or attraction force. Then there is no movement of the free electrons. If there is no movement of the free electrons, there is no current. Now coming to this point, what is electric current? The flow of free electrons in an electrical circuit or yes, in an electrical network, yes, then it is called as a electric current, and the current is represented with I, and the units of current is ampere. And also you can define the current. Rate of change of charge is called the rate of change of charge, dq by dt, dq by dt, and the current units is also called coulombs per second, coulombs per second. So dq by dt, rate of change of charge, is also called as a electric current. Now, so what is in by EMF? What is the role of EMF? So without this EMF, there is no movement of free electrons, there is no current. Okay, now what is meant by electric current? So now what is meant by electric potential? So electric potential, define electrical potential. You may solve a number of problems which is coming in a KVL mesh analysis or nodal analysis, supermesh analysis or supernode analysis, but you may forget the fundamentals, what is meant by electric potential. So this electric potential, which is represented with the V, which is represented with V. So the definition of electric potential is the ability of charged body, the ability of charged body to do the work, is called, electric potential. Electric potential. Suppose if you take your mobile phone and your mobile phone is charged to 100%, and after the charging, yes, that is stored in the form of a particular energy, that is called the electrical energy. Yes, then you are using your phone after it is fully charged. Yeah, after it is half charged also you may use. In between you can get a call and you pick that phone, right? Yes or no? So similarly, that what are the charged body? yes, in our phone. So that is used to do the some work. What is your work? What is your work? So you are using some phone, and you are using WhatsApp, and you are using some apps, background apps is also running, right? So similarly, same way, the ability of charged body, yes, the ability of charged body to do some work is called the electric potential, where V is equal to dW by dQ, where V is equal to dW by dQ. So the units of this one is called the joules per coulomb, or also called as a volts. Volta scientist, he invented the voltage. Based on his name, we can assign the units of EMF and the units of electric potential. We can use that as volts. Okay. So now, what is meant by potential difference? So what is meant by potential difference? So potential difference, as the name itself, it is a potential difference. Difference of two potentials. Yes, what potentials? Difference of two electric potentials. Difference of two electric potentials. Electric potentials is called potential difference, P dot D, which is also measured in volts. Suppose charged body A which consisting of a plus 5 volts, and the charged body B which consisting of a potential, electric potential is plus 3 volts. Plus 3 volts here. So if you are consisting of these two charges, what is the potential difference between these two? Yes, potential difference between these two is 5 minus 3, that should be equal to 2 volts. This is the potential difference. Now, the electrons which are flowing from lower potential to higher potential, but the conventional current always flows from higher potential to lower potential. How can we remember, sir? Higher potential is represented with plus, lower potential is represented with minus. If we take a water bottle, yes, water bottle is filled with water. Water bottle is filled with water, and you can kept a hole at the bottom of the bottle, and whatever the water is there, the water is flowing from high level to low level. Suppose if you want to fill the tank that is there in our home, top of our home, you can require from low level to high level, means you can require motor. Generally, if the dams is also there, yes, dams are constructed, civil engineers are constructed the dams, and the water is flows from higher level to lower level only. If you require from lower level to higher level, you can require a motor. Sir, so similarly here also always the current flows from higher potential to lower potential, and same charged body which is having plus 5 volts, and the charged body which are having a minus 5 volts. So what is the potential difference between these two? 5 minus of minus 5. 5 minus of minus 5, that should be equal to 10 volts. 5 minus of minus 5 is 10 volts. Okay. And suppose if I am taking the two charges are having a same potential, so this is plus B, he is plus 5 volts. Now what is the potential difference between these two? If a potential difference between these two is 0, 5 minus 5, if the potential difference is 0, there is no movement of electrons, so the electric current is also 0. Who will maintain the potential difference, sir? EMF maintains the potential difference. Potential difference causes the current flows through the circuit. These are all important interview questions. In this marathon, we will discuss the most important and basics. What are the questions which are required for the interviews? We will discuss. See here, how beautifully electrical circuit is designed. EMF maintains the potential difference. Potential difference causes the current flows through the circuit. Suppose if you are taking one conductor, the conductor which is having a small value of resistor, you can see here, let us say these two terminals 1 and 2, and you can give the supply voltage here, it is V, and the electrons are attracted by the positive terminal of the supply while the switch is closed. Then you can apply the V volts here, and also once it will be current is flowing, right, current is flowing. If it is consisting of a resistance is called the R. Anyway, conductors has low value of resistances, semiconductors has medium resistance, and insulators has very high resistance. Okay, right. So we will discuss what is the next important question. What is resistance? How it will be framed? Okay. Now, so the V volts will be appeared here. Always the current flows from higher potential to lower potential. This is called the conventional current. Then the potential voltage drop will be takes place. Without this voltage, there is no potential difference. There is no potential difference means there is no electric current. So now the most important part is called the electric power. So what is meant by electric power? So we are having a different types of powers. Mechanical power, okay, and but in this we will discuss the electric power, so which is represented with P, So the rate at which work is done, in a simple way I am telling, the rate means dt at which work is done is called the electric power. So I can write it as dw by dq into dq by dt. dw by dq into dq by dt. So what is meant by dw by dq is V, dq by dt is what is that? dq by dt is called the I. Yes, power which is a product of voltage into current. This is a generalized formula. If you go for the AC, you are having a three powers: active power, reactive power, and apparent power. Okay, so power is a product of voltage into current, right? So what is the units of power is called the watt. The units of electric power is called the watt. So generally you are using that current gone. When the power is switched off, you can tell that it's a current gone. No, you should not use that word. You can use that power off. Load shedding will be off. Load shedding means loads are removed. Loads are off. Okay, so you can use the technical words electric power. And now the examples of the electrical power, yes, in our homes we are having a 60 watt bulb, yes, 60 watt bulb, 40 watt bulb, yes, 1000 watt water heater, yes, and the geyser. If you take a fridge is also having some rating. Fan rating will be 75 watts. You can use different types of ratings of the fans also. But generally, I am telling that these are all the examples of the electric powers. Yes. If a bulb uses 8 hours in a particular home, you can take that is using only bulb, is using only bulb. In another home is using bulb, fan and water heater, and same hours daily they are using 8 hours like that. A water heater is 2 hours. Okay, who will get more bill? The first one will get lesser bill. Why? Because is using only 40 watt bulb in 8 hours only. Yes, if he another person which is using, yes, he has a 75 watts, 1000 watts, 40 watts, 60 watts. Add this how many hours we are using? 8 hours. That means yes, water heater also is switched on the 8 hours. It's not possible. Okay, 2 hours, but 8 hours. The power multiplied with the time, the most important one, the difference between the electrical power and the electrical energy. So now we will see the what is the meaning of electrical energy. So electrical energy, it is a product of power consumed multiplied with the time. It is represented with E, and the power units are watts and time units are hours, and it is measured in kilowatt hour. It is measured in kilowatt hour. So what is the best example of the electrical energy where we are using means, sir, in our daily appliances we are using, sir, 60 watt bulb we are using, 40 watt bulb we are using. Anyway, we are having LED bulbs which is having a different ratings. Okay, but 60 watt bulb or 40 watt bulb or geyser or water heater you are using in a different times. So water heater is used only 2 hours, and the bulb is used for 8 hours. Fan is also used for 24 hours. Yes. So if you multiply power consumed multiplied time, then you will have a electrical energy and integration of power dt. This is the generalized formula where E is equal to integration of power dt. Why? Why means, see, we are having a different ratings. Bulb is having a 60 watts which is used in 8 hours. Yes, 60 watts which is used in 8 hours, and 1000 watt geyser used in 2 hours, and 40 watt bulb is used in 16 hours like that. Yes, power multiplied time P1 T1 plus P2 T2 plus P3 T3 so on. How many days you are using? 30 days. 30 days. How many hours you are using? You are calculated. Yeah, if you want to get the January bill multiplied with 31, then you will get the January bill. So 1 kilowatt hour is equal to, or 1 unit is equal to 1 kilowatt hour. 1 unit is equal to 1 kilowatt hour. So in our homes we are having a 1 meter, that is called the energy meter. It is the energy meter from which we are getting the electricity bill. Okay, right? So this is about the electrical energy which is measured in kilowatt hour. You can observe on the electrical energy meter. You can observe on energy meter is clearly mentioned that 1500 revolutions per kilowatt hour. If you want to get 1 kilowatt hour, the energy meter disk, it should make the 1500 revolutions. 1500 revolutions. Okay. So these are all basic definitions which are related to electrical circuits. So electrical circuits. So what is my charge and what is electric potential, potential difference, EMF, electrical power and electrical energy. Define electrical energy. Okay, and total power consumed in multiplied with the time is called the electrical energy. Or electrical energy, it is a summation of power dt. Summation of power dt. So these are all called the basic definitions. Okay. Now coming to the what are the elements are there? What are the elements are there in an electrical circuit? classification of elements. Classification of elements. He may not ask what are the classification of elements, but he is asking in an interview what is meant by active element, what is meant by passive elements. So first of all, the first classification is called the active and passive elements. Active and passive elements. Okay. And the second one is called the bilateral and unilateral elements. Bilateral and unilateral elements. And the third is linear and non-linear elements. Linear and non-linear elements. And the fourth one is lumped and distributed elements. So lumped and distributed elements. And the last classification is called the time variant and time invariant elements. Okay, so in an interview he is asking about what is meant by active elements. Define active elements. What are the examples of active elements? Define passive elements. What are the examples of passive elements? Define bilateral elements. What are the examples of bilateral element? So define unilateral elements. What are the examples of unilateral elements? He may not ask the classification of elements. An element which is a two-terminal device. That's it. An element is a two-terminal device. Okay, coming to one by one. So what is meant by active elements? So what is meant by active elements? So active elements, yes, and elements which are capable of delivering the energy to the external elements is called the active elements, which are capable of delivering the energy. So and elements which are capable of delivering the energy, and elements which are capable of delivering the energy to the external circuit or external circuit elements is called active elements. The examples of active elements are voltage source. As the name itself, it is a source. Source means which delivers the energy. So second one is called the current source. Yes, first one is called the voltage source and second one is called the current source. And elements which are capable of delivering the energy to the external elements is called the active elements. Now next one is called the passive elements. What is my passive elements? Yes, active elements means which is capable of delivering energy. So what is my passive elements? What are the examples of the passive elements? That is the interview question. Passive elements means which are not capable of delivering the energy which are not capable of delivering the energy is called passive elements. The examples of the passive elements are R, L, C. R, L, C. Okay, so this is about the passive elements, and this one is called the active elements. Active and passive elements. R means resistor, L means inductance, and C is called the capacitance of the capacitor. R is the resistance of the resistor, L is the inductance of the inductor. So these three are the elements which are not capable of the delivering the energy. Yes. What is the property of a inductor? Inductor stores the energy in the form of a magnetic field. And what is the property of a capacitor? Capacitor stores the energy in the form of electric field. So, okay. So that is the main thing about the active and passive elements. Next one is bilateral. Bilateral and unilateral elements. Bilateral and unilateral elements. Okay, if I am taking a resistor, the first one is called the bilateral element. Define bilateral element. The interview question is define bilateral elements and tell me the examples of bilateral element. Tell me the examples of bilateral elements. Okay. So bilateral elements, if I am taking the resistor which is having a two terminals 1, 2, whose value is 1 kilo ohm, and if you pass the current in this direction, the resistance value is 1 kilo ohm only. Yes, plus or minus is there, tolerance, but ideal case we are taking 1 kilo ohm. If you pass the current from 2 to 1 in this direction, is there any change in the resistance? This is R21, R12. There is no change. That means the current, even though current directions is reversed, in an DC we can call it as a resistance. In an AC, we can call it as a impedance is represented with a Z. Impedance is represented with Z. Okay. So we'll discuss while the AC is comes into picture. What is the impedance value? And even though current directions are reversed, the impedance offered by the element is same. That is called the bilateral elements. R, L, C are the best examples for the bilateral elements. If you take an inductor also, if you take a capacitor also, and R, L, C are the bilateral elements. The impedance offered by the element is same, even though the current direction is reversed. Okay. And next one is called the unilateral element. Next one is a unilateral element. So examples you know that unilateral element. So unilateral elements. So what is in way unilateral element? See, bilateral elements means the impedance offered by the elements is same, even though the current direction is reversed. If you go for the unilateral elements means the impedance offered by the element is not same. The best example for the unilateral element is called the diode. Diode is the best example. We will see. And the P is given to positive terminal of the supply and N is given to the negative terminal of the supply. And what will happen? So in this P, we are having a majority carriers. In a P, we are having a majority carriers or holes. So if you take the majority carriers or the holes, and this is called the P, and this one is called the N, and the P is given to positive terminal of the supply, and N is given to the negative terminal of the supply. The majority carriers in P are the holes which are having a positive charges, and the electrons which are having a negative charges. Electrons moves towards the positive terminal of the supply, and positive will be repelled, negative will be repelled. Now what will happen? The junction will be breaks down, and the junction will be breaks down means what is the resistance of the PN junction diode during a forward biased mode? Then the value is 0 ohms. If it is connected, P is connected to the negative terminal of the supply, and N is connected to the positive terminal of the supply. I am interchanging the supply. Here the current is in this direction. If a current, you can say, take this, and holes are attracted by the negative terminal of the supply. Holes are attracted by the negative terminal of the supply. Electrons are attracted by the positive terminal of the supply. So previously the junction will be breaks down. Now holes are attracted by the positive terminal. Electrons are attracted by the negative terminal of the supply. Electrons are attracted by the positive terminal of the supply. Now see here, the width of the PN junction diode will be increases. So if it is a increases means, ideally say the resistance which is offered by the PN junction diode during a reverse bias condition is infinity. See, previously the current is flowing in this direction. Now the current is flowing, tries to flow in this direction, but it is an open circuit condition. The impedance offered by the element is different for the different directions of flow of electric current. That is called the unilateral element. What is called the unilateral element? So unilateral element. The best example for the unilateral element is PN junction diode. The best example for the bilateral element is R, L, C. Okay, and the next one is called the linear and non-linear element. Linear and non-linear elements. Okay, so I am taking which one is example? See here, the characteristics are a straight line which passes through the origin. Straight line which passes through the origin is called the linear element. So this is a curve for the R. If you go for the psi versus I, or psi versus I, and this is also a straight line passes through the origin. If you take a Q versus V here, and this is also a straight line passes through the origin. Either you can take the x-axis, vice versa, nothing is a problem. If a current flows, flux linkages will be developed. Okay, if you take a V as a capacitance is formed, this is for the inductor and this is for the capacitor. R, L, C are the best example for the linear elements. And another definition of the linear elements is an element which obeys Ohm's law. An element which obeys Ohm's law is called the linear element. The characteristics are a straight line which passes through the origin. The characteristic curve, a straight line which passes through the origin is called the linear element. The best example for the R, L, C. Okay, Y means psi is equal to directly proportional to I, where psi is called the flux linkages, where psi is equal to Li, and the Q is equal to CV here, and R is equal to V by I. We'll discuss what is Ohm's law. Okay, and non-linear elements means non-linear elements. So what is the example of the non-linear elements? Okay, So if you take a diode forward characteristics, this is a PN junction diode. PN junction diode. For a silicon steel, what is the drop? That is the next interview question. Yes, 0.7 volts is the drop here. If you cross 0.7 volts, then only conduction will be starts. And for germanium, it is 0.3 volts is enough to switch on the or turn on the diode. So if you go for the non-linear elements, means diode forward characteristics are like this, and the reverse characteristics are like this. If you draw the curve between the voltage versus current, so voltage versus current means VI characteristics are like this. Okay, yes. So on x-axis is voltage, y-axis is current. You can see that this curve will not passes through the origin. During forward biased mode, it may be linear, looking like a linear, but after it does not having a passes through the origin. Okay, and so in an interview question also he will ask like this. So this is this type of question here, and this is a linear or non-linear, and okay, let us say this is 1, 2, 3 and 4 is given to you. 4 is given to you. Which one is a linear? So the curve is linear, maybe V versus I here. But what is in a linear? A straight line passes through the origin means in third quadrant and first quadrant it will be linear. But here he is not mentioned the third quadrant, but here it is non-linear. We can say that here is mentioned the fourth quadrant, but is not mentioned the second quadrant. So that's why the options 1 is not correct, 2 is not correct, 4 is not correct, and the third one is the correct answer. Okay. So what are the examples of linear elements? Once again, R, L, C. What are the examples of non-linear elements? Is the diode is the best example for the non-linear elements. Okay. Next one is time invariant element or time invariant elements. Time invariant and time variant element. Time invariant elements. Time invariant and time variant elements. Okay, what is meant by time invariant? Means if you take a current versus time, the magnitude of the current is independent of the time. The magnitude of the current or voltage or whatever it may be, which is independent of the time, then it is called the time invariant element. Time invariant element. The best example is DC voltage, DC source. DC sources, either voltage source or current source. Okay, and if the magnitude or amplitude or changes with respect to time, which is dependent on time, is called the time variant elements. The best example is for the AC sources. Okay, and these are the examples of the time invariant and time variant systems. The most important, coming to the next interview question, what is meant by lumped element? What is meant by lumped element and distributed element? Lumped and distributed elements. Lumped and distributed elements. So lumped elements means which are physically seen, or physically separable. The elements which are physically seen or physically separable is called the lumped elements. Distributed elements means the elements which are not physically seen, or not physically separable. Yes. Okay, sir, I understood the concept. Which are physically seen or physically separable, and here also not physically seen, not physically separable. What are the examples? Are? So, lumped elements means if you take a resistor color coding of a resistor, yes, by seeing the color code, you can tell that the value of the resistor. So, carbon resistor is the best example, sir. Carbon resistor is the best example. If you take the inductor coils, on the nameplate is clearly mentioned that 50 millihenry and 25 millihenry. L is also mentioned. We are having physically seen. But if you go for the, I think in your home you have this idea. What is this called? The pole, and this is the tower. We are familiar with this tower. And here so many conductors. How many conductors? 6 conductors. Okay. And this tower is called the transmission tower, which carries the transmission lines. And this one is called the distribution lines or service mains. Okay, which is related to distribution systems only. Transmission lines and distribution lines are the best examples for the distributed elements. Okay, distribution lines and transmission lines. Distribution and transmission lines. Okay, so which are not physically seen, which are not physically separable. Physically seen means you may thought that yes sir, this much size is there conductor. No. You can identify the value. What are the values, sir? R value. If it is R is there, L is there, C is there, you can identify that value. Electrical quantities you can identify by physically seen. Then only you can tell that it is a lumped element or distributed elements. Okay, and these are the classification of the elements. Active elements, passive elements. What is active elements? Active elements means which are capable of delivering the energy to the external elements is called the active elements. What are the examples of the active elements? Active elements means the examples are voltage source and current source. Passive elements means which are not capable of delivering the energy. The examples of R, L, C. And bilateral and unilateral elements. Bilateral elements means the impedance offered by the element is same even though the current direction is reversed. The best example for the bilateral elements is R, L, C. And the unilateral elements. Unilateral elements means the impedance offered by the element is different for the different directions of the current. The best example is the diode. And linear and non-linear elements which obeys Ohm's law is called the linear elements, and elements which does not obeys Ohm's law is called the non-linear elements. Linear elements means the examples. So what are the examples? Again it is R, L, C. Non-linear elements is diode. Identify that diode is examples for the unilateral element. Diode is a best example for the non-linear elements. R, L, C examples for the bilateral element. R, L, C examples for the linear elements. Time variant and time invariant elements. Yes, and next one is called the lumped and distributed elements. So these are the classification of the elements. So the most important elements in our electrical circuits. Coming to the next intro question. So what is the property of resistor? How it will be formed?
So resistor, is a two terminal element which is represented like this. Okay, it is denoted with R. What is mean by resistance? Resistance is a property of a resistor which opposes the flow of free electrons. Okay, so I will take a conductor here. And this conductor is excited with the DC supply, and conductor which consisting of a large number of free electrons at room temperature, and the electrons are attracted by the positive terminal of the supply and repelled by the negative terminal of the supply. The electrons are attracted by the positive terminal of the supply and repelled by the negative terminal of the supply. During this journey of the electron, what will happen? Let us see. See, we are having so many atoms in a conductor. So atoms, compounds, molecules. Okay, this is about the chemistry theory. But conductor which consisting of so many atoms, each atom consisting of electrons, right? Okay, during this journey of the electron, what will happen? It will hit the one more atom, and this atom will releases the electron, and it will move. The electron will move and again hit the one more atom, and it will releases the electron. See here, if you have a straight road, you are riding a bike, and you can easily move with a 60 kilometers per hour. But if you are having a speed breakers, you can't ride the bike with a speed of 60 kilometers per hour. Okay, so you are reducing the speed, again you are increasing the speed. Once the speed breaker comes, then you reduce your speed, right? Bike speed. Okay, similarly, same way, it will hit the atom, means the speed of the electron will be reduces, and this concept can be explained with the help of one element. That element is called the resistor. Resistance, which is a property of a resistor. Resistance is the property of a resistor which opposes the flow of free electrons. George Simon Ohm, he is the scientist. Coming to the next interview question, who invented the resistor? George Simon Ohm. He is the scientist who invented the resistor, and based on his name, the units of resistance is ohm, and the symbol is like this. Okay, resistance is a property of a resistor which opposes the flow of free electrons. And what is meant by conductance? As the name itself, it is a conductance. It allows the free electrons. It is represented with G. It allows the free electrons. The symbol is also same thing here, but you can write the G, and where G is equal to 1 by R. The resistance units are ohm, and you can write in an opposite way. The resistance of conductance is mho. Our symbol is like this. Okay, define resistance and conductance. Okay, and the resistance is directly proportional to R is directly proportional to length of the conductor. That means if you take a small wire, a small conductor, let us say 1 centimeter is equal to 1 ohm. 1 centimeter is equal to 1 ohm. And as I am taking the equal length, BC length is equal to AB length, okay, right? So you can add it in series here. What will happen? So this resistance is 1 ohm. Now the total length is 2 centimeters, and that means 2 ohms. If length increases, then the resistance is also increases, and if area increases, you can treat that this is one value of resistance, this is one value of the resistance. If resistances are connected in parallel, 1 by R equivalent is equal to 1 by R1 plus 1 by R2, then plus 1 by R3. If you take a 3 resistors, means 1 by R equivalent is equal to 3 by R, so then R equivalent is equal to R by 3. What I am telling means you can take it as a parallel combination. Yes, this is one resistor, one resistor, one resistor, like that you can take. So if area increases, the resistance value will be decreases. Then we are having one relationship. Resistance is directly proportional to length of the conductor, and inversely proportional to cross sectional area of the conductor. So R is equal to rho L by A, where rho is called the resistivity of the material, and in a simple way he will ask what is the units of resistivity. Rho is equal to RA by L. Resistance units are ohm here, meter square, area units meter, the units are ohm meter. So resistivity units are ohm meter. This is very important interview question. So after that resistance, okay, and then we will discuss about the inductance. What is the property of inductor? What is the property of a capacitor? That is also very important. Yes, what is the property of a resistor? First property is it opposes the flow of free electrons. And coming to the, yes, if you have a power formula, power is equal to V into I, and the V is equal to IR. What is VIR? That is our Ohm's law. Okay, formula of Ohm's law. Yes, now we are entering into our interested subject. Ohm's law is a definition. What is the meaning of Ohm's law? What Ohm said. So if you take a conductor is having a resistance R, and I am giving a supply voltage is V here, and which is a variable. Now the switch is closed here, this switch is closed, then the current always leaves from positive terminal of the supply if one source is there, okay, and always the current flows from higher potential to lower potential. Higher potential is represented with plus, and the lower potential is represented with minus, and the current flows through a resistor, produces a drop V here, and this voltage across a conductor is directly proportional to current flows through a conductor at constant temperature. This is called the Ohm's law, and where V is equal to I into R, that R is called the resistance of the resistor, and the power is equal to V into I. Substitute here I square R. In our electrical subject we can treat that power loss, and also called as a V square by R also. If you substitute I is equal to V by R, and energy is equal to power consumed multiplied with time, What is I square RT? The units of energy is joule, and this is called the heat. Energy, we can call it as a heat. In the coming to this resistance point of view, the resistance always dissipates the energy in the form of heat. So previously in an olden days we are having a tungsten filament bulb. If you switch on the tungsten filament bulb, either it is working for 1 hour. After 1 hour, if you touch that bulb, then definitely you will feel pain, more heat coming from that bulb. So the tungsten filament bulb is the best example of the resistive load. What is meant by load? It consumes the power. What is meant by source means it delivers the energy. Delivers the energy or it delivers the power. Okay, and most of the energy which is dissipated in the form of heat. And if you take a water heater also, which is made up of nichrome plus copper, okay, and if you switch on water heater for 5 minutes, you will get that suppose the temperature of the water is 40 degrees centigrade. If you switch on the water continuously for 10 minutes, what will happen? The temperature of the water will be increases. Yes, see how the electrical engineers are beautiful. So whatever the dissipated energy in the resistor is also used as an useful one to heat the water. So we are having, yes, geyser is also like that. The same principle, the resistance property, why I am telling the examples means, a resistance property, first property is it opposes the flow of electrons, it opposes the electric current or it, yes. Second property is it always dissipates the energy in the form of heat, okay. So we are having a point form of Ohm's law. J is equal to sigma E. From this point form of Ohm's law only, we are having this Ohm's law derivation. Okay, so this you can study in EMF. What is J? Current density. What is sigma? Conductivity. What is E? Electric field intensity. Okay. Next one, inductance. What is meant by inductor? Which is represented with L. Okay. If you take a straight wire, suppose if it is a conductor here, and a straight wire is turned or twisted into number of turns. A straight wire is turned or twisted into number of turns is called the inductor. It is called the inductor here. Inductor like this. See here, inductor. A straight wire is turned or twisted into n number of turns is called the inductor. So the symbolic representation of the inductor is L, and it is represented with Henry. It is represented with Henry. Inductor is also having a two terminals. Yes, sir. When the current which is flowing through the coil, which will produces a magnetic field, produces a magnetic flux lines. So this is called the flux lines. If an inductor is wounded with n number of turns, as I said, a straight wire which is turned or wounded with n number of times is called the inductor. So if n into phi is called the psi, where psi is called the flux linkages. What is psi? Is called the flux linkages. If a current which is flowing through the coil produces a magnetic field which links with the n number of turns, that is called the flux linkages, or also called as the, yes, if current increases, the number of flux lines is also increases. If a number of flux lines increases, what happened to the psi? Where psi is also increases, where psi is directly proportional to I, and psi is equal to Li, where L is called the inductance of inductor. Okay, so inductors symbolic representation, inductance of the inductor. Inductance is the property of a inductor. Inductance is a property of a inductor. Okay, so if it is a alternating magnetic field is given, when alternating magnetic fields are, if you give the AC supply, what will happen? During positive half cycle, north pole, south pole. During negative half cycle, this one is south pole and north pole, right? Like, yes or no? So this is north pole and south pole, and this one is called the north pole and south pole. So the flux lines are interchanged. So negative half cycle is like this. According to Faraday's law of electromagnetic induction, an EMF is induced here. This EMF is called the self-induced EMF. That is a different concept, self-induced EMF and mutually induced EMF. But here we are having only one coil. So this minus sign is according to Lenz's law. Effect will always opposes the cause. And where supply voltage V is equal to minus E, if you go for the transformer action, where V is equal to minus E, yes, and V is equal to, yes, N d phi by dt. Both supply voltage and induced EMF are exactly 180 degrees. That's why the transformer is also called as a phase shifting device. N d phi by dt and V is equal to d by dt of N phi and d by dt of Si. D psi by dt we can call it as a d by dt of Li, where V is equal to L di by dt. So inductor does not allow the sudden changes of the currents. Inductor does not allow the sudden changes of current. Inductor does not allow the sudden changes of the current. Okay. And after this V, then what is mean by current? Yes. Why I am telling means, in order to know the property of the inductor, you should know all these concepts. Otherwise, you can't tell that. Okay, I is equal to from this V by L into integration of V by L into dt, and the power is equal to VI, Li di by dt, and energy is equal to integration of power dt. Energy is equal to integration of power dt, integration of Li di by dt into dt. dt will be cancelled. Then energy stored on inductor is half Li square, and the units of energy is joules here. What is the first property, sir? What is the first property? The property of inductor, it does not allow the sudden changes of the current. The second property is it stores the energy in the form of magnetic field. So these two properties are very, very important as inductor point of view. So it does not allow the sudden changes of current. And the second one is it stores the energy in the form of magnetic field. Stores the energy in the form of magnetic field. Okay, now yes, as we already discussed about the current, and these are the electrons are moving in a particular direction here, and these are the two types of currents, and DC, and this one is called the AC. So during positive half cycle it will be electrons are moving in this direction, opposite direction, and this is about the conventional current direction. See here, the voltage pushes the current here, and here also the voltage, which is a force which is used to move the electrons in a particular direction, and electric power, so which is dissipated here in the form of heat, that is called the electrical energy. And the some power, suppose if you take a bulb here, instead of using the here, you can use the power that is called the 40 watt bulb or a 60 watt bulb, and some part of the energy which is used as the illumination, and some part of the energy is dissipated as a heat. Okay, and next one is called the types of the networks elements is also over, and active elements is also over, and the passive elements, yes, R comma L comma R comma C comma L. So R and C, and this one is called the L. And so this is about the supply which is given to the bulb will be glows. So linear elements also examples, as we discussed, the most important parts here, and the lumped elements and distributed elements also discussed. And the straight line passes through the origin is called the a straight line which is passes through the origin is called linear element. And see here a small examples. Here it is voltage will pushes the current here, but this man is pulling the current, yes, so that is called the opposition. That opposition we can say that it is called the resistor, and this one is called the voltage, and this is called the current. Why I am showing this one is means you have to remember the property of a resistor. So resistor will always opposes the current. And one more point you can discuss here, and limitations of Ohm's law. So limitations of Ohm's law. So what are the limitations of Ohm's law? So this is the most important question. And first of all, V is directly proportional to I at constant temperature. That means you can frame the answer from this. So without constant temperature we can't apply the Ohm's law. Yes, and also second point is called the Ohm's law is applicable for linear elements only. Applicable for linear elements. As we discussed already, what are the linear elements? R comma L comma C, and Ohm's law it is not applicable for. It is not applicable for. Not applicable for non-linear elements. Not applicable for non-linear elements, such as silicon carbide here. For this materials, V is equal to K I power M. Yes, M is always greater than 1. M is always greater than 1. Okay, and where K is called the constant, M is greater than 1. So for that I square, parabola, I cube, like that, I power 4. So if you have for different materials, and those materials we can't apply the Ohm's law. So Ohm's law can be applicable only for wherever the temperature is constant, and it is applicable for linear elements only. It is not applicable for the non-linear elements such as silicon carbide. Okay, so this is about the limitations of Ohm's law. And so yes, we discussed the limitations of Ohm's law. And next, yes, the next element we will discuss. What is the next element is called the capacitor. So what is the property of a capacitor? So he is that is very important question. What is the property of capacitor? What is the property of a capacitor? Okay, and so this is you will take a mobile phone as the best example for the capacitor. Okay, so for understanding purpose, here I am taking two different plates here, and this is the first plate, zinc or copper, and the zinc, this one is called the copper. Okay, once the switch is closed here, that means your 5 volts is appeared, 5 volts is applied to two plates. Here the electron is loses from the first plate through the battery and accumulated on the second plate. It attains a positive charge, it attains a negative charge. Let us say this is called the 1 volt. And similarly, yes, one more electron is removed and accumulated on the second place. Let us say this is called the 2 volts. And yes, one more electron is removed and accumulated. Let us say this voltage is 2.5 volts. Now your phone is charged to 2.5 volts. So how much? Suddenly you got a call, then you disconnect the charger, and now how much it will be charged? 2.5 by 5, that should be equal to 50% it is charged. Now again you can replug the charger after your call is over, and it will start from 2.5. it is not directly going to 5 volts, that means it is not directly goes to 100%. So let us say it is called the 3 volts. This process will be continuous up to 5 volts. This first plate acts as a positive terminal of the supply, and then second place acts as a negative terminal of the supply. After disconnecting the charger, once it will be 100%, and whatever the battery is there, that battery, with the battery only you can use your mobile phone. This charge formation is directly proportional to supply voltage. We can define one constant that is called the capacitance of the capacitor. What is meant by C means capacitance of capacitor. Capacitance of capacitor. Okay, so what is meant by current? What is meant by current, sir? Where I is equal to dq by dt, d by dt of CV, where C into dV by dt, C into dV by dt. So now the capacitance does not allow the sudden changes of the voltages. Yes, even you apply for 2.5 volts, you can replug the charger. It is not directly going to 100%. It will slowly charges from 1% to 100% or 50% to 70%. So why I am telling the examples means you can remember the properties. That properties are very, very important. Inductor property stores energy in the form of magnetic fields. Now it is in electric field. Yes, you can see that what is V is equal to 1 by C integration of I dt. V is equal to 1 by C integration of I dt. What is the power formula? Where power is equal to VI, VI is equal to CV dV by dt, CV dV by dt, where energy is equal to integration of power dt. Integration of power dt is equal to integration of P. P is called the CV dV by dt into dt here, into dt. So what will happen? Energy stored in a capacitor is half CV square joules. What is the first property, sir? From this we can tell the first property. From this we can tell the first property. So property of a capacitor. Property of a capacitor. It does not allow the sudden changes of. It does not allow the sudden changes of the. Yes. Okay, it is not okay. Yes, it does not allow the sudden changes of the voltages. That is the first property. It does not allow the sudden changes of voltage. And the second property is it stores the energy. It stores the energy Yes, it stores the energy in the form of electric field, the form of electric field. Okay, so I will make one comparison table here, and from that you will it will cover the most important questions if you may face in an interviews. Okay, so elements are called elements. Yes, that is first element R, comma L, comma C. And what is the voltage equation here? What is the current equation? What is the power equation? What is the energy equation? So V equal to IR here, and I is equal to V by R, and the power is equal to I square R or V square by R, and energy or heat is equal to I square R T joules. And if you go for the L, V is equal to L di by dt, L di by dt, and I is equal to 1 by L integration of V dt, and the power is equal to Li di by dt, energy is equal to half Li square, and V is equal to 1 by C integration of I dt, and I is equal to C dV by dt, power is equal to CV dV by dt, and energy is equal to half CV square. So these are all about the comparison table is why I am drawing the comparison table. Suppose from this table only you can tell that yes, voltage what is the inductor property, it does not allow the sudden changes of the voltages. What is the capacitor property, it does not allow the sudden changes of the voltages. Sorry, here it is sudden changes of the currents, here sudden changes of the voltages. And the inductor property is half Li square. Yes, it stores the energy in the form of magnetic field, it stores the energy in the form of electric field, it always dissipates the energy in the form of heat. Okay, now the most important part coming to the active elements. Active in an active elements. Okay, in an active elements. Okay, what is dependent source and independent sources? What is mean by independent sources and dependent sources? Differentiate between these two. Independent, yes, sources means which delivers the energy, sorry, it delivers the energy which is independent on another sources, another elements. Okay, so independent sources, how many types of independent sources are there? There are two. One is called the ideal source and another one is called the practical source. And also, what is the symbolic representation of ideal? What is the symbolic representation of independent sources? So independent sources are represented with a circle. See here how many interview questions are covering in this chart. First of all, what is meant by independent sources, and how many types of independent sources are there? What is the symbolic representation of the independent source? And how many sources we are having? Two sources. What are they? Voltage source here, voltage source, and another one is current source. In an ideal also we are having a voltage source and current source. In a practical also we are having a voltage source and current source. So this is about the independent sources. Now coming to the next classification, yes, what is meant by dependent sources? What is mean by dependent sources? Dependent sources. So dependent sources are represented with rhombus. First question. dependent sources, it delivers the energy, it delivers the energy, it delivers the energy, it delivers the energy which is dependent on circuit elements or another elements, that means another sources, right? Yes, how many types of dependent sources are there? There are 4. Voltage dependent, yes, voltage dependent voltage source, and the second one is voltage dependent current source, and the third one voltage dependent, yes, current dependent current source, current dependent current source, and the last one is current dependent voltage source, current dependent voltage source. As how you can draw that? So voltage dependent voltage source means it delivers the energy which is dependent on voltage. It delivers the energy which is dependent on voltage. Okay, circuit elements, it depends upon circuit elements. Voltage source, as the name itself, it is represented with rhombus here. Yes, voltage source means plus and minus, which is dependent on what? Voltage, sir. I can write it as V is equal to KV1. And second one, see here, it is a current source. Current source is represented with arrow. Okay, and dependent means it is represented with rhombus, where I is equal to KV1. So what happened to the current dependent current source? Yes, it is an arrow current source, current dependent, where I is equal to KI1. But here current dependent voltage source, plus and minus V equal to, which is dependent on what? Current KI1. So voltage source produces a energy which is dependent on voltage. Current source delivers the energy which is dependent on voltage, and current source which is delivers the energy which is dependent on current, and voltage source delivers the energy which is dependent on current. So these type of 4 types of the dependent sources are there. And the next question is coming to the next question, what is the difference between ideal voltage source and practical voltage source? Ideal voltage source and practical voltage source. So ideal voltage source comes under the category of what? Independent source, which is represented with circle with plus and minus. Circle with plus and minus, we can call it as a ideal voltage source. Yes, so this is a symbolic representation of the ideal voltage source. The symbolic representation of the practical voltage source, is V. Yes, in series with resistance. Ideal voltage source, the internal resistance, source resistance is equal to 0. But coming to the practical voltage source, RS value should be small. RS value should be small. Yes. Why it should be small? That is the next question. Yes, sir, we are accepting that point. Internal resistance of the ideal voltage source is 0. internal resistance of practical voltage source we are having, or but it should consisting of a lesser value. Why? Okay, I will take a small example here for a practical voltage sources. So practical voltage source. So I have a 5 rupees in my pocket and the source resistance is 1 ohm and the load resistance is also 1 ohm. Load resistance also 1 ohm. I don't know that KVL and KCL concepts now, but I have a 5 rupees in my pocket, but 2 persons are there. I want to give the 5 rupees to 5 rupees equally to both of them. Now, so I have a 2.5 rupees to one person and I will give the 2.5 rupees to another person. Okay, that means you can treat that this is called the useful output. Useful output. So out of 5 rupees, 2.5 rupees is wasted and the remaining 2.5 is utilized, means how much efficiency you can calculate? Only 50%. Suppose if you consisting of a lesser value, let us say this is called the 1 ohm, 0.1 ohm, and this one is called the 1 ohm here. Now what is the current which is flowing? Yes, current is equal to 5 by 1 plus 0.1 is 1.1, approximately equal to 4.99 amperes or 4.9 amperes, and here it is 0.1 volts and here it will be 4.9 volts. As I said, the load voltage is 4.9, internal drop is 0.1. Is the second case is best or first case is best? First case is worst, because worst. Why? 50% of the source voltage will be wasted, and here only 0.1 volts is the drop, remaining 4.9 volts will be applied across the load. Means the source resistance, you have to design the source resistance, with a lower value or higher value. So design the source resistance with a lower value. And coming to the next interview question, this is very important. Why RS should be in series with voltage source, not in parallel. Why? So if you connect a voltage source in parallel with resistance, okay, so I can treat that, let us say this voltage is called the, what is this voltage is called the VAB. Okay, let us say AB is called the load. If I am connecting a parallel resistance, what will happen if I am connecting a parallel resistance? So in order to understand this, always the current leaves from positive terminal of the supply. Here open circuited current will be 0 and the entire current is passes, will be passes. Yes, and always the current flows from higher potential to lower potential. I can write it as IR minus V is equal to 0 and V equal to IR. What is this, sir? Means KVL, Kirchhoff's voltage law. Algebraic sum of voltages in a closed loop is equal to 0. You can remember that I have a 10 rupees in my pocket and 10 rupees will given to only one person. That's it. So this VAV value is equal to V only. But what is meant by ideal, sir? Ideal means 100%, sir. It is not at all possible, sir. Why? Because there is some drop is definitely present, but the drop should be minimum. Then only more utilization of the voltage or more utilization will be taken place. Okay, if I am connecting a parallel resistance, the voltage source in parallel with resistance. Coming to the next interview question, the voltage source in parallel with resistance can be equivalent to voltage source only. The voltage source in parallel with resistance is equal to voltage source. Why? Because if you apply the KVL at these two terminals, the same voltage will be appeared. But if you are connecting a series resistance here, yes, RS here, and this value should be small, and then the remaining voltage will be appeared across the load. That's why RS should be in series with the voltage source, not in parallel. Okay, so operation on independent sources, that is also very important. Can you tell the examples or operation on independent sources? This is a interview question. Okay, so first, what is our first observation, sir? If a voltage source in parallel with resistance, can be replaced with voltage source, sir. Okay, and the second observation is, if you are connecting a voltage source here V1, and this one is called the V2 here, V2. Now what is this one? Okay, so you can go in a clockwise direction. Yes, plus is connected to minus here. You can see plus is connected to minus, means minus V2 minus V1. Here also entered into minus, he entered into minus. We don't know KVL, but okay, entered into minus, means both are added. So V1 plus V2. The best example is remote. A TV remote, if you observe that, you can kept that, so here in this fashion. Yes, plus is connected to minus, then only remote will work. If both are kept at the same position like this, one more is also like this. Let us see the third case here, the interesting case. The third case, if you go for this one, if you are connected in, so this is V1 here, and same opposite with V2, what will happen? So coming to the clockwise direction, it is entered into plus, it is entered into minus, so obviously it is a subtraction only. If V1 is greater than V2, then V1 minus V2 here. If a V2 is greater than V1, say the same polarities as that of the V2 here, V2 minus V1. But if a V1 is equal to V2, what will happen? V1 is equal to V2 is equal to 0 volts. Yes, that's why if both the batteries or cells is kept at the same position or the same manner, okay, plus is connected to plus, see here, plus is connected to plus or minus is connected to minus, what will happen? Then the resultant voltage will be 0. And also, if two voltages are connected in parallel, now there is no question. If V1 is equal to V2 only, then KVL is satisfied. If V1 is not equal to V2, KVL is violated. So here I will explain what is a KVL, Kirchhoff's voltage law. I am taking a 2 resistors here. Let us say this is 1 ohm, this is 2 ohms here. I don't know about the polarities, 3 volts, and this is having a 1 volt, and this is also 2 volts here. Okay, how it came, I don't know. Okay, by doing calculations, we can know that. Yes, sir. Okay, 3 volts, 1 ohm and 2 ohms. Let's check it. 1 ohm and 2 ohms both are connected in series. Again, we want to explain what is the series connection. How can you say that it is a series connection? These are all questions comes into picture. Okay, and always the current leaves from positive to now this apply. Current flows from always higher potential to lower potential. Higher potential to is repelled with plus. Lower potential is repelled with minus. Okay, and current enters into the positive to minus. So current is in this direction. We can treat that as a voltage drop, and minus 2 plus we can treat it as voltage rise. This is also very important. Okay, what is my understood means by applying a KVL to the slope, algebraic sum of voltages in a closed loop is equal to 0. Algebraic sum of voltages in a closed loop is equal to 0. Current enters into the positive terminal can be treated as positive S plus 1. Current enters into the positive terminal can be treated as positive S plus 2 here. But here you can observe that current enters into the negative terminal, minus 3 is equal to 0 or not? Yes. Algebraic sum of the voltages in a closed loop is equal to 0, or sum of the voltage rise is equal to sum of the voltage drops. 3 is equal to 1 plus 2. This is called the Kirchhoff's voltage law statement. Kirchhoff's voltage law. Okay, so next interview question. Differentiate between ideal voltage source, ideal current source, ideal and practical current sources. Ideal and practical current sources. Practical current sources. Yes. Is it comes under the category of, yes, is it comes under the category of independent sources. Independent sources are represented with circle. Independent sources are represented with circle, and the current sources are represented with arrow. Yes, it is represented with I, and there is no internal resistance. You can see, looks like internal, there is no internal resistance, but what is the value of the internal resistance? That is very important. If you go for the ideal voltage source, internal resistance is 0, but here it is never be equal to 0. And if you have practical current sources, the practical current source resistance should be connected in series or parallel. Let us see. I am having a 5 rupees. That 5 rupees is given to 1%. 100% is not possible. That is only possible in ideal case only. We are telling that ideal case means entire current is passes through the load here. Entire current passes through the load. Here also entire current not passes through the load. Let us say this current is called the IL. If you want to pass the entire current to the load, what is the resistance of the internal is infinity. If it is a infinity, the current value is 0 to the sources. The remaining current is I here. But here, some part of the current is passes through the internal. But how much current? Again it is 5 and 5. Again it is 5 and 5 means, see, two equal resistances. Let us say this is 10 amperes, sir. This is 1 ohm, sir. This is also 1 ohm, sir. 10 and 10 rupees I am giving to 2 persons. So 5 amperes, sir. This is 5 amperes. What is the utilization of the load? 50%. But you have to reduce this internal current. You can design this resistance with a large value of the resistance. Then let us say this is 0.1 amperes of the parallel resistance. The remaining current 9.9 amperes is going through the load. What I want to convey is RP should be very high. RP should be very high. RP should be very high. Okay, so if you observe this, parallel resistance should be connected, that should be very high. The internal current value will be lower. Okay, and now, so what is the characteristic, sir? If you go for the if you go for the I, and which is independent of the voltage across the load. What is the definition of ideal current source, sir? Current source, it delivers the energy which is independent of voltage across the load. Voltage across the load. Voltage across the load. But here it will be dependent. If you draw the current versus voltage value will be decreases, or sorry, current value will be decreases. Current value will be decreases if you vary the voltage. So this is about the voltage, and this one is called the current. This one is called the current. Yes, if you vary voltage across the load, you can vary, and current is uniformly constant here. If you vary the voltage across the load, so this one is called the voltage across the load. As the loads are changes and the currents is also changes and drop is also changes, the current load current will be somewhat drops here. And if you go for the ideal voltage source, means ideal voltage source, definition of ideal voltage source, which delivers the energy, which is independent of current flows through the load. Yes, current flows through the load which is independent. Okay, that means V is directly connected to load here. V is connected to load. So voltage which is independent of the load current, and if you this is called the voltage, and this one is called the current, load current, voltage and current. So voltage and current, once again I am telling clearly. So this is about the voltage which is independent on the load current, means load current you will take the reference, but the voltage value is uniform. Voltage value is uniform. But if you go for the practical case, even load current is varies, what will happen? The load voltage value will be decreases. V equal to Vs. This value is called the load voltage. Load voltage. So how you can frame the equation now? V is equal to S. VL is the load voltage plus I into Rs. So VL is equal to V minus I into Rs. So what is IL? IL increases means what happened? VL value will be decreases. So the VL value will be decreases. Okay. So once again I am clearly telling that, so practical voltage source which is having a resistance is in series with the voltage source, and which should consisting of a lower value, and the ideal means the resistance value should be equal to 0. Internal resistance is 0. Ideal voltage source which delivers the energy, which is independent of current flows through the load. Voltage means you should concentrate on load current, okay, and current means you should concentrate on load voltage. Ideal current source which delivers the energy, which is independent of voltage across the load. And the practical voltage source, coming to the practical voltage source, resistance Rs value should be smaller value, which delivers the energy which is dependent on current flowing through the load. Yes, current flowing through the load, it will be dependent. That's why we are getting VL is equal to V minus IL into Rs. Okay, similarly for the ideal practical current source also, it depends upon the resistance, and ideal current source internal resistance will be infinity. Okay, and these are the very basic questions. And coming to the practical current source, is a higher value. You should have a higher value. So now some operations we can go for the operations on current sources. Means if two current sources are connected in parallel, let us say this is I1 here and this is called I2, and now what is the resultant current here? Okay, I will explain KCL, Kirchhoff's current law. So I will cover Kirchhoff's current law here for understanding purpose. So Kirchhoff's current law. Kirchhoff's current law. Okay, sum of the currents towards the node or junction, is equal to sum of the currents away from the junction. So how many currents are towards the junction is two currents, I1 plus I2, and the one current is away from this junction where I is equal to I1 plus I2. So what is the meaning of junction or node? So junction means two or more branches, three or more branches are connected to one common point. See, if it is a junction means, see here how many elements are connected now, 1, 2, 3, 4. So let us say this is called the I1 here, and this is I2 here, and this is I3, and this one is called the I4, and two currents are towards the node. Yes, two currents are away from the node. Sum of the currents towards the node is equal to sum of the currents away from the node, where I1 plus I2 is equal to I3 plus I4. This is called the KCL. Okay, right. So now I is equal to, now the representation is where I is equal to I1 plus I2. I1 plus I2. So one more thing, the most important part here, yes, let us say this is I1, this is I2 here. Now what is the equivalent one? What is the equivalent? If two current sources are having equal values are connected in series, let us say 5 amperes and 10 amperes, 5 amperes and 5 amperes both are connected in series. Now what is the value? This type of interview questions, fundamentals are very, very important. So I1 is equal to I2 only, KCL is satisfied. If I1 is not equal to I2, KCL is violated. KCL is violated. Okay, and what is the next one? Yes, we are accepting this point. And the current source in parallel with as in series with resistance, and this is also very, very important. Current source in series with resistance is equal to what? Current source in series with resistance can be replaced with current source only. Can be replaced with current source. Why? Because here also I only, after that R only I. Okay, and the current source in parallel with the resistance. Okay, and so that we are considering. I think we are covered the operation and independent sources, voltage source and current sources. Okay, coming to the next question. So define Kirchhoff's voltage law is already over. So Kirchhoff's voltage law, algebraic sum of voltages in a closed loop is equal to 0. So let us say this is R1 and R2, as I am giving the voltage. Always the current leaves from positive terminal of the supply. Current flows from higher potential to lower potential. Here also current flows from higher potential to lower potential. The sum of the voltage rise is equal to sum of the voltage drops. Our current enters into the positive terminal can be treated as positive. In some of the textbooks, he is giving current enters into the positive terminal can be treated as negative. Don't confuse. Nothing is the problem. Okay, as per standard books, current enters into the positive terminals can be treated as positive. Current enters into the negative terminal can be treated as negative. So minus V plus V1 plus V2 is equal to 0 here, where V is equal to V1 plus V2. Okay, so here we are having only one voltage source. And what is the basis for KVL? So KVL, Kirchhoff's voltage law, which bases on law of conservation of energy. This is very, very important. Law of conservation of energy. So what is law of conservation of energy? Energy is neither created nor be destroyed. Energy is neither created nor be destroyed. It will convert one form to another form. One form to another form. Okay. So Kirchhoff's voltage law, yes, input voltage source and which is given to the equal to the, means voltage sources is equal to the, and voltage drops, sum of the voltage drops. Okay, it never extinguishes. And Kirchhoff's current law, as we discussed in the previous questions, yes, this one is I1 is coming, I2 is coming, and I3 is outgoing current, and I4 is outgoing current. So by applying KCL, I1 plus I2 is equal to I3 plus I4. And what is the basis for KCL, Kirchhoff's current law? It works on the principle, or it is based on the law of conservation of charge. law of conservation of charge. And similarly, yes, charge neither be created nor be destroyed, okay. After that, so draw the practical inductor and explain about each element. Okay, so each element already we discussed. So what is the symbolic representation of the practical inductor? As I said, what is the meaning of inductor? A straight wire, a straight conductor which is turned or twisted into number of turns. Conductor is made up of copper. Yes, copper is consisting of some resistance. So this is the symbolic representation of the pure inductor. But if you go for the practical cases, and some R is also present. Yes, resistance is present and inductance is also present. For this, L is greater than R, or XL is greater than R. XL is greater than R. We will discuss what is XL in the next coming interview questions. Okay, and if you take a choke coil, so let us say this is called the choke coil. And the choke coil is also that is there in tube light. Now we are using LED bulbs. Previously we are using choke coils. And the choke coil means coil consisting of a resistance and as well as the inductance. Okay, and some voltage drop will be taken place at R, some voltage drop will be taken place at L. So practical capacitor, so the capacitor value, if you go for the capacitor, so this is the symbolic representation of the capacitor. So this is about the charging current. In order to deviate the charging current, you can connect a small value of resistance. This is called the small r. Okay, so this is the symbolic representation of practical capacitor, representation of the practical capacitor. This is very, very important. For an inductor, the resistance is in series. For capacitor, the resistance is in parallel. And ideal RLC elements are linear. Yes, linear already we discussed. And dependent sources is also we discussed. What is meant by mesh and what is meant by loop? Okay, so mesh and loop. Okay, if I am taking a one circuit here, let us say this is A, B, C, D, E, F. Okay, so first one A, B, C, D, E, F, loop 1, and loop 2 A, B, C, F, A, B, C, F. So this is loop 2. Okay, and the loop 3 C, D, E, F. This is a loop here, and this is also loop here. This one is 1 and this one is 2 and this one is called the 3. And 1, 2, 3 are called the loops. Okay, and we can say that BC is a one branch, and we can call it as a junction. Here 1, 2, 3 elements are connected, and here also we are having a junction, right? 1, 2, 3 elements are connected, and 3 or more elements are connected to one common point. We can say that it is called as a junction or principal node. Node means 2 elements are connected. Here see, voltage source and the resistance both are connected, and it is a node, but it is not a principal node. Principal node means 3 or more branches are connected to one common point. Then we can say that it is a principal node. Okay, whatever, maybe right. So now what is mesh? In this mesh, loop 2 and loop 3 are called meshes, but this is not a mesh. Mesh is a loop which does not contain inner loop. Mesh is a loop but which does not contain inner loop. A path which is traced by the loop wherever the starting point is there and the finishing point both are same, then we can call it as a loop. See here, we have started at A, ABCFA, ABCFA and FA, see here, FA and ABCFA and CDEFC, and so these are first set 2 and 3 are called the meshes and also loops, okay, 2 and 3, but this one is not a mesh. Why? Because it consisting of a inner loops. Okay, mesh is a loop which does not contain the inner loop. Okay, and we discuss what is a loop value and difference between the mesh and loop. Loops, branches and nodes of a given circuit. Yes, if you take a this given circuit here, so this is BC is called the one branch, CD is called the one branch, D is also one branch. Okay, and CF is also called as a one branch. Junction or node, junction means 3 or more branches are connected to one common point. 3 or more branches are connected to one common point. 3 or more branches are connected to one common point, and 2 or more branches are connected to one common point is called as a node, but it is not a principal node. It is not a principal node. Okay, and these are all the important questions. So passive elements is also we discussed the passive elements. Okay, now so R comma L comma C are over, and ideal voltage source and practical voltage sources, what is the internal resistances. Now what is when the elements are said to be connected in series, what are the conclusion points? These are very, very important. Okay, sir, what is mesh series, sir? Series means series, is it? I am taking a two elements are having a different values of resistances R1, and here also this resistance is R2 here, R2. Okay, and this is the starting end and finishing end, starting end and finishing end. The finishing end of the first resistor, the finishing end of the first resistor is connected to starting end of the second resistor. Then we can call it as a both the resistors are connected in series, or if the current flows through the flows through the elements is called is same, then the elements are connected in series. Okay, once it will be excited with a DC voltage source here, always the current flows from higher potential to lower potential, and let us say this is V1, and always the current flows from higher potential to lower potential. The conclusion points are very, very important. If the finishing end of the first resistor is connected to starting end of the second resistor, we can say that it is connected in series, or if the current flows through the elements is same, then we can say that if the elements are connected in series. Okay, so by applying KVL to this loop, Kirchhoff's voltage law, V is equal to V1 plus V2, and from this I can write it as I is equal to I1 is equal to I2. I is equal to I1 is equal to I2. In a series connection, the current is same, but the voltage is divided. That you have to remember. Voltage is divided. So this is I into R equivalent. Let us say this is I into R1. This one is I into R2. The resistances value is equal. Resistances values are added, and the R equivalent is equal to R1 plus R2. One more interview question is covered here. Two resistances are connected in series. What is the net equivalent resistance? This is a simple question only. R equivalent is equal to R1 plus R2. Okay, and so in a series connection, what is the first conclusion? Current flows through all the elements is same, but the voltage is divided. One more point. So one more, I will take a small circuit. I will take a small circuit here, and let us say this is called the 1 ohm here, and this is called the 2 ohms. And as I am applying a 3 volts here, now the current is coming like this, and these two resistors are connected in series. Yes, 1 plus 2 is equal to 3 ohms. where I is equal to what is the V by R equivalent? As I is equal to V by R equivalent 3 by 3, that should be equal to 1 ampere. Yes, I value is 1 ampere. So always the current flows from higher potential to lower potential. What is your observation? What is your observation? You can tell that observations are very, very important. So low resistance in a series circuit, low resistance, low voltage drop. High resistance in series, high resistance has high voltage drop. This is my third observation. So one more thing, the most important part here, and why the resistance symbol is like this? Why the resistance symbols is like this? Why not like this? This is an interview question. IIS interview question. As we discussed in the previous question, when the atom, we are having a conductor which is consisting of more number of atoms. The electrons, during the journey of the electron, what will happen? It will hit the one more electron, the speed of the electron will be reduced as, yes or no? So just like a mechanical braking means, if you have a speed breakers while you are riding a bike, then your speed will be reduced as yes, when the speed breaker comes, and after that you can increase your speed with the help of accelerator, and also once the speed breaker comes, you can reduce the speed. So that means similarly speed breakers will reduce as the bike of the speed. Similarly this resistance is reduces, yes, reduces the speed, again increase the speed, reduces the speed, increase the speed. That's why the symbolic representation. Yes, you can take the current, here, you can take this current in this fashion. Yes, current in this fashion. Now current is coming, increasing, again it is decreasing, again increasing, again it is decreasing. So that's why the symbolic representation of the resistor is like this. Symbolic representation of R. And why inductor is represented is like this. Why we are not taking a single conductor, right? So which is also produces a magnetic field. See here, this straight wire is wounded with n number of turns. What will happen when the current flows through the coil? Whenever the current flows through the coil or inductor, it will produce a magnetic flux lines. These flux lines linking with the number of turns is more, but here only we are having a number of turns is equal to 1 only. But number of turns, if you wound it for 100 times extra magnetic flux will be produced, then psi will be increases, then psi is equal to Li, where Li is equal to psi by I, and the psi value will be increases. That's why the symbolic representation of the inductor is like this. Okay, symbolic representation of the pure L. This one is called the pure L. Practical L means which consisting of a resistance. Pure L does not have a resistance. The internal resistance drop will be taken place. Internal resistance voltage drop will be takes place in a capacitor. So two plates are separated by a distance. Yes, two plates are separated by a distance d here, and C is equal to epsilon naught epsilon r A by D. This formula is also very, very important. If a distance between the two plates are increases, then the capacitance value will be decreases. So I think in your power system you may study about the capacitance effect for the long transmission lines, for the short transmission lines and medium transmission lines. Short transmission lines, the capacitance effect will be negligible, and the medium transmission lines effect is medium, and long transmission lines effect is very high. So under no load conditions also you can have that effect is called the Faraday effect. Receiving end voltage is greater than that of the sending end voltage due to the charging capacitance. Okay, right. So capacitance epsilon naught epsilon r. Epsilon is, what is my epsilon, sir? Permittivity. epsilon is called the permittivity. Capacitance is directly proportional to cross sectional area of the plates. Okay, and so this is also very very important, and these three are very important. Okay, so this is also over here, and passive power sign convention already we discussed, plus to minus. Okay, yes, charge QV diagram, yes, already we have written Q is directly proportional to CV here. Q is directly proportional to voltage. As voltage increases, Q is also increases. It is a straight line which passes through the origin. It is a straight line which passes through the origin. Okay, already almost all the points were discussed. Okay, now what is meant by voltage division rule? Voltage division rule. So voltage division rule is applicable for series circuits or parallel circuits or any combination. Let us see. Voltage division rule means if I am having a resistance R1 and R2, both are connected in series here, R1 and R2, as I am giving the supply voltage is V and the current is coming like this, and always the current flows from higher potential to lower potential, higher potential to lower potential, and V is equal to V1 plus V2, and R equivalent is equal to, from this we can have written R1 plus R2, and V is equal to I into R equivalent. I can write it as I into R1 plus R2, I into R1 plus R2. And what is V1 now? I into R1. Substitute here. From this I is equal to, I is equal to V by R1 plus R2. Substitute here. V by R1 plus R2 into R1, and similarly V2 is equal to I into R2 V by R1 plus R2 into R2. This is about the voltage division rule. So voltage division rule is equal to voltage across R is equal to voltage across any resistor is equal to, or R1 is equal to total voltage into same resistor by total resistor, and this can be used for only two resistors are connected in series. Suppose sir, if a three resistors are connected in series, you can make the three resistors to two resistors, then you can apply the voltage division rule. Coming to the next question. So what is the current division rule, and what is the conclusion points from parallel operation? So conclusion from parallel operation. So parallel connection of two resistors. Okay, so in a series connection, what is our observation? Current flows through all the elements is same, and also voltage is divided. So that is called that is the first observation and the second observation. And if I am taking the two resistors R1, and this is the starting end and finishing end, and one more resistances, this is starting end and finishing end here. The starting ends are connected and finishing ends is also connected. Starting end of the two resistors is connected and finishing end of the two resistors is connected. Take a terminal out from the starting terminal and take a terminal out from the finishing terminal, then these two elements are connected in parallel. So it is somewhat tough to remember, but in an easy way I will tell you. If I am applying a voltage source here, and the current always leaves from positive terminal of the supply. If a junction is there, then the current will be divided here, and let us say this current is divided as I1 and I2 here. By applying a KCL at this point, I is equal to I1 plus I2. Always the current flows from higher potential to lower potential, and this is plus and minus, and this is also plus and minus. The current flows through R1 produces a drop is V1 here, and the current flows through R2 produces a drop here V2, and simply I can write it as V is equal to V1 is equal to V2 because it is a parallel connection. The voltages are equal. Theoretically it is correct, but how can you prove it where V is equal to V1 is equal to V2? In overall electrical circuit subject, you can remember wherever loop is there you can apply KVL, wherever junction is there you can apply KCL, and Ohm's law, and if it is V equal to IR and I is equal to V by R, and open circuit properties and short circuit properties. These are very important. If you remember these 5 concepts, your circuit subject is very easy. So here I have one loop, I can apply the KVL to the first loop here, and the current enters into the positive terminal can be treated as positive S plus V1, and here the current enters into the negative terminal S, it is a minus V2 is equal to 0, and where V1 is equal to, V1 minus V is equal to 0 here, V1 minus V is equal to 0, and V is equal to V1. The first statement is completed, and apply KVL to this loop also. Apply KVL to this loop. Current enters into the positive terminal S plus V2 minus V1 is equal to 0. Then V1 is equal to V2 here, and V is equal to V1. So finally, the voltages in a parallel circuits are equal. Here there is no resistance, series resistance is not present here, and if a series resistance is present, then some drop will be taken place, the remaining voltage will be applied across these two combinations. And now from this equation, from this I is equal to I1 is plus I2, I can write it as V by R equivalent, and this one is called the V by R1, and this is V by R2 here, and because V is equal to V1 is equal to V2, I have a relation, that is I1 by R equivalent is equal to 1 by R1 plus 1 by R2, then R equivalent is equal to R1 R2 by R1 plus R2. Yes sir, what is your first observation, sir? What is your first observation? In a parallel connection, the voltage is same. The voltage across all the elements is same. And one more thing, in a parallel connection, the current is divided here. See, what is the current which is coming here? I2. And what is the current here? Yes, I2 only. But here current is I1. So apply KCL at this point, and the same current I1 plus I2 is equal to I. Whatever the current which is divided and the same current is written back, then the elements are connected in parallel. Okay, otherwise we won't tell that it is in a parallel connection, the current is divided, the same current is written back, then the elements are said to be connected in parallel. Okay, in parallel voltage is same, and also the current is divided. In a series, current is same, voltage is divided. So these two are the observations from the parallel connection. So these are very important. And one more point, low resistance. In a parallel connection, low resistance means higher current, high resistance means lower current. High resistance means lower current. Okay, so from this we can call it as V is equal to I into R equivalent, then I into R1 R2 by R1 plus R2, then V1 is equal to I1 R1, that should be equal to V here, both you can equal to I1 R1 is equal to I into R1 R2 by R1 plus R2, R1 R1 both are cancelled, then the current flows through resistance R1 is equal to total current into opposite resistance by total resistances, and this is a very important. Current flows through R, current flows through any resistor, or here I can explain for R1. R1 is equal to total current into opposite resistance, R2 here, opposite resistance by total resistance. opposite resistance by total resistance. So this is about the current division rule. Current division rule is applicable for only two resistors are connected in parallel. Suppose if n number of resistors are connected in parallel, you can make that n minus 1 resistances are connected combined into one and remaining with parallel combination of another one. So you can made that n number of resistors to two resistors connected in parallel, then you can apply the current division rule. Okay, so this is about the Kirchhoff's voltage law and Kirchhoff's current law. And now what is meant by steps for mesh analysis? What are the steps for the mesh analysis? As the name itself, it is a mesh or loop analysis. It is a combination of KVL plus Ohm's law. KVL plus Ohm's law. First of all, if you take one small circuit here, what are the steps are needed? What are the steps are needed for, so let us say this is R1 here, R2 here, R3, and this is V1, V2. So first of all, what are the fundamental loops? That is called the meshes you have to mark here, and this is about the I1 and this is about the I2. So first, what is the first step means? Identify the number of loops. Identify the number of loops. And the second one is assume loop currents either clockwise or anti-clockwise. Either clockwise or anti-clockwise. And third one, mark the polarities. Mark the polarities based on the loop current direction. Mark the polarities based on loop current direction. Loop currents directions. And fourth one, apply KVL and Ohm's. Apply KVL and Ohm's law. So apply KVL and Ohm's law here. Then fifth one, solve the equations and get the solution. So these are called the steps for mesh analysis, and the mesh analysis is a combination of KVL plus Ohm's law. Okay, how to do the problem, that is not required in an entry point of view. So first of all, identify the loops. Yes, we are having two loops. We are taking a clockwise currents and always the current flows from higher potential to lower potential here, and then apply the KVL and Ohm's law and get the two equations, unknown equations, and solve those two equations and get the currents, unknown currents. Okay, and next one is called the steps for nodal analysis. This is very, very important. Steps for nodal analysis. What are the steps for nodal analysis? Nodal analysis. Okay, first of all, identify the number of nodes here. How many number of nodes? Principal nodes are junctions. So V1, R1, R2, R3. So this is one junction and this is a second junction here. Why? Because these two are not the junctions. This is a node but is not a principal node. Wherever three or more branches are connected to one common point, then we can say that it is a node, and one of the node is taken as the reference node here. One of the node is taken as the reference node, and that is maintained at zero potential, and for the remaining nodes assign the voltages. Assume that all the currents are leaving from the node. Then apply KCL I1 plus I2 plus I3 is equal to 0. then Ohm's law. Nodal analysis is a combination of KCL plus Ohm's law. This is also very, very important. Okay, and supermesh analysis. What is, when you are, and he is asking like that, when you apply the supermesh analysis, or also in between, see here, if you take a this one, now I am having a one current source here, and this is a circuit here. Let us say this is a 2 amperes or I, and this is V1 and V2, this one is R1 and R2. So you should remember this, whenever in between two loops, if the current source is present, you can't find out the resistance across the current source. You can't apply KVL to this loop here. Okay, so I1 minus I2 or I2 minus I1 is equal to 2 amperes. Why? Because I guess I2, as I said, I2 plus 2 is equal to I1, I2 minus I1 is equal to 2 amperes. I2 plus 2, yes, is equal to I1. I2 minus I1 is equal to 2 amperes. I2 minus I1 is equal to S minus 2 is equal to S. I2 minus I1 is equal to 2 amperes. Yes, resultant is positive, right? Yes, I2 minus 2 equal to I1, I2 minus I1 is equal to 2 amperes. Okay, in between two loops, if the current source is present, you can apply the supermesh analysis. Sir, when we will apply supernode analysis means, if this current source, see here, sorry, supermesh analysis, this current source can be expressed in terms of the loop currents. And after that, for the remaining loops, you can apply KVL. So supermesh analysis is a combination of KCL plus KVL plus Ohm's law. This is very, very important. See, I1 minus I2 is equal to 2 amperes. Sorry, I2 minus I1 is equal to 2 amperes. That is called the KCL. And if you apply the KVL to this remaining loops, which is not included the current source, then you can have equations, right? So KVL plus Ohm's law plus KCL is called the supermesh analysis. Supernode means in between two nodes, if you have a, in between two nodes, if you have like this, in between two nodes, if you have a voltage source, then we can call it as a supernode analysis. Anyway, KCL plus Ohm's law you can apply, and this voltage source can be expressed in terms of the node voltages. Yes, V1 minus V2 is equal to this voltage. Then KVL, supermesh and supernode, so which is a combination of KCL plus KVL plus Ohm's law. So at what conditions you can apply, you can remember. So the most important part is called the, what are the open circuit properties? What are the open circuit properties? I will take a small circuit here. Let us say this is 10 volts. And this is 2 ohms here, and let us say this is 3 ohms. Now this is called the open circuit voltage here. What is the open circuit voltage? Is existing or not? So 2 and 3 both are connected in series, but most of them they are confusing that. If you are having a confusion, always the current leaves from positive terminal of the supply, and the current flows through 2 ohms and 3 ohms here. And let us say this is 10 by 5 is 2 amperes, 2 into 4 volts, and this one is called the 6 volts here. VOC, by applying KVL to this loop, you can get the 6 volts directly. Okay, so is there any current is flowing through open circuited wire? No. That means what is the resistance value? Infinity. So resistance is infinity, current is zero, and the voltage is existing. Open circuit characteristics, voltage is existing. Once again, 2 and 3 both are connected in series. Why? Because the same current passes through both the both the resistors, and there is no current which is flowing through this one, and I is equal to 0 value and voltage is existing. And next one is called the short circuit properties. Short circuit properties. What are the short circuit properties? What is meant by short circuit properties? So if you have the circuit here V, and let us say this is a 2 ohms here, 10 ohms, 10 volts here, and this is about the 3 ohms. If these two terminals are short circuited means is that current is flowing or not? Yes. What is the resistance of the short circuited wire? Is there 0 ohms? 0 is parallel with 3 ohms. This current is equal to 0 and the entire current is passes, right? I is equal to 10 by 2 because 0 parallel with 3, 0 parallel with 3 ohms is 0 here, so that is called 5 amperes. Your circuit is reduced to 2 ohms, and this is about the short circuited wire, 5 amperes. Previously, what is the current, sir? What is the current? 2 amperes. Now what is the current? 5 amperes because of short circuit of this 3 ohms resistance. Now resistance value is 0. Now what is the current value? Increases. If this, what is the potential difference between these two? 0 volts. Voltage across the short circuited. So if you remember all these 5 concepts, then you can easily remember the circuits concept. The first one is called the Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law, and open circuit properties and short circuit properties. So these are all very important of the short circuit and open circuit. I am taking one example and I am explaining here. So with this short circuited, so most of them they are having a confusion that short circuit means voltage 0, current 0. Is it satisfies the Ohm's law? Like that they are having so many doubts. See, we are shorting the load terminals. You should remember the shorting the load across these terminals. If that is applicable only for linear elements. If voltage increases, current is also increases. But if it is a short circuited at a particular value of the element, what will happen? At that position, the current value is increases, voltage 0, resistance value is also 0. Okay, and this is about the open circuit properties and short circuit properties. And what is meant by source transformations are? What is meant by source transformation? What is meant by source transformation? As the name itself, it is a source transformation. How many sources we are having? 2 sources. One is called the voltage source and in series with resistance. Voltage source in series with resistance can be transformed to current source in parallel with resistance. This is one of the technique, network reduction technique. What is network reduction technique, sir? As the name itself, it is a network reduction. Any number of resistors can be reduced to single equivalent resistance, or any number of resistors can be in series with voltage source can be reduced to single voltage source in series with the resistance. So what is I value, sir? V by R, sir, for the same value of the resistance. What is V, sir? V equal to IR. So where V is equal to IR. Okay. So this is about the source transformation. Voltage source in series with resistance can be transformed to current source in parallel with the resistance. Now, so what is the importance of delta connection and star connection? What is delta and star? And also, why the conversion is made? Why the conversion is necessary? What conversions are? Why conversion is necessary? Delta to star or star to delta? Why you are going for delta to star and star to delta? Suppose if I am taking a delta connection, if I am taking a delta connection. See, you can apply the voltage source here, you can apply the voltage source here, you can apply the voltage source here, because the three supplies you are giving. So instead of if it is a yes, it is a DC circuit, that's why I am taking the resistors. If it is a AC, I am taking the coils RBC and RCA, A phase, B phase, C phase, or R phase, or A phase, B phase. Okay, and let us say this is called the A, B, C. The resistance is connected between the two terminals A and B is called the RAB. The resistance connected between B and C is called the RBC. The resistance which is connected between C and A is called the RCA. So here always the current leads from positive terminal of the supply here, and the current, let us say this is I1 and I2 here, and here also I am applying, yes, this is I, let us say this is IX and IY, and here also you can take that IZ and IB here. So each branch which is having no current is same, and no current is divided, and the same current is not returned back. So each resistor which is having a two currents, one is downward current, one is upward current. So neither two resistors are connected in series nor in parallel. That's why we are going for the network reduction technique by using a delta to star conversion, and star to delta conversion. So if you go for the star, also you can check it now once. So here also you can apply the voltage source here. Yes, here also you can apply voltage source between these two, and you can apply, yes, A, B and C. Individual resistances are RA, this is RB and RC. So apply. Yes, always the current leaves from positive terminal. Yes, here the current is flowing now, and here this is a current direction, here it is a current direction is like this, okay. Now so all the currents are towards the node only. Yes, this current will be flows in this direction, okay. If it is a balanced, okay, neutral current is 0, that is under AC circuits, but each one carries two currents, neither two resistors are connected in series nor in parallel. So that's why we can go for the delta to star and star to delta connection, delta to star as well as the star to delta connections. So in order to solve the network reduction techniques, we can go for the one of the technique, that is called the delta to star conversion as well as the star to delta connection. So what is my question is, if you convert delta to star, what happened to the values, decreases or increases? And if you convert star to delta, the values are increases or decreases, increases or decreases. How can you remember that? Okay, so it's by doing the practically more calculations you can tell the answer directly here. But delta is like this. Okay, star is made up of yes, this is one is called the star. Star resistors are RA, RB, and this is RC, and this is one is RAB, and this one is called the RBC, and this is called the RCA. Insert the star here, insert the star. Let us say this is RA, RB, RC, and RA is equal to, if you are getting the parallel combination for this blue line, these orange lines are touching, that means RAB into RCA by RAB plus RBC plus RCA. So obviously values are decreases. So delta to star, the values will be decreases. Okay. So if two resistors, equal value of resistors are connected in parallel, then equivalent resistance will be half. And if you go for the star to delta, this is called the delta to star here. And the star to delta means SRA is equal to RAB is equal to SRA plus RB plus RA RB by RC. Why? Because RAB I am getting RA and RB both are touching. Yes, RA plus RB plus RA RB by RCS. The values will be increases. The values will be increases. Okay, if you go for the delta to star conversion and star to delta conversion. Okay. So I think you understood that. So from the previous slides also, current division rule, where we are applying the current division rule, and the source transformation, open circuit properties, short circuit properties, mesh analysis, nodal analysis, and these are the important questions on some of the important questions on DC. Okay, so DC analysis is given, transient state is also, DC is given to the RL series circuit. So what are the variations? What is a graph under charging condition and discharging conditions? What is meant by time constant? What is meant by time constant for RL series circuit? So if you are taking a voltage source here and DC which is given to RL, what will happen? So always source delivers the energy, the resistor always dissipates the energy in the form of heat, resistor always dissipates the energy in the form of heat, and the inductor stores the energy in the form of magnetic field. So time constant for this circuit is called L by R. L by R. So inductor stores the energy in the form of magnetic field. So what is the current equation during charging condition? So that is our next question. What is the current equation during a charging condition? So current equation during charging condition. Yes, if you are taking a switch here and the switch is closed at t is equal to 0, at t is equal to 0, once again the next question coming to picture, what is meant by 0? 0 plus or 0 minus? What is meant by transient state? What is meant by steady state? The electrical characteristics, either voltage, current, power or energy or changes with respect to time, is called the transient state. So yes, this is called the transient state, means the electrical parameters. What are the electrical parameters? Voltage, current, power or energy or changes with respect to time is called the transient state. So these are constant. Electrical parameters are constant with respect to time, that is called the steady state. We are having a total response is a summation of transient state plus steady state. So total response is equal to transient state or transient response plus steady state response. So here see this switch position which is closed at 0 seconds and close the switch. Immediately, what is the property of the inductor? Inductor does not allow the sudden changes of the current. So whatever the capacitor is also same thing. Or your phone, if you are taking your phone, if you plug the charger, it will not directly goes to 100%, it will slowly charges from 0 to 100%, 1%, 2% like that. So similarly inductor, we will take it as a current which is stored. Yes, magnetic field current which is flowing through the inductor produces a magnetic field that is stored in the form of in an inductor half Li square, as a half Li square is the equation. Now you can apply the KVL to this loop. If you apply the KVL to this loop, V is equal to IR plus L di by dt. And if you take di by dt, L is divided, and R by L into I, that should be equal to V by L. That should be equal to V by L. This is in the form of yes, dy by dx plus P into Y is equal to Q. Then we are having a particular integral and complementary function in a mathematical equation. Similarly, same way here, complementary function is called the transient response. Complementary function is called transient response, and particular integral is called the steady state response. Okay, so now in order to get the complementary function, this right side part made equal to 0. This is one of the technique. Otherwise you can write directly the equation, so where I is equal to integrating factor is equal to something. So by using a mathematical equation also you will get the answer. In order to get the transient state response, di by dt plus R by L into I is equal to 0, and I can write it as di by dt minus R by L into I, di by I is equal to minus R by L into dt. Integrate on both sides. If you integrate on both sides, then ln I is equal to minus R by L into T plus ln A, where ln A is called the constant. So ln I minus ln A is equal to minus R by L into T. This is ln of I by A is equal to minus R by L into T, where I by A is equal to e power minus R by L into T, where I is equal to A into e power minus R by L into T. This response is called the transient response. Transient response, you can check that exponential decay e power minus x is called the exponential decay. It is changes. While you are switch on the fan also, the fan will start from 0 speed and it will reaches to some constant speed. So initial state we can call it as a transient state. At the final speed we are call it as a steady state. So in order to get the steady state response, what is the inductor behavior? That is very, very important. What is the inductor behavior after fully charged? Yes, initially the charge on the inductor is 0, and finally what will happen? It will fully charged, that is 100% charged. If it is 100% charged, it acts as a current source, right? So ideally say it acts as a short circuit. Now your circuit becomes VR and inductor acts as a short circuit because V is equal to L di by dt. If your initially maybe transient state, at final steady state, what is the current value? The current value is constant. If the current value is constant, dA by dt value is 0. If a dA by dt value is 0, voltage across the inductor is 0. If a voltage across the inductor is 0, then it acts as a short circuit. This response is called the steady state response. This is one of the shortcut method to get the steady state condition. Steady state current is equal to V by R. Now what is the total response now? What is the total response? Total response is equal to transient response plus steady state response. So now the total response is equal to transient response plus steady state response, and I is equal to A e power minus R by L into T plus steady state current is V by R. Now, in order to get the condition, in order to get the constant value, you can apply the initial condition at T is equal to 0. At T is equal to 0, what is the current value? The inductor current or current which is flowing through the circuit is 0. Why? Because inductor previously it is uncharged. Uncharged means initially charge will be 0. If it is a charge is 0, current is 0. If a current is 0, inductor does not allow the sudden change of the current, means current 0 means it acts as a open circuit. So open circuit, right? Yes. I is equal to 0. 0 is equal to A e power 0 plus V by R, where A is equal to minus V by R. Substitute here. Then I is equal to V by R into e power minus RT by L plus V by R. This is minus V by R. Take a V by R is constant. 1 minus e power minus RT by L. So this is called the current equation during a charging condition. As the name itself, it is charging. Charging means if you take a mobile phone also, it's 0 to 100% as transient state to steady state. See the switch position, that is very very important. In this tau we can substitute as L by R, where I is equal to V by R into 1 minus e power minus t by tau. So this is very very important. And if you draw the curve between current versus time here, current versus time, what is the final value here? It is a V by R, and then it will slowly increases. This is about the charging condition. At T is equal to tau. This is a very very important question of interview question. At T, at which time constant, the current value reaches to steady state? Why I am deriving this equation? This is very very important analysis. Complementary function which represents the transient state, particular integral which represents the steady state, and the T is equal to tau 0.368 in V by R. I think 1 minus 0.368, that is 0.69 V by R. Okay, so at T is equal to 5 tau, I is equal to 0.99 V by R. At T is equal to 5 tau, it will settles to final stage. So what are the interview questions on this concept? What is the time constant for RL series circuit? And if it is excited with DC supply, what is the charging current equation? What is the charging current equation? If a current will be charged, right, what happened to the voltage level? The voltage level values will be decreases. So check that V is equal to VL is equal to L di by dt. VL is equal to L di by dt. L d by dt of V by R into 1 minus e power minus t by tau. VL by R d by dt of 1 is 0, minus into minus, minus t by tau into 1 by tau. 1 by tau, tau is equal to L by R, LL will be cancelled, then V into e power minus t by tau. Substitute this value at t is equal to 0, it is V only, and at t increases, it will be slowly discharges. It will be discharges as the sources are there. Inductor is taking the power, inductor is slowly charges. So provided the initial charge is equal to 0. Suppose during discharging, what is the behavior of the inductor? What is the current equation? What is the current equation? Discharge. Suppose if you want your mobile to be discharged, means if it is 100% fully charged, means from 100% to 0%. Is during that condition you can't plug the charger, yes or no? Charger is away from that your mobile phone. Okay, now what is the discharging equation? What is meant by discharging equation? So what is the discharging equation? So if you take a R here, and now the inductor is fully charged. Inductor is fully charged. But once it will be charged, it will change its polarities during the discharging path. This is about the current. Whatever the energy is there, that is dissipated in the form of heat through the resistor. Okay, without resistor, there is no discharging. Yes, but if you take a coil consisting of some resistance, right? So now your equation is IR plus L di by dt is equal to 0 here. 0. What is the initial charge, sir? Initial charge is I naught. So di by dt plus R by L into I is equal to 0. So finally I is equal to A into e power minus RT by L. In order to find out the constant value, apply initial conditions. This is very, very important. Apply initial conditions, where if t is equal to 0, where I is equal to I naught, substitute here, then I is equal to I naught e power minus RT by L. So I is equal to I naught, that should be equal to A value is substituted here, then it will be I naught e power minus RT by L. I naught e power minus RT by L, where I is equal to I naught e power minus RT by L. Yes, where tau is equal to L by R, then I is equal to I naught e power minus T by tau, at T is equal to tau. Yes, so that is 0.368. At T is equal to infinity, at T is equal to 0, I is equal to I naught, at T equal to 0, I value is 0 here. It is a exponential decay performance. There we have to consider the 0.69. Here we are considering the 0.638 at one time constant. So now coming to the RC series circuit. Here. What is the charging equation for RC series circuit? What is the discharging equation for RC series circuit? Inductor means you should concentrate on current. Capacitor means you should concentrate on voltage. Time domain analysis of RC series circuit here. It is a time domain analysis of RC series circuit. Okay, so this is about the V here, and if you close the switch, then obviously current is passes. V equal to IR plus 1 by C integration IDT, provided pre-charge is 0. That is very, very important. Pre-charge is equal to 0. Here. and differentiate this equation because we are giving a DC supply dV by dt value is equal to 0, and this is di by dt into R, di by dt into R plus I by C, di by dt R di by dt equal to minus I by C, and the di by I is equal to minus 1 by RC into dt. Integrate on both sides, this is ln I is equal to minus T by RC plus ln A. Same equation you are getting, I is equal to A e power minus T by RC. What is I? So what is I here? A e power minus T by RC. This is the current equation. This is the current equation at T is equal to 0. What is the current? Sir, you should know the capacitor behavior. What is the capacitor property? Capacitor does not allow the sudden changes of the voltage. What is the charge? So you will take a battery. So battery is uncharged, means from 0%, yes, 0 volts. So VC is 0 volts. At the capacitor voltage is 0 at initially 0 means it acts as a short circuit or open circuit. Yes, definitely it is a short circuit. So short circuit means I is equal to V by R, substitute here, and T is equal to A is equal to V by R only, V by R into e power minus T by RC. But what is the meaning, sir? What you want to say, sir? Yes, I want to concentrate on voltage rather than current. So now what is the voltage across the capacitor? You can see here what is the voltage across the capacitor. Vc equal to 1 by C integration of I dt, 1 by C V by R e power minus T by RC integration into dt. So V by RC e power minus T by RC by minus 1 by RC plus one constant C here. RC will be cancelled, minus V e power minus T by RC plus C. So again you can apply the initial condition. Sir. Initial conditions you can apply. Initial conditions at T is equal to 0. Vc value is 0 because the capacitor is uncharged. Yes, substitute here 0 equal to minus V plus C, C is equal to V. Substitute here Vc equal to V into e power minus T by RC. Yes sir, we are accepting. Charging means 1 minus e power minus T. Discharging means e power minus T. Yes. What is the time constant for this circuit, sir? RC. Equation won't be changed. Vc equal to V into 1 minus e power minus T by tau. Again the same story. At T is equal to tau. Vc equal to 0.698 V here. So your equation will be, so during charging like this, V versus T, Vc is equal to V. During discharging conditions means if a battery is fully charged or capacitor should be fully charged. Why I am taking the battery, sir? Battery is like a capacitor, no? For understanding purpose, as I am telling the examples of the phone battery, because you are using your phone in daily life, yes or no? So that's why I am telling the best examples. Okay, from a mobile phone is also charging from 0 to 100%. If you take the capacitor is just like an example, right? So capacitor charge is 0, yes, 0 volts. Capacitor is 100% means 100% voltage means full voltage. Suppose if the capacity of the capacitor is 5 volts, phone battery capacity is 4.8 or 4.9 volts, it will charge to 5 volts, right? So you are using 5 volts charger, 80 watts is a super fast charger, right? Okay, so during a discharging condition, what happened during a discharging condition? So what is my discharging condition? Means the capacitor is fully charged, means Vc value should be equal to V. This you have to remember. So now there is no sources here, there is no source, and C is parallel to, yes, C is parallel to R here. Now you can assume, for understanding purpose, for a easy analysis, the charging current, you can assume the virtual node here. This is I, virtual node here, I plus IC is equal to 0 here. By applying the case, you can assume the voltage, virtual node here, virtual node. So this is called the V here. From this V only we are generating current. So I is equal to S V by R plus IC is C dV by dt is equal to 0. And V by R minus C dV by dt equal to 0, and the dV by V is equal to minus 1 by RC into dt, minus 1 by RC into dt. So now ln V is equal to minus T by RC minus T by RC plus ln A. Ln A is a constant. As V by A is e power minus T by RC. V equal to A e power minus T by RC. But in order to calculate the constant values, apply initial conditions. Apply initial conditions. So what is the initial condition, sir? At T is equal to 0, sir. A value is V here, that means Vc value is V. Substitute here V equal to A, and substitute Vc is equal to yes, Vc by R, Vc, and V is equal to V into e power minus T by RC, and it will be exponential decay 100% to time. Charging equations are I is equal to, in an inductor RL series circuit, I is equal to V by R into 1 minus e power minus RT by L. Discharging equation is I naught e power minus RT by L. If you go for the capacitor charging equation, what is my charging equation? Yes, Vc equal to V into 1 minus e power minus T by RC. Discharging equation, Vc equal to V into e power minus T by RC. At T is equal to tau, yes, at T equal to 2 tau, at T equal to 3 tau, at T equal to 4 tau, at T equal to 5 tau. At 5 tau you are getting the constant value or steady state value. So what are the applications of DC? That is a very, very important question. What are the applications of DC? What are the applications? What are the applications of DC? So it is used in PMMC instruments. PMMC instruments, yes, to measure average value, to measure the average value. PMMC instrument is used to measure the average value. Okay, so we are using a DC applications, means we are having a DC motors and DC generators. These are outdated now, nowhere it is used, but at the time of starting DC generators are used here. And the brushless DC motor, brushless DC motor, Okay, so PMMC used as a voltmeter as well as the ammeter here, and DC series motor. DC motors means we are having a DC shunt motor, DC series motor, DC compound motor. DC series motor can also be work for AC with pulsating torque. That's why we are using a universal motor. Okay, which is used in cranes, hoists, elevators, so and so applications are there for the DC motors. So these are the applications of a DC supply. Yes, coming to the next question. So what is mean by AC? What is the meaning of AC? So AC means alternating current. AC means alternating current. So what is the single phase AC voltage? What is the standard value of the AC voltage? Is 230 volts. Single phase AC or Indian frequency is 50 Hertz. Okay, so what is the meaning of frequency? Is the number of cycles per second. That is coming the next interview question. And what are the advantages of AC? Advantages of AC over DC supply. Over DC supply. So the first advantage is, with the help of a transformer, you can raise the voltage or down the voltage. So step up the voltage, and step down the voltage, is possible with the help of AC. Is possible. Voltage is possible with the help of AC. So with the help of transformer. ST by F is called a transformer. So as you all know, what is a transformer? Transformer is a static device which transfers electrical energy from one side to another side with changing of voltage and current levels without changing frequency. Okay, and what is the advantages of step up or step down the voltages? Our generation level will be 11 kV. That 11 kV stepped up to 220 kV. What is the advantage if you step up the voltage? So if I want to transfer power, that is a fixed amount of power, so that is called the, let us say this is yes 10,000 watts, which we were already discussed in machines marathon. So once again I am reminding here, and voltage levels will be 100 volts and the current is 100 amperes. In order to get same 10,000 watts, if voltage is increased to 1000 volts and the current value will be reduces here. If voltage is 10,000 volts and the current is only 1 ampere. Now as you are increasing the voltages, what will happen? The current value will be decreases. If a current value will be decreases, you know that branch which is consisting of R and X, right? S and I square R losses are reduced here. Transmission losses are reduced with the step up the voltages. And with the lower current, the conductor size is also decreases. If the conductor size is decreases, what happened to the cost of the transmission lines is also decreases. So these are all interlinked to each other. So there is advantages of AC. Who invented the AC? Nikola Tesla was invented the AC. There was a war was happened between the Thomas Alva Edison and Nikola Tesla. So DC is as per yes, Thomas Alva Edison point of view, DC generators are best. As per Nikola Tesla, AC generators are best because of the step up the voltages, step down the voltages is possible with the help of a special device is called the transformer, and also 90% of the in our So in the world 90% of the loads are only AC. The nature of the loads is AC. When you want to convert DC, we require a rectifier which converts AC to DC. And if you want to charge the battery, means in that charger mobile charger, we are having a rectifier. Okay, so these are the advantages of the AC. And where we are using the AC means, so how to measure the AC? How to measure the AC voltage and AC current? So AC quantities are measured in RMS values. So RMS values, root mean square. AC quantities are measured in RMS values. And also we are having a voltmeter MI instruments, moving iron instruments, which will measure the AC quantities. So these are the advantages of AC over a DC. And so different types of signals we are having, we are having now. So different types of signals are there. AC signals, different types of AC signals. Okay, so coming to the next introduction, why we preferred sinusoidal waveform over all other waveforms? Why we prefer the sinusoidal waveform? So now if you go for the sinusoidal waveform, so this is about the sinusoidal quantity. Let us say this is current versus omega t here, and this is also alternating waveform here, current versus omega t, and this is also alternating waveform. Alternating means it should consisting of a positive off cycle and negative off cycle. So it should consisting of a positive off cycle, negative off cycle, positive off cycle and negative off cycle. Yes. Out of all these waveforms, why we prefer only sinusoidal waveforms? Why we prefer only sinusoidal waveforms? What are the advantages of sinusoidal waveforms? That is a very, very important interview question. So integration of the first advantage. So advantages of the sinusoidal signals. Yes, advantages of the sinusoidal signal here. First one, advantages of sine wave. Integration of sine theta is minus cos theta. Integration of cos theta is sine theta, and differentiation of sine theta is cos theta, and differentiation of cos theta is minus sine theta. Sir, what you are telling, sir? Why differentiations are comes into picture? Why integrations are comes into picture? Why? Because of energy storage elements are there in our circuit, that is called the inductor and capacitor. Voltage across the inductor is LdA by dt. Current through the capacitor is CdV by dt. Voltage across the capacitor is 1 by C integration of I dt. Yes, current through the inductor is yes, 1 by L integration of V dt. So we are having a integrations and differentiations. If you are integrating the step signal, then you are getting the ramp. Integration of 1 dt is t here. Integration of t is t square by 2. Integration of t square is t cube by 3. Otherwise, you can go for the differentiation of a step is called the impulse signal. Differentiation of ramp is a step signal. Yes, you have a different types of signals, but So because of energy storage elements, tell me students, at what type of waveform the loads are properly working. So that's why we have to develop a universal waveform, that is called the sinusoidal waveform. All the loads are properly working for pure sinusoidal waveforms only. And also one more thing, any non-sinusoidal waveform can be converted into sinusoidal waveform by using a Fourier series analysis. So any non-sinusoidal waveform can be converted into sinusoidal waveforms with multiple frequencies using Fourier series analysis. Using Fourier series analysis. So what is Fourier series of f of t? Sigma n is equal to 0 to infinity, or minus infinity to plus infinity, or a naught plus sigma n is equal to 1 to infinity a n cos n omega t plus b n sin n omega t. Suppose if you are having a square waveform, if you are interested on square waveform is generated, this square waveform is inbuilt of so many sinusoidals. Yes, this is a fundamental waveform. You can have a third harmonic components are like this. Yes, fifth harmonics. So third harmonic is having 3 omega, fifth harmonic is having 5 omega. What is omega, sir? Angular frequency. If you add all these harmonics, you may get a square waveform. So what Fourier said, Fourier is beautifully explained. Any non-sinusoidal waveform can be converted into sinusoidal waveforms with multiple frequencies. We can call it as a harmonics. A waveform which should contains multiple frequencies is called the harmonics. It is unwanted signals. If you remove this 3 omega and 5 omega, then you will have a only fundamental waveform. So either it is a triangular waveform, either it is a sawtooth waveform, either it is any type of waveforms. It is a inbuilt of so many sinusoidals. For odd signal, we are having S, An is present. For an even signal, Bn is present, An value is equal to 0. So like that you studied in signals and systems. Okay, so if you fold yes, I will ask you one question here. Cos of minus theta, yes, cos of minus theta is cos theta here, and sin of minus theta is minus sin theta. Yes, as all know that cos theta is a even function and sin theta is odd function. How can you prove that this is yes, which is related to mathematics, which is related to signals and systems, which is related to electrical circuits? And why it is called as a even signal, why it is called as a odd signal? If in an interview he may ask like that. So what is a cos theta waveform? This is about the cos theta waveform. And this one is called the cos theta. If you go for the sin theta waveform is like this. If you fold y-axis, then exactly it will coincidence the original waveform. That's why cos of minus theta is cos theta. If you fold y-axis like this, then it is a mirror image of the original waveform. That's why sine of minus theta is minus sine theta is odd signal, cos of minus theta is cos theta, which is an even signal, So this is about the why we prefer the sinusoidal waveforms. Integration of sine is a cosine, integration of cosine is sine. The nature of the waveform is sinusoidal nature. The nature of the waveform is sinusoidal nature. Yes, the nature of the waveform is sinusoidal nature. Then we can call it as we can preferred as sinusoidal waveform. All the loads are working properly for a pure sinusoidal waveforms. If you go for how can you eliminate these harmonics, means by using yes, distributed winding and pitch factor, you can eliminate the some harmonics in an synchronous machines you may studied in an electrical machines. This circuits is a fundamental to all the subjects. Without knowing the electrical circuits, you should not know the other subjects. Okay, now first of all, what is a instantaneous value? Define instantaneous value. So define instantaneous value. This is the next interview question. And so if you take an alternating quantity, this is your alternating waveform. Let us say I versus omega t here. I versus omega t, this is 0 degrees, and let us say this is T1, T2 and T3 and the T4 and T5 and the T6 and T7 here. Okay, so now you can define the alternating quantity at any instant of time is called the instantaneous value. The value of an alternating quantity, the value of an alternating quantity, the value of an alternating quantity at any instant of time, at any instant of time is called instantaneous value. Yes, instantaneous value. Now what is meant by cycle? What is meant by cycle? Next question is define cycle. A set of positive instantaneous values, positive and negative instantaneous values of an alternating quantity is called a cycle. Quantity is called a cycle here. And next one is called the what is meant by amplitude. What is meant by amplitude here? The maximum value which is attained by the positive peak and the negative peak of the alternating quantity is called the amplitude. Here it is I maximum and here it is minus I maximum. So the maximum value attained by the maximum value attained by the alternating quantity, the maximum value attained by the alternating quantity is called peak value. What peak value? What are the names of the peak? Peak or maximum value. Yes, maximum value and also called as a crest value, or also called the crest value. Crest value, peak value, maximum value, all are same only. The other name for that one. And the next one is called the what is mean by. Yes, what is mean by what is meaning by time period. Yes, time period which is represented with T. Yes, time required to complete one cycle is called the time period. So this is yes, this type of waveforms are repeating here. This is one cycle. Yes, time period 0 pi, and this one is 2 pi here. I versus theta or omega t. Theta is replaced with omega t. Okay, so it's at 0 you can observe that the waveform will be increasing, and after pi you can see that at pi position it is decreasing, it is not repeating, but at 2 pi the waveform is repeating the previous waveform or previous cycle. Here you can see here you can see at 0 the waveform is increasing, at 2 pi the waveform is following the previous waveform. Then we can call it as a time period. Time required to complete one cycle is called the time period. As time required to complete one cycle, time required to complete one cycle is called time period. Okay, yes sir, what is the time period value? Time period value for our Indian frequency. What is the time period value for one cycle? Yes, our frequency is 50 Hz, and that what is the frequency? Yes, once again coming the next interrogation, what is mean by frequency? Frequency which is measured in hertz, number of cycles per second. How many cycles are passed in a second is called the frequency, and the frequency and time period both are having a inverse relationship, and the time period is equal to 1 by 50, that should be equal to 20 milliseconds. The time period of the sinusoidal waveform, time period value of the one cycle, time period of the one cycle. One cycle means only time period. Time period of the sinusoidal waveform is 20 milliseconds. Half of the time is 10 milliseconds, and the remaining half is 10 milliseconds. But see here, within 10 milliseconds the brightness of the bulb should be increases. Brightness of the bulb will be coming the next 10 milliseconds should be decreased, but our eye can't detect the whatever the changes which is occurred during 10 milliseconds. That's why brightness of the bulb which is looks like a uniform, it is at 20 milliseconds. Okay, so I will draw the waveforms. He may ask that so what is the frequency of the particular one, what is the time period of the waveform, is it symmetrical waveform or asymmetrical waveforms? First of all, check the waveforms. How many types of waveforms are there? First one is called the symmetrical waveform. Symmetrical waveform. What is my symmetrical waveform here? Let us say this is 5 volts and this is minus 5 volts versus omega t. This is about the first waveform, and the second waveform you have this type of waveforms here. Let us say this is 10 volts and magnitude amplitude will be minus 10 versus omega t. And okay, symmetrical and asymmetrical waveform. we can identify the waveforms as a symmetrical waveform, or is it a symmetrical waveform or asymmetrical waveform. And the third one, you can go through this and I am having a sinusoidal shape here, and this is about the 5 volts and this is minus 2 volts versus omega t. Okay, so V versus omega t, here also V versus omega t, V versus omega t. And the fourth one is and it is having a positive half cycle and negative half cycle. This is plus 5 volts and minus 5 volts. And the fifth one, you have this type of waveforms here, 0 1 2 3 here. So this is time period in milliseconds. Let us say this one V. Yeah, out of these five waveforms, which one is a symmetrical waveform, which one is a asymmetrical waveform, So what is the definition of a symmetrical waveform? The shape of the positive half cycle is equal to shape of the negative half cycle. It should satisfy the two conditions. First condition is shape of the positive half cycle is equal to shape of the negative half cycle. And the second condition is amplitude of the positive half cycle is equal to amplitude of the negative half cycle. Then only we can say that it is a symmetrical waveform. Otherwise it is called as a asymmetrical waveform. Yes sir, 5 volts here, minus 5 volts. Yes, second condition is satisfied here. What is the first condition, sir? Shape of the positive half cycle is equal to shape of the positive half cycle is equal to negative half cycle. Yes, two conditions are satisfied. This one is called the symmetrical waveform. And here also, yes, 10 volts, minus 10 volts. Shape of the positive, shape of the negative is same. It is also symmetrical waveform. And here shape first condition is satisfied, but the second condition is not satisfied. Why? Because amplitude is 5 volts here, and here amplitude is yes, negative half cycle maximum value is minus 2 volts, which is not satisfied. Then we can call it as a asymmetrical waveform. And here you can observe that the first condition is not satisfied, but the second condition is satisfied. Why? Because maximum value during the positive half cycle is plus 5 volts, during the negative half cycle is minus 5 volts. But if it is not satisfied, one of the above conditions, we can call it as a asymmetrical waveform. Okay, asymmetrical waveform. But coming to the last one, there is no negative half cycle here. It is not a symmetrical waveform, it is not a asymmetrical waveform. But you can clearly see that if you shift the x-axis to above level, then it consisting of a positive and negative, then this waveform is called the hidden symmetric waveform. We can call it as a sawtooth waveform also. Sawtooth waveform. So these are all about the definitions, basic definitions. What is meant by cycle? A set of positive instantaneous values and negative instantaneous values of an alternating quantity is called the cycle. What is meant by instantaneous value? The value of an alternating quantity at any instant of time is called the instantaneous value. What is meant by maximum value or peak value or crest value? Means the maximum value which is attained by the alternating quantity is called the maximum value, peak value or crest value. And what is the meaning of time period? Means time required to complete one cycle is called the time period. What is the meaning of frequency? Is the number of cycles per second is called the frequency. Now what is the angular frequency here? Angular frequency, what is meant by angular frequency? So this is very important, angular frequency. So which is represented with omega, units are radians per second. So now in an angular frequency, once again you can yes, this is called the omega t, and this is about the current or voltage. What is this value here? Omega capital tau. What is the value here? 2 pi. So omega t is equal to 2 pi. What is omega now, sir? 2 pi by t. What is 1 by t, sir? 2 pi f. This is about the angular frequency, radians per second. So this is very important. Angular frequency is in radians per second. So radians per second. And the next one is generation of AC. Generation of AC. I will explain how the AC will be generated. So we are discussing the interview questions on a sequence here. Okay, and first of all, advantages of AC over a DC. DC step up or step down are not possible. Large losses will be produced, transmission losses will be more, and the AC current will be reduced, voltage levels will be increases, transmission losses will be reduces, size of the conductor reduces, cost is also reduces, overall efficiency of the transmission line will be more. And the generation of AC, how the generator will be generated the voltage means, I will explain with the constant magnetic field, with a constant magnetic field. So the flux which is produced by this, the flux which is produced by, or the current which is flowing through the field is a steady flux. Current flux produced by the field is a uniform field here, as I am taking the pointer, and this is a conductor which is rotating in a clockwise direction. This is a tangential force acting on the conductor, tangential force acting on the conductor here, tangential force acting on the conductor. So this is first position, second position, third position, and fourth position. So now at first position, what will happen? The magnetic flux lines and the tangential force both are having a parallel direction. There is no cutting action, and EMF is induced here, E is 0. At second position, maximum number of flux lines are cut by the conductor, EMF is maximum here. At third position, which is anti-parallel, the force is anti-parallel, then the EMF which is induced here, it will be 0. At fourth position it will be 0, and that in order to complete one revolution, then it will comes to one position. It will be rotating. So with the help of a prime mover or manually you can rotate the conductor, it will cut the flux and EMF is induced here, and the generation is AC only. And this is about the E versus theta, where E is equal to BLV sin theta. This is about the Faraday's law. E is equal to BLV sin theta, where B is called the flux density, L is called the active length of the conductor. The conductor which is existing under the magnetic field is called the active length of the conductor, where V is called the velocity of the conductor, when theta is called the this is a conductor position, this is a magnetic field position, and this is about the conductor position. The angle of these two is called the theta, where E is equal to E max, theta is replaced with omega t, then E is replaced with Vs, Em is replaced with Em as Vm sin omega t. See here how beautifully it is designed. We are using in a single phase, a transformer or whatever it may be, induction motor. We are using universal equation where Vs is equal to Vm sin omega t. Theta is in degrees, and that is converted into time domain, time analysis. Then theta is replaced with omega t, where Vs is equal to V max sin omega t. This is the generation of the voltages. So what is V maximum, sir? Maximum value of the voltage, sir. What is omega, sir? Angular frequency, sir. Yes, what is Vs is called the supply voltage. This is how the generation of the AC is generated. AC voltage will be generated according to Faraday's law, sir, whenever conductor cuts the flux, an EMF is induced in a conductor. So where E is equal to VLV sin theta, sir. From that E is equal to E max sin theta or E max sin omega t. E is replaced with Vs. E max is replaced with V max. Vs is equal to V max sin omega t. So Vs is equal to V max sin omega t. So this is about the generation of AC, generation of the AC. And next one is called the define RMS value. Define RMS value. So most of the thing that they know that what is RMS is called the root mean square. It is an abbreviation, it is not a definition. It is a abbreviation, it is not a derivation. I am taking a water heater here. So instead of resistor, I am taking a water heater. First of all, I am applying a DC voltage. I am DC voltage, and the DC voltage is replaced with the AC voltage to the same water heater, and the resistance value is same, and the instantaneous value of the voltages, instantaneous values of the currents are represented with small letters. Instantaneous value of the voltages, instantaneous values of the currents are represented with the small letters. Sinusoidal symbol, yes, we are AC is represented with the circle with the sinusoidal. Okay, the voltage at which, so what is the meaning of RMS value means, so the voltage at which heat transferred in DC circuit, heat transferred in DC is equal to heat transferred in an AC. Heat transferred in AC provided the resistance is same and the operating time period is also same. Operating time period is same. This is our very important. Operating time period is same. Yes. Heat transferred in DC circuit is equal to heat transferred in an AC circuit provided the resistance is same and operating time period is same. What is the heat transferred in DC is equal to current I is flowing, right? I square RT, it will be operated at 5 minutes, then it will be generated the I square RT joules. I square RT joules. But in an AC you can observe that, yes, as this is about the I versus omega t. What happened to the negative half cycle? What happened to the negative half cycle? Root mean square of the negative half cycle is converted into positive half cycle. Square of the negative half cycle is equal to positive half cycle. That's why, what is the time period of that waveform? 0 to pi only. The time period of this waveform is called the 0 to pi, and this can be divided as at t1 instantaneous value is I1, at t2 the instantaneous value is I2, at tn the instantaneous value is 1, at instantaneous value is In. Yes, at t1 heat is I square R t1. So you can divide this x-axis. Into n equal number of tons. So t, small t, you can take small t is divided into n equal number of tons. Each term is t by n only. T by n, t1 is equal to t by n. Yes, I square R t by n. At t2 is also t by n. I2 square. Yes, I2 square R t by n. And at Tn In square R t by n. So by adding all these heat produced in an AC, I1 square R t by n plus I2 square R t by n plus 1 In square R into t by n. In square R into t by n. So take a t is common here. Yes, I square RT. RT is common. I1 square plus I2 square, so on IN square. And this is about the heat produced in AC. But what is the definition? The voltage at which the heat produced in an AC is equal, DC is equal to heat produced in an AC, then provided the same operating time and resistance is also same. So heat produced in DC is equal to heat produced in AC. Heat produced in DC is equal to heat produced in AC. I square R T is equal to RT, then I1 square plus I2 square plus on IN square by N. RT cancel, then IRMS is equal to root over I1 square plus I2 square plus on IN square by N. This method is called the graphical method. What is this method? Is called the graphical method. So finally the conclusion point is met or not. Let us see here. Root S, squares is also there here. Squares is also there. Root mean square, mean square. Otherwise coming in reverse order, squares, yes, squares of I1 square, I2 square, so on IN square. Mean means plus 1 by N, then you can apply the root, then we can call it as a root mean square. So what is IRMS value? What is the IRMS value for an AC? What is the value of the IRMS for a sinusoidal waveform? What is the value of VRMS for a sinusoidal waveform? So then we can go for the analytical method. Analytical method. Yes, see here, this is 0 to pi here, and see negative half cycle is also converted into positive half cycle. This is I square versus omega t 2 pi. So what is the time period now? Pi only. At the 0 the waveform is increasing, at pi the waveform is increasing, then we can call it as pi is called the time period. Okay, right. So I am drawing clearly here. I am drawing clearly. Yes, we are considering, why we are considering only positive half cycle, means that is the meaning. I versus theta. What is RMS value? Here root mean square. So 1 by pi is the area. Integration 0 to pi. I is equal to Im sin omega t, yes, Im sin omega into d theta sin square theta or omega t. So yes, omega t as I am taking. This is called the IRMS square. IRMS square. Then I can call it as a Im square by pi. Sin square theta can be written as 1 minus cos 2 theta by 2. 1 minus cos 2 theta by 2. Integration 0 to pi d omega t. And IRMS square is equal to Im square by 2 pi. Im square by 2 pi. Integration of 1 is s omega t. Integration of cos is sin 2 omega t by 2. So limits you can apply 0 to pi. Limits you can apply 0 to pi. Yes, Im square by 2 pi, and the upper limit substitute okay, pi, and the lower limit is 0, and sin 2 pi value is 0, sin 0 is 0, pi will be cancelled here, then IRMS is equal to Im by root 2. While we are considering the full cycle, IRMS value is Im by root 2. Im by root 2. Similarly, VRMS is equal to Vm by root 2. As I said, AC quantities are measured in RMS values. AC quantities are measured in RMS values. Instantaneous values are represented with small letters. maximum values are represented with capital letters, RMS values are represented with capital letters, average values are represented with capital letters. Okay, now if I am taking the another type of waveform, what is by seeing the waveform you can tell the answer. So what is my interview question is, what is the RMS value of the pure sinusoidal waveform? What is the RMS value of the, yes, RMS value of the half wave rectifier, you can say that. So this type of waveform, so 0 here, this one is pi, and this is called the 2 pi, 3 pi, and this is about the I maximum, I versus omega t. What is the RMS value? What is the RMS value? With, so you no need to derive the all the values, but you have to remember carefully, because this is a very important. What is the time period, sir? What is the time period? Time period is not pi, the time period is 2 pi. Most of them they commit a mistake here only. Time period is 2 pi. Why? At 0 the waveform is increasing, after pi no, 2 pi only the waveform is repeating the previous cycle waveform, then time period is 2 pi, and but the waveform is existing only 0 to pi, then IRMS square is equal to 1 by pi integration 0 to pi I square d omega t. But what is the shape of the waveform? The shape of the waveform is sinusoidal, the 0 to pi Im square sin square omega t d omega t, and plus pi to 2 pi. And what is the magnitude of the current? The magnitude of the current is 0 here. You can split like this. Then IRMS square is equal to Im square by 2 pi, and this is 1 minus cos 2 omega t by 2 integration 0 to pi d omega t. So Im square by 4 pi and omega t minus sin 2 omega t by 2 and integration 0 to pi. Substitute here Im square by 4 pi into pi, and these two are cancelled, then IRMS is equal to Im by 2. So practically say, what this type of waveform, so in an EDC, I think in electronic devices and circuits marathon, you can know that. So this is output of the half wave rectifier. What is this one? Is called the output of the half wave rectifier. So output of the half wave rectifier is Im by 2. Okay, so and similarly, so what is the RMS value for sawtooth waveform, a triangular waveform? So for triangular waveform, what is the RMS value? How can you know this? Yes, RMS value for the sawtooth waveform. So this is about the third waveform. So he is directly asking only what is the RMS value for pure sinusoidal, what is the RMS value for a half wave rectifier output waveform, what is the RMS value of the sawtooth waveform, like that he will ask. So this is 0 here, and this one is called the pi, and this is 2 pi, and let us say this is called the I maximum, I versus theta or omega t. Okay, but first of all, sir, if a waveform is given to you, what are the parameters should be considered? First of all, to solve the problem, first to see the shape of the waveform. That shape of the waveform you can write in terms of equation. Then second point is identify the time period and substitute in the IRMS equation or average value, then you can easily get the answer. So what is the x and y coordinates here? 0, 0, this is phi, Im. Find out this is x1, y1, and this is x2, y2. So m is equal to y2 minus y1 by x2 minus x1, and y means what is the y axis? I. Minus y1 is 0. So yes, Im by pi. into what is the x-axis here? Omega t. X-axis is omega t. So IRMS square is equal to 1 by pi integration 0 to pi Im square by pi square. Im square by pi square into omega t. Omega t whole square. Omega t whole square into d omega t. So Im square by pi cube. Im square by pi cube. Omega t whole cube by 3 integration 0 to pi. So Im square by pi cube into pi cube by 3. These 3 are cancelled. Then IRMS is equal to, yes, what I said. Yes, IRMS for sawtooth waveform is Im by root 3. It's Im by root 3. Yes, you can remember like this for all the waveforms, for trapezoidal waveforms and for different types of the waveforms, RMS values you have to remember. Now coming to the next concept is called the most important concept is called average value. Yes, what is meant by average value? So average value, what is the definition of the average value? I am taking the same water heater and so here I am applying a DC voltage and some current is passes here and replace the DC voltage with AC and provide the resistance is same and operating time period is also same here. R is the same, time period is same, operating time period is same here. Okay, the voltage at which, the definition of a average value, the voltage at which charge transferred in DC circuit is equal to charge transferred in DC circuit is equal to the charge transferred in DC circuit is equal to charge transferred in an AC provided the resistance is same, operating time period is also same. The voltage at which the charge transferred in DC circuit is equal to charge transferred in an AC circuit provided operating time period and the resistance both are same. Now what is the charge transferred? What is the charge transferred in DC? What is a charge transferred in DC? QDC is equal to, yes, IDC into T, RI into T. But what is the average value for a pure sinusoidal waveform? It is equal to 0. See, average value for symmetrical waveform, average value of pure sinusoidal, this is very very important, is equal to 0. You should not say that 2 Vm by pi or Im by pi. Okay, average value of the pure sinusoidal is equal to 0. Yes, this is 0 here, this is plus 1, this is minus 1, this is plus 2, this is minus 2, this is plus 3, minus 3, like that. You can add. Then that's why we are considering the only half cycle, we are considering half cycle. So as I am considering the positive half cycle, so I am considering the positive half cycle, right? So this is 0 here and this one is about the pi, and let us say this is T1, T2, T3, so on Tn. The instantaneous values of the currents are I1, I2, I3, so on In. Let us say I versus theta. I versus theta here. Now, so what is the charge at T1? Q1 is equal to this T, this period is divided into T1 is equal to T2 is equal to T3, so on Tn is equal to T by n. I1 into T1, that is I1 T by n, and the Q2 is equal to, so I can write as small q1 small q2, yes, I2 T2, that should be equal to I2 T by n, I2 T by n, and the Q3 is equal to I3 T3, I3 into T by n, so on Qn is equal to In Tn, In T by n. Add all the charges in charge produced by AC is equal to Q1 plus Q2 plus Q3, so on Qn, so on Qn. Charge produced in AC is equal to I1 T by n plus I2 T by n plus I3 T by n plus so on In into T by n. And so I1 T is equal to, so take a common is T by n, I1 plus I2 plus I3, so on In. Tt will be cancelled, then I average is equal to I1 plus I2 plus I3, so on In by n. We can call it as, this method is called the, what is this method is called the graphical method. What is this method is called the graphical method. Yes, what is your observation, sir? Average, sir. Suppose if you have a 6 subjects, and how many marks you are scoring in each subject, so 85, 90 like that, divided by 6, you will get the average value. So next, so I can use this slide. What is meant by analytical method? What is meant by analytical method? What is meant by analytical method? Graphical method is over. I average is equal to I1 plus I2 plus I3, so on In by n. Once again, what is RMS value, sir? The voltage at which the heat transferred in DC circuit is equal to heat transferred in an AC circuit, provided the time period is same and the operating resistance, is same and the operating time period is same. And the charge transferred in DC circuit is equal to charge transferred in an AC circuit, provided operating time period is same and the resistance is also same. Analytical method, why we should consider only positive half cycle, sir? Why we should consider only positive half cycle? Tell me. Because it is a symmetrical waveform, sir. Positive half cycle is equal to negative half cycle magnitudes. At any time you will take it, with the average value is equal to 0. I average is equal to, yes, what is our definite? You can, yes, 0 to pi, area over half cycle, area over half cycle by length of the base, RMS value is also like that, the area of the squares of half cycle by length of the base. So I average is equal to, what is the time period is as pi, 0 to pi. This is in the form of shape of the sinusoidal waveform, Im sin omega t d omega t, Im sin omega t d omega t, then Im by pi Integration of sine is called the minus cos 0 to pi. As I said, integration of sine is cosine, or integration of cosine may be sine. Forget about sines, but the nature of the waveform is sinusoidal waveforms, and I average is equal to Im by pi minus Im by pi. Cos phi is S1 minus 1 S minus 1, and then you will get the 2Im by pi. As I said that average value for a pure sinusoidal is 0. Average value for while we are considering the half cycle 2Im by pi. In an interview is asking clearly that average value for pure sinusoidal is how much. You should not say this one. Average value for pure sinusoidal is 0. Why I am repeating so many times means this is a very important. Average value for a symmetrical waveform is 0, and the average value here I average is equal to 2Im by pi. Similarly, V average is equal to 2Vm by pi. Then we are having one factor, two factors are very important, sir. Two factors are very important. Two factors. What is form factor? So the ratio of form factor, it is the ratio of RMS value to the average value. RMS value to the average value. Yes, we should consider for this type of waveform to average value. What is the average value for half wave rectifier is also we can derive, right, as 2 pi to 3 pi. I average is how much? What is my question is I average is how much? Which is I only, which is I. What is the time period? First of all, identify the time period. The time period is equal to 2 pi. But the waveform is existing only from 0 to pi only. And then, yes, I average is equal to 1 by 2 pi integration 0 to pi. Why I am writing 0 to pi? Yes, pi to 2 pi, the magnitude is 0. And Im sin omega t d omega t. Then I average is equal to, why? Because form factor is very important. I average is equal to Im by 2 pi minus cos omega t integration 0 to pi. Then you will get 2Im by 2 pi, and this will be cancelled. Then I average is equal to Im by pi. This is for half wave rectifier output waveform. Then you should calculate the form factor. Here. So form factor RMS value is Vm by root 2. Average value, what is the average value is 2 Vm by pi. So pi by 2 root 2, the value is 1.11. Yes, and if you go for this is for full wave rectifier output waveform or sinusoidal waveforms. Full wave rectifier or sinusoidal waveforms. If you go for the half wave rectifier, and this is Vm by 2 here, and this is about the Vm by pi. So that should be equal to pi by 2, that is 1.57. And next one is the most important, that is called the peak factor. Peak factor. So it is a ratio of maximum value by RMS value Vmax by root 2, that is 1.414 for pure sinusoidal. Pure sinusoidal are also called as a pure sinusoidal and are also called as a full wave rectifier output waveform. Full wave rectifier output waveform. If you are going for half wave rectifier, now what is this value? Maximum value by Vmax by 2, that should be equal to 2. What is value, sir? Peak factor. Yes, I will consider the average value for this one. So third waveform is yes, this is 0, pi, 2 pi and 3 pi, and let us say this is called the I maximum versus omega t. Yes, what is the slope of this one is here? What is the slope of S0 Im? Yes, Im by pi into omega t. And then I is equal to 1 by pi integration 0 to pi Im by pi omega t d omega t. So Im by pi square omega t whole square by 2 d omega t. Then you will have a Im by pi square by 2, these two are cancelled, then Im by 2 average. Otherwise there is a one shortcut method is there for this to find out the average value. I average is equal to, yes, first of all you should calculate the area. What is the area? Yes, for what is the right angle triangle area? Half into base into height. Half into base is pi, height is Im. Then I average is equal to area by length. Area is half of pi Im by pi will be cancelled, then Im by 2. Yes sir, it's a one step answer only. One step answer. So in this way you have to calculate the average value and RMS value, but calculations for understanding purpose, but you have to tell the answers within a fraction of the seconds. What is the average value for pure sinusoidal? What is the average value of the sinusoidal waveform? And what is the average value of the sawtooth waveform? What is the RMS value of the sawtooth waveform? What is the average value, RMS value of the pure sinusoidal and half wave rectifier with the different types of the waveforms? What is the definition of the RMS value? What is the definition of the average value? Yes. What is coming to the next question? So what is the average value for a pure R? What is the average value of the power for pure R? So average value of the power, for a pure R circuit. If a AC supply is given to pure R circuit, let us say V is equal to Vm sin omega t, as I am giving the supply here, AC voltage, where V is equal to Vm sin omega t, and then the current which is flowing here also, it is Im sin omega t. Why? Because I is equal to V by R and Vm sin omega t by R. What is Vm by R? Is Im sin omega t. This is the instantaneous value of the current. It is the instantaneous value of the current. Okay, so now the instantaneous power is equal to, it is a product of voltage into current. So where V is equal to Vm sin omega t and I is equal to Im sin omega t. V is equal to Vm sin omega t and I is equal to Im sin omega t. And the product of these two is now Vm Im sin square omega t. This is about the instantaneous power. But in order to get the average power, what is we required? So we require the time period. Yes. Then you should draw the waveforms where V is equal to V max sin omega t and I is equal to I max sin omega t. Now the phase angle difference between the voltage and current, the phase angle difference between the voltage and current is 0 degrees. So here we can represent it as a straight line. So what is meant by phase? Phase means a fraction of time period is called the phase. This is a very important. What is the phase and phasor? Phase means a fraction of time period. A fraction of time period is called, a fraction of time period is called the phase, and the phase angle means the angle between the voltage and the current is called the phase angle. So if I am taking the voltage as a reference and the current is also, both are in same phase, the phase angle is equal to 0 degrees for a pure resistive load. The angle between the voltage and current is also called as a power factor angle. Is also called as a power factor angle. Okay, now, so what is the waveform? What is the waveform of the voltage here? And the voltage at omega t equal to 0 degrees, 90 degrees, 180 degrees, 270 degrees and 360 degrees, and 0 to 180 and 180 to 360 degrees here, and let us say this is called the voltage waveform. This one is maximum value of the voltage, I is equal to I max sin omega t, where I max is equal to V max by R, where I max is equal to V max by R. So now, so this is reduced now with a magnitude that depends upon the R, and now here, see here, this angle, phase angle is called the 0 degrees. The maximum value of the voltage, the maximum value of the current taken place simultaneously. Okay, so this is maximum value of the voltage and this one is the maximum value of the current. So the product of these two will give, so yes, positive into positive will give the positive maximum here, and this is the power waveform, instantaneous power. And now negative into negative is also positive here, yes, positive, and this is the power waveform here. Now what is the time period of this waveform? Power waveform, what is the time period of this waveform is pi only. The voltage waveform completes one cycle, but the power waveform completes how many cycles? 2 cycles. Power waveform completes how many cycles here? 2 cycles. Let us say this is called the power, instantaneous power. And now in order to get the average power, area should be known. Yes, 1 by pi is called the length, integration 0 to pi. What is the instantaneous power here? Vm Im into 1 minus cos 2 omega t by 2, 1 minus cos 2 omega t by 2 into d omega t, and the Vm Im by 2 pi, integration of 1 is omega t, integration of cos is sin 2 omega t by 2, integration 0 to pi. And now we are having Vm Im by 2 pi. Substitute the upper limit is pi and the lower limit is 0 here, and this value is called the pi, and the pi will be cancelled. Then the average power is equal to Vm Im by 2, then I can call it as a Vrms into IRMS. I can write it as Vm by root 2 into Im by root 2, then the average power for a pure R is Vrms into IRMS. This is a very, very important. So what are the considerations for this? First of all, you should write the voltage equation, then the current equation, then the instantaneous power, and fourth one is called the waveforms, and fifth one is called the average power. You have to calculate this average power. In order to calculate this average power, you should know the time period. Average value of the power is equal to Vrms into IRMS for the pure resistive load. So coming to the next one. So what is the average power through pure inductor? Average power through pure inductor is 0, is dash. It is 0. So how can you say that the average power through pure inductor is 0? How can you remember that? Yes, what is the first one? You can take a pure inductor, that is L, as I am giving a sinusoidal voltage where V is equal to Vm sin omega t, where V is equal to Vm sin omega t. If this is a closed one, then the current will be flows. Yes, what is the voltage across the inductor formula? L dA by dt, and the current is equal to 1 by L integration of V dt. 1 by L integration of V dt. So 1 by L integration of Vm sin omega t into dt. So then I am getting Vm by omega L, integration of sin is minus cos omega t, So Vm by XL, I can call it as XL. Coming to the next introduction, what is inductive reactance? So I can write it as sine of 90 minus theta, So again I can write it as I is equal to I max sine of, minus sign is getting inside, so omega t minus 5 by 2. This is your second equation. Now what is I maximum here? That is V max by XL. Yes, what is XL now? XL is equal to omega L. We can call it as a inductive reactance. What is omega is called the angular frequency. That is the radians per second. And I max is equal to V max by XL. Right now, as I am taking voltage is the reference now, the current lags at an angle of 5 by 2. The current, inductive current is always lags at an angle of, pure inductive current is always lags at an angle of 5 by 2, 90 degrees. So the angle between the voltage and current, the inductive current is 90 degrees for pure inductor only, right? So minus sign means a lagging, minus sign means it is a lagging, plus means it is a leading. You should remember always the inductive current is lagging, okay. So with respect to voltage, now the next one is instantaneous power. Now what is the instantaneous power? The instantaneous power is equal to, it is a V max into I max sin omega t. This one is minus cos omega t. So V max I max by 2. So sin 2 theta, yes, sin 2 omega t. So in order to get the average power, so first of all, this is a voltage equation, voltage waveform, instantaneous value of the voltage where V is equal to V max sin omega t, and this one is called the 0 degrees, and this is 90 degrees, and the 180 degrees, 270 degrees, and next one is called the 360 degrees. And now after that, when the voltage waveform crosses the point here and the current which is passes through the 90 degrees here, 90 degrees to like this. So this is a waveform now. The angle between, see here, the angle between the voltage and current is 90 degrees. This angle is called the power factor angle, or also called as a phase angle. And 90 degrees, this difference 90 degrees to the total time period is 360 degrees. This is called the phase. A fraction of time period is called the phase. A fraction of time period is called the phase. Now this is about the voltage waveform here and the current waveform. The product of these 0 points, this is 0 point, this is 0 point, and this one is 0 point. Here also 0 points, 0 points, mark the 0 points here. Mark the 0 points. 0 into something is equal to 0. 0 into something is equal to 0. Now positive into negative, you will get the negative value. Positive into negative is, you will get the negative value. And the positive into positive, you will get the positive value. And the next to negative, yes, positive into negative, negative value. Yes. When the when the voltage waveform completes one cycle, but the power waveform completes how many cycles? 2 cycles. That's why I am getting the 2 omega. That is very, very important interview question. Important interview question. Now, so the average power, what is the time period in order to calculate the average power? Now, it is 1 by pi integration 0 to pi, 1 by pi integration 0 to pi Vm Im by 2 minus Vm by m by 2 sin 2 omega t. So Vm Im by 2 pi cos 2 omega t integration 0 to pi, so that is equal to 0. 1 minus 1, the average power through pure inductor is 0. What is it meaning? Means during positive of cycle it stores the energy, during the negative of cycle it releases the energy, then the average power is equal to 0. Average power through pure inductor is equal to 0. That is very, very important. So similarly, what is the average power? What is the average power through pure capacitor? What is the average power through pure capacitor? So average power through pure capacitor is also 0. And now, so which one is the leading, which one is the lagging? That is a very, very important. Pure inductive current is always lagging, or inductive current is always lagging. Pure inductive current is always lags by 90 degrees. So this is, see here, as I am giving the voltage where V is equal to V max sin omega t, and now I require the current which is flowing, right? So what is your observation? Tell me from the overall single phase AC is given to pure R, single phase AC is given to pure L, single phase AC is given to pure C. What is your overall observation? Now I is equal to C dV by dt. I is equal to C dV by dt. C into d by dt of Vm sin omega t. Vm sin omega t. So C into, yes, Vm into omega cos omega t. Generally I is equal to V by something, right? Yes or no? I can write it as Vm by 1 by omega c sin of 90 plus omega t. Sin 90 plus omega t. I can write it as V max by xc sin of 90 plus omega t. So I can write it as directly I max cos omega t also. Then I is equal to I max sin of 90 plus omega t, 90 plus omega t. This is our second equation. If you go for this second equation now, if you go for the second equation where I is equal to I max sin of 90 plus omega t. So the angle between the voltage and the current, capacitive current is 90 degrees, and the capacitive current is always leading. What is the capacitive current? The capacitive current is always leading. The capacitive current is always leading by 90 degrees. That is a pure capacitor only. I am talking about a pure capacitor. Now, instantaneous power is equal to, what is the instantaneous power? Is equal to V max sin omega t into I max cos omega t, then V max I max by 2 sin 2 omega t. Again you understood that when the voltage waveform completes one cycle, power waveform completes how many cycles? How many cycles? Power waveforms completes how many cycles now? So then power waveform completes 2 cycles. Then waveform, if you draw the waveform here, this is about the voltage waveform and the voltage waveform here, and the current waveform is like this. Current waveform is like this. So then multiplication of these two will give us positive 0, 0, 0, 0, 0 points marks. You can 0 points. So this is a negative here, and this one is positive, negative, positive, negative, right? This is about the instantaneous power. Then average power is equal to 1 by pi integration 0 to pi Vm Im by 2 sin 2 omega t. So Vm Im by 2 pi minus cos 2 omega t, then 0 to pi 1 minus 1, then average power through pure inductor is equal to 0. Average power through pure inductor is pure inductor is 0, pure capacitor is also 0, and during positive off cycle of the supply, voltage, what will happen? It stores the energy. During the negative off cycle of the supply voltage, it releases the energy. The average power through pure capacitor is equal to 0. Pure capacitor is equal to 0 here. And the next one, so what is meant by impedance? Yes, how XL and frequency, how XL varies with frequency. Yes, if XL is equal to omega L, where omega is equal to 2 pi FL, then if a frequency is 0, when the frequency value is 0, tell me X versus frequency. For a DC, the frequency value is equal to 0, number of cycles per second is equal to 0, and the frequency increases. If frequency increases, then X value is also increases linearly. X value is also increases linearly. What is the Xc value? 1 by omega C 1 by 2 pi fc. Xc is inversely proportional to f. If you draw the curve between the Xc versus frequency, for a frequency value is 0, Xc value is equal to infinity, which is an open circuit, and if a frequency increases and the frequency value increases, what will happen? Xc value will be decreases. X is called the reactance. X is called the reactance. R is called the resistance. What is the units of XL is ohm, and Xc is also is in ohm. It is measured in ohm. And now, what is mean by impedance? What is impedance for RL series circuit? What is my question is, what is the impedance for RL series circuit? Why Z is equal to, and the second question is why Z is equal to R plus JXL. Why plus sign is coming into the picture? So you should go in depth of this subject. Why the plus sign is assigned between the R and XL? Why? Instead of yes, what you are understood, for a capacitive it is leading plus, for inductive it is a lagging minus. Why? Yes, what is the impedance value here? Now I am taking RL series circuit now, R and L. So it is a practical example. If you take a coil consisting of a resistance as well as the inductance, as I am giving a supply voltage is V here, and then the current passes through R and as well as the L or a choke coil, it will produce a drop here VR, this one is VL. At a particular instant only I am taking. Generally the polarities are not marked because this one is phase and this one is called the neutral. For understanding purpose I am at a particular moment only, during positive of cycle only, I am mentioning the polarities where V bar is equal to VR bar plus VL bar. Why it is called as a bar means it is a phasor sum, it is not arithmetic sum. Now what is your observation? As I am taking the current is a reference, I is equal to IR bar is equal to IL bar. Why? Because the current which is flowing through this one is IR bar and IL bar is same. Why? Because it is connected in series now. With respect to IR, VR is in phase component now. VR bar is in phase component. VR bar is in phase component now. And with respect to IL, as I said, pure inductive current is always lagging. Pure inductive current is always lagging means voltage is leading or not. Suppose two subjects are there, and faculty which is one faculty completes the 5 units and another faculty is B faculty completes only 4 units. With respect to A completion of the syllabus, B is lagging. With respect to B, A is leading. That's it. So similarly same way, so IL is lagging, but if I am taking the IL is a reference, VL is leads at an angle of 90 degrees, but one is a horizontal vector, horizontal phasor, and another one is vertical vector or vertical phasor. Sir, what is your, sir, you are using sometimes is called the vector, sometimes is called the phasor. What is the difference, right? Scalar it is. It consisting of only magnitude, and the vector it consisting of a magnitude and direction. Phasor means magnitude, direction and rotation. Okay, so by adding these two phasors, by using a parallelogram concept, dry line which is parallel to VR, dry line which is parallel to VL, then we are getting the V bar. Now the angle between the resultant voltage and the resultant current is called the pi. What is pi is called the phase angle, are also called as a power factor angle, and also called as a power factor angle, and also called as a power factor angle. Now if you see this, one triangle is formed. Now which triangle it is? Voltage triangle. The horizontal portion is VR, the horizontal vertical portion is VL, and the hypotenuse is called the V here. Hypotenuse is called the V, and where V is equal to VR plus J times of V, where J is equal to 1 at an angle of 90 degrees, which is rotating in anti-clockwise direction. What is the importance of, what is the role of J operator? So in order to represent the vertical component, we can use I. In mathematics we are using I is equal to 1 at an angle of 90. But I is already assigned for electric current, that's why I is replaced with J now. Then we are getting VR plus J times of VL, and the magnitude is equal to under root of VR square plus VL square, and the phase angle phi is equal to tan inverse of imaginary part by real part. And now I am expanding. Now VR is equal to I into R, VL is equal to I into XL, then V is equal to IZ. From this voltage triangle only I am deriving all those things. This is V is IR now, VL is I into XL, now V is I into Z. II will be cancelled now, then you will get the impedance triangle ZR and XL. ZR and XL. Now this is in the positive imaginary axis, that's why it is called as a XL at an angle of 90 degrees, R plus J XL. And also coming to the next introduction, what is the average power? What is the average power? Yes, what is the average power through RL series circuit? Average power of RL series circuit is how much? I understood that Z is equal to R plus JXL. What is your conclusion point, sir? Yes, here we are doing a derivation, but you can tell in an interview like this, sir, if With respect to current, voltage is leading, that is in 90 degrees leading. 110 angle of 90 is equal to plus J. That's why we are getting R plus JXL. What is the average power now? So this is about the voltage here. The current value is like this. The angle between the voltage and current is power factor angle, where I is equal to, if I am taking I is equal to Im sin omega t. Yes, Im sin omega t. I is equal to Im sin omega t, but V is equal to V max sin of omega t plus phi. Why? Because with respect to current, voltage leads at an angle of phi. Then, so instantaneous power is equal to, what is the instantaneous power? Product of these two, Vm Im sin omega t sin of omega t plus phi. So this is sin A, sin B, where A is equal to omega t, where B is equal to omega t plus phi. So cos of A minus B minus cos of A plus B is equal to 2 sin A sin B. 2 sin A sin B. Instantaneous power is equal to V max I max sin omega t. Then we are getting yes, average that instantaneous power is equal to Vm Im by 2 cos of A is omega t is cos phi minus cos of 2 omega t plus phi. Then the waveforms you can see here. Waveforms now. Waveforms. How can you draw the waveforms now? Yes, this is a current waveform now. It's a current waveform, but the voltage leads at an angle of plus phi. So this is a plus phi. So this angle is called the phase angle now, the power factor angle. So which likes this. Mark the 0 points here, 0 points here, 0 points, all the 0 points you can mark. 0 into something is equal to 0. And the positive into negative is yes, negative. Yes, positive into positive, positive maximum. Then this type of waveform will comes here. Then positive portion is more instantaneous power. The time period is always pi. So you can 0. This one is called the pi here. Pi. So then the average power is equal to 1 by pi integration 0 to pi. 1 by pi integration 0 to pi. So Vm Im by 2 cos pi minus cos of 2 omega t plus phi. Then Vm Im by 2 pi cos pi into omega t, limits are 0 to pi, minus sin of 2 omega t plus phi by 2, limits is also 0 to pi, overall bracket. This term is equal to 0. Why? Because sin 2 pi plus pi sin pi, sin 0 plus pi sin pi minus sin pi 0. Upper limit you can substitute here. Vm Im by 2 pi cos pi into pi, then Vm by root 2 into Im by root 2 into cos phi, then Vi cos phi. This is about average power, or also called as a active power. Average power are also called as a active power. Active power. Yes. Now what is the next coming question? What is a reactive power? What is apparent power? Reactive power or apparent power? Now from this voltage triangle, if you multiplied with current, then you will get the power. This power is called the active power. This power is called the inductive reactive power. This power is called the apparent power. Now impedance is a property which opposes the alternating nature of the current. Resistance is directly opposes the current. Impedance is the property which opposes the alternating nature of the current, right? So VR, this one is VL and this one is V. Cos phi power factor, it is the ratio of VR by V. IR by I into Z. R by Z. From this I can write it as VR is equal to V cos phi. And similarly sin phi is equal to VL by V. VL by V. And from this VL is equal to V sin phi. VL is equal to V sin phi, right? Now, so power is equal to VR. What is VR? V cos phi. Yes, VI cos phi. This power is called the active power. Yeah, units are watts. Units are watts. And the reactive power is equal to VI sin phi. Let's check it. VL into I. VL is V sin phi. And the apparent power S is equal to SP plus JQL. That should be equal to VI under root of P square plus QL square. So this is about the reactive power. Units are where? This one is called the KVA or volt ampere. Kilowatt. Kilovolt ampere reactive. Kilovolt ampere is the units of PQ. Yes. Yes, coming to the next question. What is the impedance formula? What is the impedance for RC series circuit? RC series circuit, and also why Z is equal to R minus JXC. Why Z is equal to R minus JXC. Then if I am drawing the RC series circuit is excited with V, where V is equal to Vm sin omega t, or V instantaneous value of the V, and the current which is flowing through R produces a drop VR, and this one is Vc, only positive of cycle, and let us say this is I bar, IR bar and IC bar. If I am taking the voltage as a reference, not the voltage, you will take the reference as the current, because the current is same in a series circuit. Let us say I bar is equal to IR bar is equal to IC bar. With respect to IR bar, VR bar is in phase component, ER bar is in phase component, and capacitor current is always leading and the voltage is lagging here. Capacitor current is always leading, and that means with respect to voltage, capacitor current is always leading. With respect to current, the voltage is lagging. Now addition of these two phasors will produce as a resultant voltage is V. The angle between voltage and current is called the power factor angle. So what is the defined power factor? Defined power factor. Power factor is a ratio of R by Z. In the power factor, it is a ratio of active power to the apparent power, and power factor angle is the angle between the resultant voltage and the resultant current in a circuit, that is called the power factor angle. And now from this we are getting the voltage triangle. You should observe this. Let us say this is VR and this one is VC and this is called the V, and this VC is in the negative imaginary axis portion. That's why you are getting VR plus VC at an angle of minus 90. So then finally you will get VR minus J times of VC. So this is the resultant voltage equation. So now finally VR is equal to V, magnitude of the V is equal to under root of VR square plus VC square, and the phi is equal to tan inverse of minus VC by VR. Tan inverse of minus VC by VR. And if a VR can be written as I into R, and Vc can be written as I into Xc, and V is written as I into Z. And from this you can calculate the cos phi here. Cos phi is equal to VR by V. If I am writing the VR by V, what is VR is equal to V cos phi. And similarly, sin phi is equal to VL by V. From this, VL is equal to V sin phi. VL is equal to V sin phi. And I is taken as a common and I is cancelled out. Then you will get the impedance triangle here. And this is R, XZ, where Z is equal to R plus XC at an angle of minus 90. That's why it is called minus sign is comes into picture. So in order to get the active power, reactive power or apparent power, you can see here I multiplied with I to the voltage triangle. This is VR into I, VC into I, and this is about the V into I. So what is VR into I is called the active power. What is VR? V cos phi, that is VI cos phi. And this power is called the average power. The voltage and current, in average power equation are the RMS values, and the Q is equal to VL VC into I, that is VI sin phi. The units are active power is watt, the reactive power is var, and the S is equal to P minus JQC under root of P square plus QC square, that should be equal to volt ampere, that is VI only. So this is about the right. So this is about the apparent power here, apparent power. And now with the help of derive the average power equation, for RC series circuit. Average power equation for RC series circuit. Anyway, it is a VRMS into IRMS. See here, current and the voltage is lags at an angle of phi. Let us say I is taken as the reference, Im sin omega t, and Vc is equal to Vmax sin omega t, and the instantaneous power is equal to Vmax Imax sin square omega t. And in order to get the average power, then your requirement is to draw the waveform. I is Im sin omega t, this is called the Im sin omega t, and the voltage is lagging at an angle of minus phi. So this is about the voltage equation, voltage waveform here, and mark the 0 points, and product of this will gives to product, the product is now, this is about the negative half cycle and the positive half cycle, negative half cycle, positive and negative. The time period is pi only. Now the average power 1 by pi integration 0 to pi Vm Im by 2 1 minus cos 2 omega t d omega t. So if you substitute here, what will happen? Then the average power is equal to Vm Im by 2 pi. So this is omega t, integration is sin 2 omega t by 2 integration 0 to pi. Then I am getting Vim by 2, and this is as omega t, and this one is called the cos phi comes into picture, cos of 2 omega t minus phi, sorry, this is also sin of 2 omega t minus phi. this is not a sin square omega t, this is not at all a sin square omega t, this is sin omega t into sin of omega t minus phi, sin of omega t minus phi. So finally what is your answer is Vm Im by 2 cos phi. Here cos phi is there, cos phi into omega t. So again it is average power equation is VI cos phi. Then only you can know that Vrms into Irms into cos phi, Vrms into Irms into cos phi is called the average power, or also called as a active power, or also called as a true power, or also called as a real power. See here how many names are there. Active power, real power, and true power. Active power, real power, and true power. So this is about the RC series circuit. For what is the impedance value, what is the impedance value here. Next one is for RLC series circuit. Impedance for RLC series circuit, what is the formula? And R, and this one is L and C here, R comma L comma C, and I am giving to the voltage here, and the current which is flowing through this one, current flows through this one is I bar, and the current flows through R is IR bar, current flows through L is IL bar, current flows through C is IC bar. The current flows through R produces a drop VR bar, and this is VL bar, and this is VC bar, as I am taking only for positive half cycle, that's why I am mentioning the polarities. Okay, V bar is equal to, by applying a KVL, VR bar plus VL bar plus VC bar. As I am taking the current as a reference, I bar is equal to IR bar is equal to IL bar is equal to IC bar. With respect to IR bar, VR bar is in phase component, VL bar is exactly leads by 90 degrees, and VC bar is lags at an angle of 90 degrees. Now we are having one is a horizontal vector and another one is two vertical vectors. How can you add these three? It is impossible. So you can made it two only. So that's why we are going for the case 1. Yes, see here 2 plus J3 minus J2, that is 2 plus J1. 2 plus J3 minus J4 is 2 minus J1, and 2 plus J3 minus J3 is equal to 2. We have to take the cases like this only. Okay. Right. So in a case 1, we are taking like that, VL is greater than VC. VL is greater than VC. If a VL is greater than EC, I into XL is greater than I into XC, and XL is greater than XC. That means inductive reactance is dominating the capacitive reactance. Then your resultant phasor diagram is then VL minus VC is in the positive imaginary axis, 90 degrees here, and by adding these two phasors by using a parallelogram concept, then you are getting the resultant voltage. The angle between the voltage and current is called the power factor angle. From this we are getting the voltage triangle, VR bar, VL minus VC bar, and this one is called the V here. In the same story, where V is equal to, yes, V is equal to VR is equal to I into R, XL minus XC here, and then you are having a I into Z, I into Z. So from this I am having a impedance triangle R XL minus XC, and this one is called the impedance Z, where Z is equal to R plus J times of XL minus XC, and the power factor is not changing, where cos phi is equal to R by Z. Cos phi is equal to R by Z. Similarly, for a power triangle, if you multiply this is VR into I, VL minus VC into I, this is VI here, VR into I. So active power is VR into I, VI cos phi, reactive power VL into I minus VC into I, VI sin phi. ఎలా వచ్చింది? How can you get that answer? As sin phi, you can take that sin phi here. It's opposite VL minus VC bar by V. So where VL minus VC is equal to V sin phi, and S is equal to P plus J QL minus QC. This is the first condition. You have to take this as a first condition now. Next, case 2. What is, how many cases we are taking? The most important part. What is impedance formula? When XL is dominating, Z is equal to R plus J into XL minus XC. As case 2, VC is greater than VL, I into XC is greater than I into XL, XC is greater than XL, or XL is less than XC. If XL is less than if XL is less than XC, now tell me, this is VC minus VL, this one is VR, and the resultant one is resultant voltage is V, and the current, as I am taking the reference now. The angle between the current, voltage and current, voltage and current is power factor angle. The angle between the voltage and current is called the power factor angle. So then, cos phi is called the cos phi. From this, I can make the voltage triangle here. Base is VR, and this one is VC minus VL, and high potency V. So VR by V, nothing is changed here. Okay. So cos phi is VR by V only. The sin phi value VC minus VL by V. VC minus VL by V. And from this same you are getting R XC minus XL, and Z is equal to R minus J times of XC minus XL. This is a very important impedance formula for whenever XC is greater than XL. XC is greater than means for lower values of frequencies, XL is greater than for higher values of frequencies. This is about the impedance formula. Similarly, you can go for the active power, reactive power, and apparent power. Okay. So what is your observation from this? So XL is greater than XC. In case 1, XL is greater than XC is greater than XL. So that is in a second condition. So what is resonance? So VL is equal to VC. As I said, 2 plus 3i minus 3i, that should be equal to 2 only real part we are having. Imaginary part equal to 0. And XL is equal to XC. This condition is called the resonance condition. What is this condition is called the resonance condition. What is my resonance? Resonance is a phenomena at which both voltage and current are in same phase. The angle between the voltage and current is 0 degrees. What is the power factor under resonance condition? Unity. The power factor under resonance condition is unity. XL is equal to XC, where we are having a resonant frequency omega RL, omega R square is equal to 1 by LC, where omega R is equal to, we can call it as omega naught, that should be equal to 1 by root LC in radians per second. And if you are converting in terms of hertz, Fr is equal to 1 by 2 pi root LC. So this is the resonant frequency for RLC series circuit. This is very, very important. RLC series circuit. So what is your observation, sir? What is your observation? Now, what is the impedance formula? R plus J XL minus XC. If XL is equal to XC, 2 plus something is greater than 2. Yes or no? So, similarly, Z minimum or maximum, Z is minimum. If you take a R is 2, XL minus XC is something, 2 plus something is greater than 2. Why? Because under root of 2 square plus S imaginary part square, right? And Z minimum is equal to R. If a current is Z impedance is minimum, what is the current value? I is equal to V by Z minimum. In the denominator we are having a minimum value. What about the current? The current is a maximum value. What is the current value? At resonance only. At resonance, current value is maximum value. If you draw the curve, current versus frequency at Fr maximum, yes, maximum, and increase the resonant frequency, thus impedance value will be increases. Resonant frequency Xc is increases or XL increases. Let's check it. Below resonant frequency, which one is dominating now? Below resonant frequency, which one is dominating? In this case, Xc is greater than XL. In this case, XL is greater than Xc. Why, sir? Why? At the lower values of frequencies, Xc is dominating. At higher values of frequency, XL is directly proportional to F. So F increases means XL is also increases. So exactly maximum current, current and impedances both are having a inverse relationships. Inverse relationships means exactly in what we here. So this is about the Z versus frequency, and this black line is current versus frequency. Below resonant frequency, at lower values of frequencies, Xc increases. At higher values of frequencies, what will happen? XL increases. So now we will move to the what is omega naught. What is next question? What is omega naught? Express the resonant frequency in terms of half power frequencies. Express the resonant frequency in terms of half power frequencies. So that is the next interview question now. So it's very simple. Omega naught is equal to root omega 1 omega 2. But how you should be remember now? Okay. So what is I max formula? V by Z minimum, that should be equal to V by R. But AC is measured in IRMS is equal to IM by root 2 is equal to V by root 2 R. This is the equation number 1. Now under normal operating condition, IRMS is equal to V by Z. So V by under root of R square plus XL minus XC whole square. Equation number 2. Equate equation number 1 and 2. Equate equation number 1 and 2 here. Equation number 1 is equal to equation number 2. Equation number 1 is equal to equation number 2. So what you will do, V by root 2 R is equal to V by under root of R square plus XL minus XC whole square, sir. R square XL minus XC whole square, sir. Squaring on both sides, these two are cancelled now. 2R square is equal to R square plus XL minus XC whole square, and XL minus XC is equal to whole square is equal to R square. 2R square minus R square. XL minus XC is equal to plus R minus R star, plus R minus R at lower values of frequencies. At omega 1, you can call it as a omega 1. So which one is dominating? Lower frequencies. At lower frequencies, F1 is at F1, XC is greater than F, XC greater than XL, then your value will be negative. Your value will be negative. So that's why omega 1L minus 1 by omega 1C is equal to minus R. This is the third equation. And after that, when it will be positive there, XL is greater than XC, then you will say that resultant value will be positive, that is at higher frequencies. This is analysis is required. Omega 2L minus 1 by omega 2C is equal to plus R. So this is about the fourth. By adding these two equations, add equation number 3 plus equation number 4 here. Equation number 3 and equation number 4. Then omega 1L minus 1 by omega 1C is C plus omega 2L minus 1 by omega 2C is equal to 0 here, and omega L, if you take a common, omega 1 plus omega 2 minus 1 by C, LCM you will take omega 1 omega 2, this is omega 1 plus omega 2 is equal to 0, and here omega 1 plus omega 2 is taken as common here, then L minus 1 by C omega 1 omega 2 equal to 0, and anyway this x into y is equal to 0, x is not equal to 0 or y equal to 0, and omega 1 plus omega 2 both are added, it is never be equal to 0. L minus 1 by omega 1 omega 2 C equal to 0, and from this omega 1 omega 2 is equal to 1 by LC, that should be equal to omega naught square, then omega naught is equal to root omega 1 omega 2. As I said, they express the resonant frequency in terms of half power frequency. Express the resonant frequency in terms of half power frequency is omega naught is equal to under root of omega 1 omega 2. Sir, where we are getting, sir? At lower frequency F1 here, sir. F2 is higher frequency. So this is maximum value by root 2, sir. Im by root 2. Project the line. You will get the lower cutoff frequency, higher cutoff frequency. Bandwidth is equal to F2 minus F1, sir. What is the formula? Yes, what is the formula? F2 minus F1, what is the formula? Okay, so subtract the equation number 3, right? Omega 1L plus XL minus XC, right? XL minus XC, omega 1L equation number 4 minus equation number 3. Omega 1L minus 1 by omega 1C is equal to minus R. Omega 2L minus 1 by omega 2C is equal to plus R. This is equation number 3. This is equation number 4. Equation number 3 and equation number 4 here. And if you subtract this one, then omega 2L minus 1 by omega 2C minus omega 1L plus 1 by omega 1C is equal to R minus of minus R. That should be equal to 2R. If we take L is common, omega 2 minus omega 1, sir, minus 1 by C is common here, or 1 by omega 2 minus 1 by omega 1, otherwise plus C. This is minus 1 by omega plus 1 by omega 1 is equal to 2R here, and L into omega 2 minus omega 1 plus 1 by C, take LCM omega 2 omega 1, then minus omega 1 plus omega 2, so is equal to 2R. What is omega 1 omega 2, sir? 1 by LC. What is omega 1 omega 2? 1 by LC. So substitute here L into, yes, take a omega 2 minus omega 1 is cancelled, take a common, L plus 1 by C into 1 by LC. C will be cancelled here. C will be cancelled. Then you will have a 2R. Then omega 2 minus omega 1 into 2L is equal to 2R. 2 will be cancelled. Omega 2 minus omega 1 is equal to R by L. This I can call it as a equation number 5. Bandwidth here, and F2 minus F1 is equal to R by 2 pi L. This equation is very important. This equation is very important. F2 minus F1 is equal to R by 2 pi FL. R by 2 pi FL. Omega naught is equal to root omega 1 omega 2, bandwidth formula R by 2 pi L. So express the resonant frequency in terms of half power frequencies, cutoff frequencies. Okay, so and this is about the resonance condition. So the important equations at resonance. In a series resonance, it acts as a voltage magnification circuit. Voltage magnification circuit. So you should draw the curve now. You should draw the curve. So here like this, and Z is equal to R plus J XL minus XC. If you draw the curve, this is about the XL here, this is about the XL, and the XC value is here. Why? Because before XC you are assigning the minus value. At one point of time, XL and XC both are equal. So both are equal, then this point is called the, at X is equal to XL minus XC. So if you draw the resultant curve, so this is about the net reactance curve versus, okay, net reactance curve, X versus frequency, X versus frequency. What is the power factor under resonance condition? Unity. And series circuits, what happened? And the VL is this one, and VC is also this is VL here, and this is also minus VC and minus VC here. At VL is equal to VC, resonance point will be taken place, I into XC minus I into XC, and the voltage will be improved. Series magnetic circuit is a series resonance circuit, acts as a acceptor circuits. Acceptor. So what is another name for series resonance? It is a acceptor circuit. So this is a very important question on resonance. Okay, and next one. Yes, what are the applications of inductance? Here, as we already discussed, right, inductance, we are using a choke coil. So choke coil that is there in tube light. Nowadays we are using LED bulbs, and also fan winding. So any type of winding, fan winding, motor winding, yes, motor winding, and the single phase motor winding. Here also we are using single phase motor winding. Fan is also having a motor only, and in refrigerators also we are using a single phase induction motor. In a DC motor also you are having winding, winding consisting of it, definitely it is a inductance. Okay, so and the most 90% of the industries are used, 90% of the industries are used only three-phase induction motors only, which is the best example for the inductive loads, and the application of a capacitance. Yes, in a fan we are using a capacitor to produce the rotating magnetic field, RMF, and also to produce starting torque, sir. Okay, and in a motor also, if he consisting a single phase motor also, we are using capacitor, same purpose, and to improve the power factor, that is the most important one, to improve the power factor. Okay, and the next one. So what is the permittivity and what are the units? We will discuss later. What is the permittivity is called the epsilon. Okay, permittivity is called the epsilon here, and we will discuss in detail later. So permeability will once comes into the magnetic field and electric field, which is the difference between those two. We will discuss these bits. Okay, right. So you can add an extra slide. So now, what are the advantages of three-phase circuits? So still now we studied about the single-phase circuits, and first of all we are concentrating on single DC circuits. Later, disadvantages of DC, why we are going for the AC, and applications of AC, where we are using, and now we are entering into the three-phase circuits. After that, we will discuss the theorems. Okay, three-phase. So instead of carrying suppose if you take a transformer, three single-phase transformers, instead of carrying three single-phase transformers, you can use a three-phase transformer, and overall size will be less and cost is also less. While you are buying a vegetables, half kg is 50 rupees, half kg is 30 rupees. For what purpose they are telling, I don't know, but the quantity is also reduced and also cost is also increased. Similarly, for each and every transformer, single phase transformer, you can require a core material and as well as the winding material. Core material and winding both are required. So that's why cost is more. And three phase bulk generation, our generation is three phase, and up to the distributed generation also three phase, except at the consumer levels we are using at the homes. Service means we are using only single phase, but the transformer which is there nearby to home is also having a three phase only, So those are all advantages of the three phase. We already discussed in the marathon of electrical machines. And so what is the star connection and what is mean by delta connection? How it will be? What is the difference between the star and delta connection? So I am taking a three coils here, and this, let us say this is called the R phase and R dash here, and this one is called the Y and Y dash here, and this is called the B and B dash here, B and B dash. The finishing end of all the phases are connected to one common point, then I can call it as a neutral point, sir. What is the difference between the neutral wire and earth wire, sir? The external wire which is connected to the neutral to the ground is called the earth wire, sir, or also called as a ground wire. And the equipments, if you take a laboratory also, it consists of induction motors, DC motors, or whatever it may be. Each panel you can see that one external wire is connected to the panel that is going to the ground. We can call it as a earth wire. So to avoid the shocks, shocks. Okay, now and this is a neutral point here, and the voltages between the two phases, let us say this is R phase, Y phase, B phase. So VRY, and next one is called the VYB, and next one is called the VBR. VBR is called the line voltages. The voltages between the two phases is called the line voltages. The voltages between the phase and neutral VRN and VYN and VBN are called the phase voltages, but the angle between the voltages will be the angle between one voltage to another voltage is 120 degrees. So VRN is equal to, let us say, Vm sin omega t. Vyn is now what? Vm sin of omega t minus 120 degrees. Vbn is equal to Vm sin of omega t plus 120 degrees. Omega t plus 120 degrees. So Vrn, Vyn and Vbn. Okay. So now what is the angle between the phase voltage and line voltage? What is the angle between the phase voltage and line voltage in a star connection? For a resistive load, for a inductive load, for a capacitive load, he may ask like that interview questions. Okay. Now, so Vrn is taking as a reference here. Vrn is taking as a reference. Now tell me, Vry, comma, Vyb, Vbr are called line voltages. Line voltages. And Vrn, Vyn, Vbn are called phase voltages. Phase voltages. Vrn, Vyn, and this is called the Vbn are displaced by 120 degrees. 120 degrees. So Vrn, Vyn, Vbn, but Vry can be written as Vrn plus Vny, but our representation is Vyn only. So Vry is equal to, that means all are bars only, phasors only. Vry bar is equal to Vrn bar plus Vny bar. I can write it as Vrn bar minus Vyn bar. Vrn bar minus Vyn bar. So then I can draw the phasor diagram, then you can know the difference. So Vyn minus Vyn is like this, minus Vyn bar. Exactly it is a 120 degrees. How much it will cut? 60 degrees. Half means 60 degrees. Half means 60 degrees. Draw a line which is parallel to Vrn. From this Vrn, draw a line which is parallel to minus Vyn. Then again it is 30 degrees. What is this line voltage? The angle between the line voltage and the phase voltage is 30 degrees. Which one is a leading? Which one is a leading? Line voltage. Line voltage leads the phase voltage by 30 degrees. Okay, leads the phase voltage by 30 degrees. Okay, now I understood, right? So if it is a resistive load as 30 degrees, if it is a lagging load, yes, the line current and phase currents both are same. IR here, and this one is called the phase current. So in a star connection, what is our observation? Line voltage and phase voltage both are different. Line current and phase current both are same. IR is equal to IY is equal to IB is equal to S, phase current only, and as well as called the line current. So in the, why it is called as a phase and line means the current which is flowing through the winding is called the phase current. The current which is flowing through the line is called the line current. Line is called the line current. If you go for a lagging loads, for a lags loads, VL leads IR by 30 plus 5. This is very important, very important interview question. So for a leading loads means capacitive loads, RC loads, VL leads IR by or line current by or phase current by 30 minus 5. 30 minus 5. So these are all very important interview questions. Once again I will explain. In a star connection, line voltage and phase voltages both are different, and from this we will do the derivation. What is the relationship, right? Yes or no? We are adding as VRY is equal to VRN square plus VYN square, magnitude square plus 2VRN into VYN into cos of angle between these two is called 60 degrees. You can apply the square. Now V phase square plus V phase square plus 2 into V phase, cos 60 is 1 by 2, 2 will be cancelled, and then you will get the root 3 V phase, and the line voltage is called the root 3 V phase. VL is equal to root 3 V phase. See here, V phase is equal to VL by root 3 and I phase is equal to IL. Suppose I want to design for 100 kV transformer or 100 amperes transformer, and amount of insulation required. So V phase or insulation is required directly proportional to phase voltage. How much insulation is required? Approximately 100 by root 3, 57.7 kV. That means the amount of insulation required for a star connection is less. The amount of insulation required, yes, in a delta connection we will discuss later. But the current is directly proportional to area. Current is not changed, right? So this can be suitable for high voltage and low current applications. High voltage and low current applications. Next one. So the next connection is called the delta connection. What are the advantages and what are the relationships between the line voltage and line current in a delta connection? That you have to remember. In a star connection, 30 plus 5 for lagging power factor of the load, 30 minus 5 for a leading power factor of the load. If you go for the delta connection here, so here I am taking a coil here, and this one is called the coil, and R phase, Y phase and B phase here, R phase, Y phase and B phase, and the finishing end of the first coil is connected to starting end of the second coil. Finishing end of the first coil is connected to starting end of the second coil. Finishing end of the first coil is connected to starting end of the second coil. Now the voltage between these two lines is called the VRY here, and let us say this is called the IR is called the line current, but the phase current is different here. Phase current is different, and I can call it as IRY. Yes, this is IRY. IYB, IBR, IBR here. So now okay, so this is about the IRY, IYB, IBR. Okay, now apply KCL at this point here. Apply KCL at this point. IR is the incoming current, IBR is the incoming current, is equal to outgoing current is IRY bar and IRY bar, and IR bar is equal to IRY bar minus IVR. Okay, and in this VRY and phase voltages, line voltages and phase voltages both are same. VRY is equal to VYB is equal to VBR is equal to line voltage, and IR comma IY comma IB is equal to line currents. So just I am repeating the terminology. Voltages magnitudes are equal, but the angle it consisting of a angle here. Okay, now next IRY, IYB, IBR called the phase currents, sir. By observing this, line voltage is equal to phase voltage in this delta connection. In this delta connection, line voltage is equal to phase voltage. And now I am taking this IRY currents, I am taking the reference IYB. Next one is called the IBR. Now, okay. Now IRY bar minus IBR bar. So this is minus IBR here. Draw a line which is parallel to this one. Then you will get IR bar. This is 60 degrees. If you go for the VRY, is leads IRY by 5. The angle between line current, see here, phase current leads the line current. This is very important. Leads the line current by 30 degrees. See here, it is 30 degrees. And the angle between the VL and IL is called 30 plus 5 for lagging, 30 minus 5 for leading. And what is the total power? What is your observation? Yes. What is your observation now? IR is equal to root over IRY square plus IYB square plus 2IRY IYB. Cos of angle between these two is 60 degrees. Cos of angle between these two is called the 60 degrees. Then this one is called the I phase square plus 2I phase square by 2. Then you will get line current is equal to root 3 times of phase current. The phase current is equal to IL by root 3. So what is your observation now? In a delta connection, V phase is equal to VL and V phase is equal to VL and I phase is equal to IL by root 3. And also we are discussing for balanced loads only. For balanced loads, these are all called the balanced supplies we are discussing. If you are, instead of representing the reactance, if you are representing the impedance Z1, Z2, Z3, okay, these you can call it as a loads, 3-phase loads. Okay, so if I phase is equal to IL by root 3 and V phase is equal to VL in a delta connection, the I phase line current, phase current leads the line current by 30 degrees and angle between the voltage and current 30 plus 5 for lagging, 30 minus 5 for leading. So once again we will discuss this, a very important concept now. So apply the KCL at this point. IR plus IB bar is equal to IRY bar. Okay, so based on that only we can frame the equation. So what are the advantages of delta over star? So what are the disadvantages? Means neutral point is not available. We can't connect the single phase loads. Where V phase is equal to VL and 100% and I phase is also IL by root 3. Suppose I want to design a transformer for 100 amperes, and current is directly proportional to cross sectional area of the conductor. Area is directly proportional to phase current, right? Or current is directly proportional to area. So 100 by root 3, that means 57.73 percentage of area is required, so which is lower cost only, but 100% insulation is required, and this is suitable for high voltage applications and low current applications. High voltage applications and low current applications. And the next one is called the, so still now we discussed about the balanced load here. Balanced load. So what is meant by balanced supply? We discussed what is meant by balanced load. So if you are taking in a star connection, so this neutral point, this is IR here, IY, IB, and this is about the neutral current, Z1, Z2, Z3. Z1, Z2, Z3. If a Z1 is equal to Z2 is equal to Z3, then we can call it as a balanced load. Okay, and otherwise IR bar plus IY bar plus IB bar is equal to 0. Neutral current is equal to 0, sir. Neutral current is equal to 0. We can call it as a balanced load in a star connection. There is no shifting of neutral, there is no harmonics, all those concepts are there. Here. And next one is called the unbalanced load here. Unbalanced load. So what is my unbalanced load or a balanced load in delta? So how can you frame that delta? So this is about the and this one is Z1 here, Z2 here, same, there is nothing here. Z1 is equal to Z2 is equal to Z3, Z1 is equal to Z2 is equal to Z3, unbalanced load. And also you know that power is equal to 3 V phase I phase cos phi, because in a single phase power we are having a V phase I phase cos phi, and the active power is 3 V phase I phase cos phi, and the line power is equal to active power, same power, V phase is equal to VL and I phase is equal to IL by root 3 cos phi, and then active power is root 3 VLIL cos phi, which is the active power. So while you are going for the reactive power, the reactive power Q is equal to root 3 VLIL sin phi, and the apparent power S is equal to under root of P square plus Q square and root 3 VLIL. So root 3 VLIL. So this is about the complex power, reactive power, 3-phase power, and active power here. So kilovolt ampere reactive, kilovolt ampere, kilowatts. So in order to measure the active power, for a balanced load, how many wattmeters are required? Only 1 wattmeter is enough in the phase. If you are going for the measurement of active power, so measurement of active power, so how many wattmeters are required? Measurement of active power for balanced loads. balance load in a star and delta connection. So this is about the three-phase variac here. From this you are getting the three-phase supply, R phase here, Y phase here, B phase here, and the neutral point is also getting, and this is about the neutral point, R phase, Y phase, R phase and Y phase here, and this is about the B phase, R phase, Y phase, B phase, and the neutral point here, neutral point. Okay, and I am connecting a wattmeter M and ammeter. In order to measure the voltmeter, you can have a voltmeter between the lines, two lines, and the pressure coil is connected. So this is ML is called the current coil. The pressure coil is connected in the phases only. So this is a neutral point only, neutral point. So you can measure with the help of this, you can measure the single phase power multiplied with 3, then you will get the three phase power. Now tell me, in order to measure V phase, I phase, cos phi, in order to measure the single phase power, we require only one wattmeter where P is equal to V phase, I phase, cos phi, and multiplied with 3. If the wattmeter shows 100 watts, if the wattmeter shows 100 watts, you can multiply it with 3, then you will get a 300 watts is the three phase power, 3 V phase, I phase, cos phi. And this is about the measurement of active power using a single wattmeter method in a star connection. Coming to the next question. So if you go for the measurement of active power for a delta connection, you can see here delta connection. So this is about the delta supply, and okay, I can connect as a load now. Yes or no? Let us say this is Z1, Z2, Z3, and this is for balance load. Balance load. You can connect the wattmeter here, and ML is in series here, ML. Okay, so now I am representing separately here. So this is about the Z1. Okay, this Z1, ML is the current coil, and the pressure coil is connected. So the pressure coil is connected across these two. Okay, so current coil is connected just like ammeter in series, and the pressure coil is connected across this combination. Then it will measure the single phase power and multiplied with the 3, then you will get the three phase power. Okay, so for unbalanced load, what is mean by unbalanced load means if Z1 is not equal to Z2 is not equal to Z3 here. If a Z1 is not equal to Z2 is not equal to Z3, Z1 is not equal to Z2 not equal to Z3, then we can call it as unbalanced load. For this unbalanced load, we have to place like this. Yes, 3 wattmeters you have to place in the phases. So this is about the one combination. You have to place a remaining combination at this position and the remaining combination at this position. So instead of placing 3 wattmeters, then you can use n-1 wattmeters for a n phase system. For a n phase system, you can use n-1 wattmeters. This is called the Blandel's theorem. According to the Blandel's theorem, for a n phase system, n-1 wattmeters you have to place. For 3-phase system, 2 wattmeters are enough. And how you can connect the 3 wattmeters like this? So in the 2 phases now, S, let us say this is called the SRY, and this is RYB. So this is Y and this one is called the B. And here you can place the one more wattmeter here. One more wattmeter, it will measure the three-phase power. So how it will measure the three-phase power means W1 is equal to V1 I1 or VL IL. So you are getting a 30 plus 5, and W2 reading is VL IL cos of 30 minus 5. Cos of 30 minus 5. So if you add these two, W1 plus W2 readings, you VL IL take a common, cos of A plus B plus cos of A minus B, 2 cos A cos B. 2 cos A cos B. Cos 30 is root 3 by 2, then you will get the root 3 VLIL cos phi. So now W is equal to root 3 VLIL cos phi. It will measure the active power. So for n-phase systems we require n minus 1 wattmeters. So measurement of reactive power. So this is very important. Measurement of reactive power. For this, current coil should be placed in one phase. Current coil is placed in one phase, and the pressure coil is placed in the remaining two phases. The pressure coil is placed in the VYB here, and this one is called the IR. So you can place like this. VYB IR. So now as I take VR, VRN, VYN and VBN here, and the IR here, SIR, VYN minus VBN. So this is minus VBN. Add these two phasors, then you will get the VYB. Okay, so the angle between VYB and IR should be S. Let us say VYB is called, or otherwise you can go for the VBY. So VBN minus VYN at this position. Okay, anyway, the angle you are getting 90 plus 5. The angle you are getting, it is exactly 90 plus 5. So measurement of reactive power is so VYB and IR. VYB and IR. So exactly for a leading load, if you take it, this is called the phi here, and this one is called the 120, and this one is called the 60, and this is called the 30. 60 plus 30 is 90. So 90 plus 5, 90 minus 5, yes. So VYB IR cos of 90 plus 5, that should be equal to VLIL sin phi. So this wattmeter represents the VLIL sin phi. For that you will multiply it with the 3. So multiplied with the 3, then you will get the three-phase reactive power. You will get three-phase reactive power. Three-phase reactive power. Okay, so this is about the three-phase 3-phase balanced load or unbalanced load, how you can measure the active power, how you can measure the reactive power, So for unbalanced load for a star connection load, for unbalanced load in a star connected IR bar plus IY bar plus IB bar is not equal to 0, some neutral current is passes, then only we can say that it is a yes. And so what is the wattmeter readings W1 and W2? So this is V1 I1 cos of 30 plus 5, and one more thing is called the V1 I1 VL IL cos of 30 minus 5, VL IL cos of 30 minus 5. If a phi value is 60 degrees or phi is 0 degrees, W1 is equal to W2. If a phi value is 60 degrees, W1 is 0, and the W2 value is cos 30 is root 3 by 2. If a phi value is 90 degrees, W1 value 30 plus 120 is cos 90 is negative here, and W2 is 90, 60 cos 60 is 1 by 2 here, 1 by 2, and so like that. So 45 degrees or 50 degrees, you can check that. So W1 is equal to W2, equal values, and as well as the negative 90 S120 sin 30 value is yes, equal and opposite W1 is equal to minus W2, or W2 is equal to minus W1. So if one of the wattmeter goes to negative reading when the when the angle value is more than 70 degrees, one of the wattmeter shows the negative reading. That's why while you are testing the three-phase induction motor, having a lower power factor, and the power factor angle is greater than 60 degrees, that's why W1 you are getting is a negative value, and compared to W2 is positive. So W2 is positive, and so the most important term is missing now. What is meant by admittance and parallel RL circuit? Parallel RL circuit here. Okay, so a single phase AC is given to parallel RL circuit here, and see here in parallel voltage is same, V equal to VR bar is equal to VL bar, and from the source we are getting the current now. This is I bar, IR bar, and this one is called the IL bar, and I bar is equal to IR bar is equal to IR bar plus IL bar, IR bar plus IL bar. So then I bar is equal to V by Z, this is V by R, and this is V by XL, and 1 by Z is called the admittance. So Y is equal to 1 by R is G, and V by JXL, then G minus JBL. This is very important. Admittance Y is called the admittance. Admittance is the inverse of the impedance. What is G is called the, as we already know, that conductance. And what is BL is called the inductive susceptance. Inductive susceptance. Okay, so we are getting the inductive susceptance. Next one, so inductive susceptance. Okay, so after that so admittance triangle, yes, we are getting IR is a base one, and I am taking the voltage as a reference. IR is the in phase component here, and IL is the lagging component. By adding these two phasors, by using a parallelogram concept, the angle between these two is called the power factor angle, resultant current is I. Okay, that's why you are getting G minus JVL. This is IR and this is IL and this is I. The angle between these two is called the phi, and the cos phi is equal to IR by I. Sin phi is equal to IL by I. And after that we are getting the conductor admittance triangle here. This is G here and this is BL here, and this point is called the admittance, where Y is equal to G minus JBL. Magnitude of Y is equal to under root of G square plus BL square, and the power is equal to same active power. Active power is V phase I phase cos phi, and the reactive power is V phase I phase sin phi. V phase I phase sin phi. And also in resonance also we are getting one circuit. So what is meant by quality factor? What is meant by quality factor? So what is meant by quality factor? Quality factor, this is very important. Q is equal to 2 pi into energy stored in inductor. Energy stored in an inductor, or energy stored, maximum energy stored per cycle by energy dissipated per cycle. Energy dissipated per cycle. So if you go for the 2 pi, yes, what is your answer? Half Li square by half Li square by half Im square, or 2 pi into half Li square by energy dissipated is IR square T. Yes or no? So you can cancel this current here now. 2 per cycle he is asking by 2. So finally you will get Q is equal to omega L by R, and the Q is equal to 1 by omega RC. Q is equal to 1 by omega RC. If you substitute the value, then you will get quality factor is equal to omega L by R. Quality factor is equal to omega L by R, or quality factor is equal to 1 by omega RC. 1 by omega RC. Okay. So quality factor I can written as FR by bandwidth also, and also I can write it as FR by F2 minus F1. FR by F2 minus F1. And so this is about the S3 phase and as well as the single phase resonance. And one more point is there, and for the tank circuit, RL in parallel with C. RL in parallel with C, RL in parallel with C here, R in parallel with C here. So in order to get the resonant frequency for this, FAR is equal to 1 by 2 pi root 1 by LC minus R square by L square. R square by L square. This is a very important formula. This we can call it as a tank circuit. tank circuit. FAR is equal to 1 by 2 pi root LC minus R square by L square minus R square by L square. And if you go for the RC parallel circuit, so R this one, and this is called the C, which is given to sinusoidal here, I bar, IR bar, IC bar. I bar is equal to IR bar plus IC bar, and same V by R plus V by minus JXC sir, V by Z. Y is equal to G plus JBC. What is JBC? BC is called the capacitive susceptance. Capacitive susceptance. Okay, after that Y. So Y is equal to G plus JBC. And after that you will have a admittance triangle here, current triangle. So this one is called the IC, IR and I, and this one is called the phi. So why we are getting the positive sign also, you have an idea. G plus JBC, this one is called the admittance here, where Y is equal to G plus JBC, and the power is equal to active power is VI cos phi, reactive power is VI sin phi, and the apparent power is VI. For RL parallel circuit, RLC parallel circuit, so we can call it as a three conditions. So R here, L here, and C. Then with respect to voltage, IR is in phase, IL is lagging, and IC is leading. The case 1, IC is greater than IL, then you are having a positive triangle here, IC minus IL, and this one is called the I. And if IL is equal to S, IL is greater than IC, negative imaginary axis, IL is equal to IC, then V by XL is equal to V by XC, BL is equal to BC, that is called the resonance condition, or XL is equal to XC also you can say that, and it acts as a current magnification circuit. Current magnification are also called as a rejection circuit, and also called as a rejection circuit. Rejection circuit, why it is a rejection now? So IL is equal to IC, then Y is equal to G plus JBC minus BL, Y minimum. If our admittance is minimum, what happened to the current is also minimum. Current is also minimum. Okay, so now this is about the circuit concepts what we are missed just now. And so see here, DC, AC circuits, DC disadvantages, AC advantages. After that single phase to resonance concept, after the resonance to three phase to, yes. Now we are going for the theorems. State Thevenin's theorem. State Thevenin's theorem. First of all, suppose I am taking a voltage source here, and this one is R1, and this is about the R2, and the middle one is called the R3, and the load resistance. Find the load current using a Thevenin's theorem? No, okay, in an interview you can tell the statement, but understand how to remember the statement by applying to a circuit. This can be written as a voltage source in series with resistance now. Finally, the removed resistance you can connect V Thevenins in series with R Thevenins. Yes, this one is RL here, this is IL, where IL is equal to V Thevenins by R Thevenins plus RL. No, by drawing this also you won't understand what is the Thevenin's theorem. In any linear bilateral network, consisting of number of independent sources, here we are taking only one source, and number of resistors, or we can call it as if you go for the AC, number of impedances, can be replaced with a single voltage source in series with a single voltage source is V Thevenins in a single voltage source in series with resistance. How can you get the V Thevenins? As after that you can connect the load resistance. Now load current is V Thevenins by R Thevenins plus RS. But what are the steps to get V Thevenins is very important. Steps to get V Thevenins is very important. Steps to get V Thevenins. Okay. So steps to get V Thevenins. V Thevenins is measured at the open circuited load terminals. Directly I am writing the steps here. V Thevenins is measured at open circuited load terminals, open circuited load terminals by V Thevenins is measured at the open circuited load terminals, and that's it. So first of all, remove the load. The second point is measure the voltage at open circuited load terminals. And the third point, what is the third point here? How to get R Thevenins? So R Thevenins is measured. First of all, remove the load, and the second point is measure the resistance, measure the R at open circuited load terminals, by replacing all independent sources are equal to 0 or replacing all independent sources with their internal resistance. Internal resistances. So first of all, once again, in any linear, what is mean linear? It obeys Ohm's law. What is mean by bilateral? The impedance offered by the element is same even though current direction is reversed. In any linear bilateral network consisting of number of independent sources and impedances can be replaced with single voltage source in series with resistance. Voltage source V Thevenins is obtained at the open circuited load terminals. First of all, what are the steps? Remove the load and measure the voltage across the open circuited terminals. And the second point, R Thevenins is measured at the open circuited load terminals by replacing all independent sources with their internal resistances. And Thevenin's theorem So Thevenin scientist who is found this theorem, so who invented this theorem, and then according to this the statement is passed, the complex networks you can use Thevenin's theorem. And even if you go for the operational amplifiers, while you are solving operational amplifiers, op amps, you can apply the Thevenin's theorems and for solving more number of problems. Okay, and if you take one problem, right, so what is the problem now? So V Thevenin's V is the supply voltage here, and in order to calculate the V Thevenin's here, and this is about the R1 and R2 here and R3. Yes, is there any current which is flowing through the low R3? IL is equal to 0 here, and now V, as I required V Thevenin's at this point, V Thevenin's is equal to total voltage into same resistance R2 by R1 plus R2. Most of the students, they got it out that how V Thevenin's and R2, the voltage at this point is also V Thevenin's. Why? The current is 0 into 3 is equal to 0. If you apply KVL, if you have a doubt, as I said, if you have a doubt in an open loop, you can apply the KVL. Yes, in a closed loop is also you can apply the KVL. Wherever the junction is there, you can apply the KCL. And in order to calculate the R Thevenin's now, and this is about the R2, and the open load resistance here, it is R3 here, and by replacing the independent sources with their internal resistances, R1 and R2 both are parallel. R Thevenin's is equal to R3 plus R1 parallel with R2, that is R3 plus R1 R2 by R1 plus R2. Suppose if a current source is there, if make a current source is 0, if a current source is 0 means it is a open circuit, current is 0. If it is a voltage is 0, if a voltage is 0 means you can't act as a short circuit. That you have to remember. Okay, so this is about the Thevenin's theorem. Advantages of the theorem: any complex problems can be solved with in a simple way. Okay. Yes. Coming to the next question, what is a Norton's theorem statement? State Norton's theorem. So the statement is in any linear bilateral network, same, it consisting of a number of independent sources and the number of resistors can be replaced with a current source, a single equivalent current source in parallel with resistance. Single equivalent current source in parallel with resistance now. And you can add the removable resistance. This is called the load resistance. Now you can apply load current equation where IL is equal to total current into opposite resistance Rn by Rn plus RL here. Rn by Rn plus RL. So now what are the steps to calculate I Norton's? First of all, remove the load, and the second point is short the load terminals, and measure the current flows through short circuited terminals. And the current flows through short circuited terminals. And first of all, in any linear bilateral network consisting of a number of independent sources and resistances can be replaced with a single equivalent current source in parallel with the resistance. And how can you get the I Norton's? I Norton's is measured at the short circuited load terminals. current flows through short circuited terminals, load terminals, and R Norton's procedure and R Thevenin's both are same. R Norton's is measured at open circuited load terminals. See here, R Norton's is measured at open circuited load terminals. Yes, load terminals by replacing all independent sources are equal to 0, or all independent sources with their internal resistances internal resistances. Okay. So I Norton's means, first of all, this one is R1 here to measure I Norton's, to find I Norton's. This one is R2 here and R3, and short the load terminals here and find the current which is flowing through short circuited terminals. That is our Norton's current. And R Norton's and the procedure of R Norton's and R Thevenin's both are same. And this one is called the R1, and this is R2 and R3. And open the load terminals and measure the resistance by replacing all independent sources are equal to 0 or replaced with independent sources. R3 plus R1 parallel with R2, that is your R Norton's. Okay. And after that, if you observe that, after that what will happen? Now this is about the I Norton's procedure, how to calculate it, and R Norton's procedure, and to find out the load current now. And then you will get third theorem, the most important, superposition theorem. And this theorem is applicable only for multi-source networks. Networks. He may ask that which theorem is applicable for multi-source networks. Okay, and which theorem is applicable for 2 or more sources. Like that he may ask in an interviews. And this is about the one source and R1 here, and this one is R2, and this is R3, and you can take the current source here for understanding purpose, V and I. So in any linear bilateral network consisting of number of independent sources and number of resistors or number of impedances, comma, the response in any element is equal to algebraic sum of the responses caused by individual sources. I think you understand, right? Okay. In any linear bilateral network, consisting of number of independent sources and number of impedances, the response in any element is equal to algebraic sum of responses caused by individual sources Okay, responses caused by individual sources. Next, what is the case 1? I think you understood. V is acting, I is deactivated, source 1 acting, source 2 is deactivated. Suppose if 3 sources are there, one source you should activate and the remaining sources you should deactivate it. So now your circuit is V here, this is R1 and R2, and this one is about the R3. So current source will be deactivated, means it acts as a open circuit. See the response is asking about the current. Yes, current. Now let us say first response is I1, and case 2, current source is acting, voltage source deactivated, voltage source is deactivated. Now your circuit is reduced to SR1. Now see the response is R2, I2 here, sorry I2, this one is R3, current source as I am applying. Right, now total response is equal to I1 plus I2. Total response is equal to I1 plus I2. Okay, if case 3, if you are going for the case 3, if 2 sources are acting, then I1 plus I2. Next one is called the state maximum power transfer theorem. State maximum power transfer theorem. As the name itself, it is a maximum power transfer theorem. Maximum power transfer theorem. So if you take a one circuit here, let us say same circuit as I am taking R1, R2, and this is R3, and this one is called the RL, and the current which is flowing through this one is ILV. The maximum power is transferred from source to load when load resistance is equal to source resistance. If RL is equal to R Thevenin's, maximum power is transferred, sir. Maximum power is transferred, and the power is equal to, or maximum power is equal to V Thevenin's square by 4 RTH. V Thevenin square by 4 RTH. Same pressure, you should calculate the Thevenin's voltage, and you should calculate the R Thevenin's. Okay, and otherwise you have a one derivation. This is called the V Thevenin's, and let us say this is called the RS, and this is about the RL. So I is equal to, where I is equal to V by, let us say V by RS plus RL, and V I max square into RL. So V by RS plus RL whole square into RL here, RL, and then differentiate this equation with respect to RL and made equal to 0, then you will get RL is equal to RS. Substitute in power equation, then you will get the maximum power is equal to V Thevenin square by 4 RTH. V Thevenin square by 4 RTH. Now the most important part, so what we are discussing now, that is called the reciprocity theorem. Yes, it is called the reciprocity theorem. Reciprocity theorem. As the name itself, recipro means response to excitation. So this is V here, V R1, R2, R3. I want to see the response, and this is about the first circuit. The second circuit is represented with like this: R1 here, R2 here, let us say R3. This is about the supply voltage is V, and see the response here. this response is I2, this response is I1, and this is V1 and V2. V1 is equal to V2 and I2 is equal to I1 now. Sir, you are drawing the circuits, we are accepting that point. But what is the statement? The ratio of response to excitation. The ratio of response to excitation is same even though response and excitation are interchanged. The ratio of response to excitation, the ratio of response to excitation is same even though response and excitation are interchanged. So this is about the reciprocity theorem. Reciprocity theorem. And the next one, next analysis is called the Milliman's theorem. Milliman's theorem. So this is about the Milliman's theorem. So any number of resistors, let us say V1 R1 here, and this is R2 V2 and this is R3 and this one is V3 here, and n so on, we can connect it to one load resistance. N number of voltage sources in series with resistances are connected in parallel. N number of voltage sources in series with resistances are connected in parallel combination. Parallel combination can be replaced with a single voltage source in series with resistance. Let us say this is the equivalent circuit now, RS and VS. You will get Vs is equal to V1 G1 plus V2 G2 plus V3 G3 by G1 plus G2 plus G3. What is G1, sir? 1 by R1. What is G2, sir? 1 by R2. What is G3, sir? 1 by R3. 1 by R3. And R you are 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus so on 1 by Rn. Okay, so this is about the Milliman's theorem. You have an advantage of a Milliman's theorem. Next one is called the compensation theorem. Compensation theorem. So what is your observation from the compensation theorem? As it is a compensation theorem. Okay, suppose if you are taking one circuit here, this is R1 and this is R2 and this one is called the R3. If R3 is changed to R3 plus delta R, first find the current here, I here, and the compensated voltage VC is equal to I into delta R. Compensated voltage VC equal to I into delta R. Now you can write this R1 now here, R3 here, and this voltage is called the reverse voltage. This is minus and this one is called the plus. So this is minus and this one is called the plus here, R3 and the new value, and this is about the R2. If a voltage source is there, you can make it as a short. A reverse voltage you have to apply. You have to apply a reverse voltage. This is about the compensated voltage. The compensated voltage can be replaced or can be obtained with I into delta R as the change in the resistance. So with this and the theorems analysis is over, and the theorems which will get the solutions very short way, in a short way. Okay, so that's why Thevenin's theorem and Norton's theorem, superposition theorem, maximum power transfer theorem, reciprocity theorem, Milliman's theorem, and the compensation theorem, and the last one is called the Thevenin's theorem. Thevenin's theorem here. Thevenin's theorem. So simply I am writing here power delivered is equal to power delivered, sum of the power delivered is equal to sum of the power observed. Power delivered, sum of the power delivered is equal to sum of the power observed. So this is about the Thevenin's theorem. And now coming to the most important part is called the what is the Z parameters, where we are using two-port networks. So here, and this is the input port. Input we are having a two parameters V1 and I1 here, V1 and I1. Output we are having a two parameters, that is called the V2 and I2. So either it may be a T network or pi network or any network. Input is having a two terminals, output is also having two terminals and two unknowns, V2 and I2. The relationship between these four parameters is called the and two port networks, and we can call it as a Z parameters and Y parameters and H parameters. Okay, inverse H. So and so. And Z and Y and H parameters are very important. Okay. Now what is the Z parameters? What is the Z parameters? What are the independent variables? What are the dependent variables? Z parameters. What is the Z parameters? Z parameters. V1 is equal to Z11I1 plus Z12I2. V2 is equal to Z21I1 plus Z22I2. Z22I2. Okay, so you can write in a matrix form also. You can write in a matrix form Z11, Z12, Z22 into I1 and I2 here. And I1 and I2 is called the independent variables. I1 and I2 is called the independent variables, and V1 and V2 is called the dependent variables. Okay, so I1 and I2 is called the independent variables, and V1 and V2 is called the dependent variables. In order to get the bus impedance matrix in power system analysis, you can use these parameters. Okay, but it is a full matrix, it is not a sparse matrix, so it is very complex. That's why we are going for the admittance and the admittance parameters. Admittance parameters are also called okay, so still some part of the explanation. What is open circuit impedance now? Yes, Z11 is equal to V1 by I1 by making I2 is equal to 0. Z12 is equal to V1 by I2. And here Z21 is equal to V2 by I1 by making I2 is equal to 0. And this one is V1 by I2, that is I1 is equal to 0. And Z22 is V2 by I2 by making I2 is equal to I1 is equal to 0. Z11 is called the cell. What is the Z1? Input impedance. Z22 output impedance. Z21 transfer impedance, and this one is called the transfer impedance. Okay, open circuit transfer impedance, and if a Z1 is equal to Z22, okay, and Z12 is equal to Z21. If Z11 is equal to Z22, we can call it as a symmetrical network. If Z12 is equal to Z21, we can call it as a reciprocal network. these are the all the parameters are very important.
Yes, coming to the next intro question. What is the equivalent circuit? What is the equivalent circuit of Z parameters? How you can represent equivalent circuit of Z parameters? Okay, so in the previous question, so V1 is equal to Z11 I1 and V2 is equal to Z12 I2 and V2 is equal to Z21 I1 plus Z22 I2, and this is about the Z parameters. You can easily remember the Z parameters where V is equal to IZ combinations, and you can represent in terms of matrix form where V1 and V2 here, and this is Z11, Z12, Z21, Z22, and then we are having a I1 and I2. Now, so I can write it as this one is called the Z11. The current which is flowing here is I1, and let us say what is the V1 here, and then you can represent in terms of a voltage source which is depending. See here, this V1 is dependent on I1 and I2, and you can represent in terms of the dependent sources, that this one is Z1 to I2. And here coming to the second parameters, this is called the Z22, the current which is coming in the output port, yes, is the second port is called the V2 and I2 are the parameters. And now Z2 to I2 is over, and now we are having a dependent source. What is the value of the dependent source is Z21 I1. So this is the equivalent circuit of the Z parameters. The equivalent circuit of a Z parameter which is represented in series with the input port, in series with the output port. Okay, so what is in my Z11? Where Z11 is equal to V1 by I1 by making I2 is equal to 0. Open circuit forward impedance. We can call it as a open circuit forward impedance. And Z22 is Z11. Yes, Z11 is equal to V1 by I1 by making I2 is equal to 0. This is called the open circuit, means the port 2 is open circuited. Open circuit forward impedance. This is called the open circuit forward impedance. So he may ask, what is the Z11? What is the name, which type of name, what is the name which is assigned for the Z11? And Z21 is equal to V2 by I1, and by making I2 is equal to 0. This is also open circuit forward transfer impedance. Open circuit forward transfer impedance. Forward transfer impedance. And next Z12, what is in by Z12? So first one is coming, right? Yes or no? So V1 by, and the next one is 2 is coming. Z, you know that V by I. So V1 by I2 by making I1 is equal to 0. So this is open circuit reverse impedance. Reverse impedance. And this is Z21 is Z12 is over. Z22 is V2 by I2. V2 by I2 by making I. So open circuit output impedance. Okay, so port 2 impedance, we can call it as a port 2 impedance. So now we will go for the what is the Y parameters, what is the importance of Y parameters. So what is Y parameter and what is the importance of Y parameters? what is Y parameters. And what is the importance of Y parameters. So Z matrix is a full matrix. For solving the power system networks, it is very difficult, but Y parameters has an advantage. It is a sparse matrix. This is used in analysis of transmission systems, Gauss-Seidel method and NR method. Okay, fast decoupled method. In those methods, we are using a Y matrix. Why we are using the Y bus matrix means 90% of the parameters or elements in a matrix are equal to 0. So you can easily solve the problem for an N-bus system by using a Y parameters. So you know that what is I is equal to V by Z, right? I is equal to V by Z, and I can call it as a V into Y also. 1 by Z is called as V into Y, where I1 is equal to V1 Y11 plus or Y12 V2 Y11 V1, yes, Y11 V1 plus Y12 V2 Y11 V1 plus Y12 V2. I2 is equal to Y21 V1 plus Y22 V2. Okay, so we are having how many ports we are having? 2 ports. Input is V1 here and the current is I1, and I can go for the 2-port network, and this is called a 2-port network, and this voltage output port or second port V2, and the incoming current is I2 now. Incoming current is I2. So Y11 V1 plus Y12 V2, Y21 V1 plus Y22 V2. So what is meant by input impedance or input admittance? Input impedance in Z parameters, input admittance. So Y11 is equal to I1 by V1 by making V2 is equal to 0. By making V2 is equal to 0. See, I1 is a function of V1 comma V2. I2 is also a function of V1 comma V2. What is the meaning of this one? He may ask in an interview what are the dependent variables, what are the independent variables for Y parameters. So V1 and V2 are the independent variables, I1 and I2 are the dependent variables in a Y parameters. So I1 by V1 where V2 is equal to 0. If a V2 is equal to 0 means it is a short circuit or open circuit, it is a short circuit. So we can call it as a short circuit. We can call it as a short circuit input admittance. Input admittance. Okay, and similarly, what is meant by Y21? So the first one which is coming I2, right? So 2 means yes I2, and Y already we can define I by V. So I2 by V1 by making V2 is equal to 0, and we can call it as a we can call it as a short circuit forward admittance. So we can call it as a short circuit forward admittance. And coming to the next one, what is meant by Y12?
So I1 by V2, by making V1 is equal to 0, I can call it as a short circuit reverse admittance. Short circuit reverse admittance. Short circuit reverse admittance. And Y, so Y12 is over, Y22 is also I2 by V2, by making V1 is equal to 0, I can call it as a short circuit output admittance. Okay, output admittance. And we can call it as a output or input. We are giving the input, so wherever V1 is equal to 0, this V2 acts as a input, I2 acts as a input. But in overall what we called, so in an input, V1 and I1 is the input parameters, V2 and output we can take it as a output parameters. Based on that we can define the output impedance or input impedances. Okay, so Y22 is equal to I2 by V2. What is the equivalent circuit? What is the equivalent circuit of Y parameters? What is the equivalent circuit of Y parameters? So I is equal to Y11 V1. You can represent in a parallel combination, where I1 is equal to Y11 V1 plus Y12 V2. What is I2 is equal to Y21 V1 plus Y22 V2, and I can call it as, this one is called the Y11, and you can represent the dependent current source. This is Y12 V2. So input parameters are V1 and this one is called the I1. Similarly for output is also you can represent. So this is Y2, yes, Y21 V1. What is value here? Y22. What is the output parameters? We can represent now. V2 and this one is called the I2. So Y admittance can be represented in a parallel combination. Why? Because I is, by applying the KCL at this point, you can see that I1 is equal to, yes, Y11 V1 plus Y12 V2. Y12 V2. Okay. So next one is H parameters. What is the importance of H parameters? What is H parameters? What is the importance of H parameters? What is H parameters? And what is the importance of H parameters? What is the importance of H parameters? Okay, so V1 is equal to H11 I1 plus H12 V2, and I2 is equal to H11 I1 plus H22 V2. Okay, now what are the dependent variables and independent variables? It is a function of I1 comma V2, and this is a function of I1 comma V2. I1 and V2 are the independent variables, and V1 and I2 are called the dependent variables. These are called the dependent variables. And this is about the independent variables. What is called the independent variables? Now what is meant by H11? What is meant by H11? H11 looks like impedance only, but Z11 is open circuit input impedance and this one is called the short circuit input impedance. Short circuit input impedance. And H21, sorry, this one is H21. Now H21 is equal to I2 by I1. This is very important. Short circuit forward current gain. Forward current gain. H21 is equal to I2 by I1. This is short circuit forward current gain. And next one is H12. What is meant by H12? So H12 is equal to V1 by V2. V1 by V2 by making I1 is equal to 0. This is open circuit reverse voltage gain. Open circuit reverse voltage gain. And similarly for H22, so H22 is, what is meant by H22? So H22 is I2 by V2. I2 by V2 by making I1 is equal to 0 means this one is, what is this one? Open circuit output admittance. Sir, yes sir, we understood that. What is the H parameters? V1 is equal to H11 I1 plus H12 V2 and I2 is equal to H21 I1 plus H22 V2. But what is the importance of the H parameters? What is the importance of H parameter? So, while designing of a transistor, so while transistor is modeling, H parameters are required. For that, we by conducting a Z parameters, means by knowing the Z parameters, we can know the input impedance or output impedance or forward transfer impedance or reverse transfer impedance. By using a Y parameters, if we use a Y parameters, what will happen? You can know the input admittance or output admittance, transfer and reverse admittances. But the gains are not known with the help of a Z parameters and as well as the Y parameters. So that's why in order to know the current gains, so gain value and as well as the voltage gain and forward and transfer impedance or admittance, all the parameters you can measure with the help of a H parameters. While designing a transistor also, transfer of resistor is called the transistor, and the gain is also very important. Transistor which is acts as a amplifier, right? Okay, so gains are very important. So in that transistor is also called as a current controlled device. It is a current controlled device. So that's why in order to know all the parameters with the help of H parameters, that's why we can use H parameters instead of all other parameters. So now, what is the symmetry condition for H parameters? What is the symmetry condition? Symmetry condition for H parameters is delta H is equal to 1 and reciprocity so property delta H is equal to 1 for symmetry and H12 is equal to minus H21. What is delta H, sir? What is delta H? So H11 H22 minus H21 into H12 is equal to 1. And yes, what is the symmetry property for Y parameters? So symmetry property for Y parameters, this is for H parameter. If you go for the symmetry property for Y parameters, Y11 is equal to Y22
that is for the symmetry property. If you go for the reciprocity property or reciprocal, so you can say that reciprocal y12 is equal to y21, y12 is equal to y21. Okay, and the next one okay, so last parameter is called the ABCD parameters. What is the importance? What is the parameters now? So V1 is equal to AV2 minus VI2. I1 is equal to CV2 minus DI2. Sir, Y minus sign is assigned for the ABCD parameters. So if you go for the transmission lines, see, it is a only unidirectional. It is a unidirectional from the source to load only the current will be flows. But as per our two-port networks, the output voltage across this one is V2, but the current direction what we are mentioning is into the port of the network. But coming to the practical case of transmission lines, so transmission lines, the current is in an opposite direction, that's why I am mentioning the minus sign. So this is very important interview question. Why minus sign is assigned? Why minus sign is assigned for the ABCD parameters, minus B and minus D, and also this we can use it as a transmission lines. ABCD parameters applications are transmission lines. We can know the voltage gains and the sending end voltage and the receiving end voltage. And see here, sending end voltage is V1, receiving end voltage is V2. So we are taking as a VR at an angle of 0. So receiving end parameters we are taking as the reference line anyway, you know, in our power systems, and we can measure what are the dependent variables here, independent variables. V1 and I1 are called the dependent variables. V1 and I1 are called the dependent variables. And V2 and I2 is called the independent variables. Okay, right. So what is the A value? Where A is the reverse voltage gain. So what is the reverse voltage gain, sir? Open circuit. Reverse voltage gain. Open circuit reverse voltage gain. If you go for the C is equal to I1 by V2. This is called the admittance. Open circuit admittance, I by V, reverse admittance. So this will represent the shunt capacitance effect in a transmission lines. And next one is called the B is equal to minus V1 by I2 by making V2 is equal to 0. Short circuit reverse impedance. The D value we can call it as a current gain, reverse current gain here. So reverse current gain, so by making V2 is equal to 0, short circuit reverse current gain. So coming to the next, so what are the what is the symmetry property? You have to remember what is the symmetry property. So symmetry property for this one, where A is equal to D for the symmetry, for reciprocal, when said to be reciprocal means AD minus BC is equal to 1. Okay, anyway you are having a inverse H parameters and inverse
Okay, inverse hybrid parameters is also there, but that is not at all important. These four parameters are very very important. Symmetry condition and reciprocal condition is important, and applications of each and every parameters are also important. So coming to the next topic, magnetic circuits. The interview questions on magnetic circuits. So what is meant by magnetic field, which is represented with the flux, magnetic flux lines? Okay, magnetic flux is represented with the flux. Magnetic lines of force is called magnetic lines of force is called magnetic field. So magnetic field and magnetic flux which is represented with flux. Then permeability. What is meant by permeability? Permission to allow the flux. You can remember like that. For an easy access of following the flux. For an easy access of allowing the flux is called permeability. So which is represented with mu, where mu is equal to mu naught into mu r. What is the mu naught value? Where mu naught is equal to 4 pi into 10 to the power of minus 7 Henry per meter. What is the mu r value? For a mu r value for a vacuum, this is very very important. Relative permeability. Relative permeability, mu r is called the relative permeability. For a vacuum, it is equal to 1. So what is meant by permittivity? So permittivity is represented with the epsilon, and it which is a product of epsilon naught into epsilon r, where epsilon is absolute permittivity. Okay, and epsilon is equal to 8.854 into 10 to the power of minus 12 farad per meter. Okay, this is about the permittivity, and the units of permittivity is also very very important. Units of permittivity. Then what is my magnetic flux density? What is magnetic flux density? The magnetic flux density which is represented with B here, where B is equal to flux per area Weber per meter square. The units of magnetic flux density or magnetic flux density is measured in Weber per meter square. Weber per meter square. If you take a magnet, around the magnet you have a magnetic fields. If you observe the magnetic field now, and this you can take the area, how many number of flux lines are passes through this area. So this is called the magnetic flux density, and the next one is called the magnetic field intensity. Magnetic field intensity which is measured, which is represented with H. Our magnetic field intensity can be represented with Ni by L, and it is a formula Ni by L, ampere turns per meter. Ampere turns per meter. So Ni is called the magnetomotive force. The force required to move electrons in a particular direction is called EMF. Similarly, in a magnetic field, the force required to push the magnetic flux lines is called the magnetomotive force, MMF. What is coming the next interview question? What is mean by reluctance?
reluctance is represented with S. Reluctance is represented with S. And reluctance is the property of a magnetic material. It is the property of a magnetic material. It is the property of a magnetic material. It is a property of a magnetic material which opposes the magnetic flux lines. Which opposes the magnetic flux lines. Reluctance is directly proportional to length of the magnetic material. It is inversely proportional to cross section area of the magnetic material. S is equal to KL by A, where K is equal to 1 by mu. Then finally reluctance is equal to L by mu A. L by mu A. Okay. And next one. What is meant by permeance? Yes, what is meant by permeance? So permeance and reluctance both are having a relationships, inverse relationship. Permeance is equal to 1 by reluctance. 1 by reluctance. Okay. And what is my flux is equal to magnetic flux is equal to MMF by reluctance. What is magnetomotive force? So magnetomotive force, which is number of turns into current, is called the magnetomotive force. Ni by S. Ni by S. Magnetomotive force. Flux is equal to MMF by reluctance. Flux is equal to MMF by reluctance. If we take a straight conductor, how can you apply the right hand grip rule? So right hand thumb rule. If a current flows through a conductor, produces a magnetic field here. Current flows through a conductor, produces a magnetic field. And around the conductor, if a thumb indicates the current, rapid finger represents the direction of the magnetic field. Suppose if you take a circular coil, the coil is wounded on this one, and then the current passes through this one, and current is in this direction. That means the rapid fingers represent the direction of the current, thumb indicates the direction of the flux. So it acts as a north pole, it acts as a south pole. And this is about the circular coil. We can call it as a circular coil. This is called the straight conductor. So straight conductor. This is called the straight conductor. And what is the difference between the electric field and the magnetic field? So electric field and a magnetic field. So this basics you have to know that. Yes, that means what are the parameters? I am not talking about the definitions. What are the parameters? Yes, in an electric field we can call it as a resistance, which is represented with the R. In a magnetic field we can call it as a reluctance. The symbol which is represented with S. The symbol which is represented with S. And here it is called the EMF, electromotive force. Here I can call it as a MMF, the same function. And next one is called the current here, I. And here you can call it as a flux, phi. Okay, so this is difference between the electric field and as well as the magnetic field, electric field and magnetic field. If you are taking
a circular coil, a circular ring, you can wound the winding like this. If you are supplying a voltage, then you have only one reactance offered by this ring. This reluctance is called the S is equal to mmf by S flux. Okay, suppose if you take a circular coil and some area P is provided here and I am giving a supply voltage, this is called the area. But here the flux lines are gathering like this. This is called the fringing. What is called the fringing? We can call it as a fringing. Area is provided. How many reluctances we are provided? So area of the magnetic path and also area of the open path, area 2. So S1 plus S2, that is the total reluctance offered by this ring. This type of ring is called the S1 plus S2. S1 plus S2. Okay. So now what is mean by, next one is called the, what is mean by self-induced EMF, self-induced EMF, and also called as a self-inductance, and also called as a self-inductance. If you take a coil here and some coil is wounded on it, this coil is called the coil 1. Coil 1. And now I have this A1 is called the coil 2. Coil 2. And here I am passing the current here with the sinusoidal current I can pass, and the current flows through the coil 1, which will produce a magnetic field. Current flows through a coil. Current flows through a coil, produces a magnetic field. This is the number of flux lines here. Time varying flux, this flux is common for both the coils. According to Faraday's law of electromagnetic induction, an EMF is induced in a coil 1 as well as the EMF induced in a coil 2. And this EMF is called the self-induced EMF. Self-induced EMF. It is the EMF induced. It is the EMF induced in a set of. It is the EMF induced in a set of conductors. Set of conductors due to current flows through its own coil. Due to current flows through its own coil. And where E1 is equal to minus N1 d phi by dt. What is N1 is called the number of turns of the coil 1. Minus sign is according to Lenz's law. And this I can written as minus N into d phi by di1 into di1 by dt. The current which is flowing through the coil 1, I can say it is I1 only. And this part is called the SL di by dt. This L is called the self-inductance. That should be equal to minus N d phi by di1. It is the rate of change of flux when the current flows through its own coil. It is the rate of change of flux when the current flows through its own coil. We can call it as a self-inductance of the coil. Self-inductance of the coil. And coming to the next interview question. What is meant by mutually induced EMF? What is meant by mutually induced EMF? What is meant by mutually induced EMF? So, if you are taking this coil here, current passes through the coil 1, produces an EMF induced in a coil 2. It is the statically induced EMF. It is statically induced EMF in a coil 2 because of current flows through another coil is equal to minus m into minus n into d phi by dt, where E2 is equal to minus m into, I can call it as a d phi by I1 into di1 by dt. I can say that it is called the this is N2 here. This is N2. I can call it as a mutual induced inductance is called the Mn2 d phi by di1, where m is called the, what is a m, where m is called the mutually induced mutual inductance only. L is called the self inductance. Where m is called the mutual inductance. Okay, what is m is called the N2 d phi by di2 di1, m2 di by di1. Because of current flowing through the first coil, there is an EMF is induced in a second coil is called the mutually induced EMF. Rate of change of flux in the coil 2 because of current flowing through the first coil is called the mutually induced EMF. We can call it as a mutual inductance. This one is called the mutual inductance. Okay, and now what is if two inductors? So if two inductors are connected in series aiding, what is the net equivalent inductance? What is L equivalent? What is in the series aiding now? What is in the series opposing now? We can say that, see here, suppose if a current sense of winding is like this, the second coil is also like this, the current flows through the coil 1 and the current flows through coil 2 here, and this is the current. I am applying a voltage here also I am applying a voltage, sir. Here you can take that it is a dot, here also you can take that it is a dot now, that is called the sense of the winding. If the current passes through the coil here and this is the current direction, current enters at the front side of the coil and the front side of the iron pieces and leaves at the back side of the iron piece. Okay, back side of the iron piece we are having anyway conductors right now. Here also same thing. See here, the flux is produced by the first coil is in this same direction. Let us say this is called the phi 1. So leftward direction. If you apply the right hand grip rule on the coil 2 is also producing the, let us say this is phi 2, this one is called the phi 1. If both are aiding, we can say that it is a positively coupled circuit. Now. Okay, and mutual induced EMF, it is a EMF which is induced in the second coil due to the current flowing through its another coil which is magnetically coupled to it, electrically isolated. Suppose if I am taking the same for the same sense of winding, you can pass the current in a opposite direction. This is the current direction now. So current is flowing to the coil 1 is in this direction at a particular time. The current is downward direction. This current passes through here. I am not changing the sense of the winding. If the current passes through the second coil is in the opposite direction, this is the flux direction. Yes, this one is the flux direction here. Phi 2, phi 1 and phi 2. See, rapid finger represents the direction of the current. Thumb indicates the direction of the flux. Here also rapid finger represents the direction of the current. Thumb indicates the direction of the flux. Both are subtracting. So phi 1 minus phi 2 or phi 2 minus phi 1, we can call it as a negatively coupled circuit. Negatively coupled circuit. And if you go for the, I am changing the sense of winding. I am changing the sense of winding. You can change the winding like this. So this is sense of winding. Sense of winding I am changing. If I am changing the sense of winding, this is called the dot here. Here it is called the dot. Means I have started the winding at this position. You can pass the current in this direction here. Now current will be upward direction coming to your point of view. And then if the current enters here, let us say this is the voltage I am applying, and the current is also entered here. The current is also entered. Current is also, yes, current enters like this. Current enters at this position if the current is passes right upward direction. So here also flux is phi 1 is in this direction. Here also flux is in this direction. What is your observation? If the current enters into the dot in both the windings, then we can say positively coupled. The fluxes are both are aiding position. Suppose for the same sense of winding, whatever the sense of winding, see your sense of winding is different now. If I am passing the current in this direction now, and here I am passing the current at this position, this is called the dot, here it is dot, and the starting winding is what? What is the dot reference? Dot represents what? Dot represents it is started at the winding is started at this position only, and now the flux direction is in this direction now, and here also flux is opposite direction. Then the net flux value is equal to phi 2 minus phi 1 or phi 1 minus phi 2. That depends upon the number of turns. It is a negatively coupled, sir. Negatively coupled. Positively coupled means if current, see 1, 2, 3, 4, this is called the 3 and this one is called the 4, and the remaining 1 and 2, observe that 1 and 3 if the current enters the dot in both the windings. If current enters the dot in both the windings, then we can say that it is a positively coupled. If the current enters the dot in one winding, if the current leaves the dot in another winding, we can say that it is a negatively coupled circuit. Okay, now coming to our question now. What is mean by, yes, L equivalent is equal to, so what is the L equivalent value? L equivalent value. So this is called the L1 here, and self-inductance, this is L2, self-inductance of the coil 2, and the current passes in this direction, and the mutual inductance is there between these two. When the current flows through coil 1, produces a flux that is linked with the coil 2. If the current flows through the coil 2, produces a flux which is linked with the coil 1. How many mutual inductances are, mutual flux will be there? 2 fluxes. Because of 2 mutual inductances are there, then L equivalent is equal to L1 plus L2. See here, if the current enters the dot in both the windings or not? Yes, it is a series aiding and subtracting, aiding. So due to this M is added, due to this M is added, plus 2M. Suppose if the current enters into the dot in one winding, if the current enters into the dot in one winding and leaves the dot, so you can connect the combination like this. So this is about the dot here, and this is a one more coil, right? This is about the dot. You can connect the coil like this. You can connect the coil like this. What happened? The current leaves the dot. Here current enters the dot. Obviously, L equivalent is equal to L1 plus L2 minus 2M. Minus 2M. If you go for the parallel aiding, if you go for the parallel heading, this is about the inductance L1 and this is about the inductance L2 here. If the current enters into the dot in both the windings and L equivalent is equal to L1 L2 minus M square by L1 plus L2 minus 2M. This is for the parallel heading. And if you go for the parallel subtracting, if the current enters the dot in one winding, if the current leaves the dot in another winding, this is about I1 and this is about I2 and I here. What is the L equivalent is equal to L1 L2 minus M square by L1 plus L2 plus 2M. L1 plus L2 plus 2M. If the current enters the dot in one winding and leaves the dot in another winding, so then this is about the parallel heading and parallel subtracting. Now what is the most important question is called the what is retentivity and cohesivity. What is the retentivity property and cohesivity property? I think it is spelling mistake is there. You have to correct it. Cohesivity property. And if you take an air core, this is called the air core, and the BH curve is a straight line. Both the current and flux zeros values are taken place simultaneously at the same time, and the maximum points is also same time. Okay, so this BH curve is linear. But now, if you go for the transformer, if you go for the DC machine, if you go for the any machine, synchronous machine, induction machine, you have to wound the winding on the core material, that is on silicon steel. So if you take a soft iron piece and the coil is wounded on this, if a current passes, what will happen? The BH curve, because of its material property, the BH curve is not linear. The BH curve is a non-linear curve. Both maximum points of flux and currents are taken place simultaneously. Peak values are taken place simultaneously, but 0 points will be different. You can see that at this position what will happen? As the current is existing and the flux is 0 at this position, and the 0 current some flux is present at this position, minus I mu comma 0. So even though current is 0, some flux is retained in the core material. That property is called the retentivity property. What is that property? Is called the retentivity property. Okay, and because of its material, soft magnetic material, hard magnetic material, soft magnetic material is only 5%. Hard magnetic material, we are having 30 to 40% of the flux is retained, but we don't go for the hard magnetic material because of initial voltage is only, if it is from the total voltage, if a residual voltage is more, it is very difficult. And cohesivity property, in order to bring this flux is 0, in order to bring this flux to 0, some external force is required. If some external force is required, right? Yes or no? That external force is called the cohesivity principle or cohesivity property. Definitely, sorry, that property is there. Yes, iron core material, definitely a BH curve is non-linear. As you all know, for a silicon steel, this loop value, area value is less, and for X value is equal to 1.6. You know that hysteresis loss neta V max power 1.6 FV, where V is called the volume of the material, F is called the frequency of the supply, and V max is called the maximum flux density.
Neta is called the Steinmetz coefficient. The area under the hysteresis curve is called the hysteresis loss. If you go for the cast iron material, cast steel material, mild steel materials, the BH curve will be larger and the area is also high. If you are providing the area is more, between BH curve area is more, means hysteresis loss is more, and because of material property only. What is the hysteresis loss? As you all know, right? The power required to change the orientation of the molecule is called the hysteresis loss. The power required to change the orientation of the molecule is called the hysteresis loss. Okay, and so in this overall magnetic circuits, you should concentrate on what is the magnetic field intensity and the magnetic flux density. What is the magnetic flux lines, and what is the law of magnetism? So law of magnetism. So law of magnetism is what is the law of magnetism? Force is equal to directly proportional to strength of the poles, the product of two pole strengths, and it is inversely proportional to distance with square of the distance. Unlike poles attract each other, like poles are repel each other, and the force is equal to, it is a product of two pole strengths and inversely proportional to square of the distance. This is about the law of the magnetism. And coming to that, after that we were concentrating on the most important, what is the reluctance and magnetic flux density is flux per area Weber per meter square. What is the mean by reluctance, what a property, and what is the permeance, and what is the permeability for an axis of following the flux. And after that discuss the magnetically coupled circuits, and series aiding and series subtracting and parallel aiding and parallel subtracting. All those formulas are very important in an interview point of view. And so what is the law of magnetism? So these are all related to and the magnetic circuits. Okay, coming to the next concepts, graph theory. So what is the advantage of network topology? What is the advantage of network topology over conventional methods? This is very important. See here. So we are using mesh analysis, nodal analysis, star to delta conversions, and branch current methods. So many methods are there for solving the networks. But if you want to solve the 69 bus system or 118 bus system or 14 bus system in a power system networks while you are applying NR method, okay, and Gauss-Seidel methods for transmission systems, and for distribution system forward sweep method you can use, and different methods you are using. And if your number of networks will be more and buses is also more, you can't apply the mesh analysis and nodal analysis. It is very difficult to, if loops are increases, mesh analysis is very difficult, nodal analysis also very difficult if nodes are increasing. So in that point of view, and every branch we can represent it in terms of a twig, like a thick line, and by using a network topology, and this is a way, and by applying which is represented in terms of a matrix form, as we already discussed in the previous interview questions, that is on magnetic circuits. You observe that in two-port networks, Y parameters. What are the advantages of Y parameters? 90% of the elements in a matrix that should be equal to 0. Yes or no? And for network topology, this is also you can apply for like a cut set matrix and tie set matrix. You can apply by using a KVL and KCL equations. It's very easy to frame the matrix. Okay, and suppose if I am taking a problem, how can represent it as a graph? What is mean by graph? That is called the first question. What is by graph? And this is also an element is having R1, and this is element is called the R2, and this element is called the inductor, and the L1 here, and this is V R, and here one having a capacitance Z, and here I am having a current source. I think first of all you can easily understand that this is about the first identify the nodes here, 1 here, 2 here, and this one is called the 3, and this one is called the 4. And you can represent, and some branches are represented like a thick line, right? So 1, 2, 3, and this one is called the 4 here. 1 to 2 resistor element is connected, you can represented a line here. 2 to 3 is also represented as it is a line, and now 2 to 4 is also connected as it is a line here, and 1 to 4 is also connected as it is a line, and 3 to 4 is also connected, it is a line, and 1 to 3 is also connected, it is a line. But 3 to 4 how many connected? One capacitor is connected, one capacitor is connected, and as well as the one current source is connected. This current source can be open circuited. If a voltage source is a short circuited, voltage source is there, you can make it as a short circuit. If a current source is there, you can make it as a open circuit. Now this is called the graph. Now a representation of the electrical networks or electrical circuits in terms of branches is also represented in terms of lines. That is called the graph theory. We can call it as a graph. What is meant by oriented graph? So graph, you understood what is my oriented graphs. Oriented graphs. Okay. If the direction is marked here, if the direction is marked, then we can call it as a oriented graph. The graph with the direction is called the oriented graphs. Oriented graphs. So that is also very, very important. So next one is called the planar graph. Yes, planar graph. So what is the representation of the planar graph? So here this type of circuit is called the planar graph. So whatever the junction point or the node point which is not repeated twice is called the planar graph. Non-planar graph is definitely it is a represented twice, more than twice, like this A, B, C, which touches the, again it is having a, yes, repeated branch at C here, B here, and C. This is called the non-planar graph. So what is meant by tree here? For the previous circuit, what is meant by tree? Yes, oriented graph is the direction is marked. So now what is meant by tree? So it should not consisting of a closed path. Now this is about the, yes, one type of tree here. I can represent in terms of dotted line. I can represent in terms of dotted line here. 1, 2, 3, and this one is 4. Let us say this branch A here, branch B here, branch C here. A, B, C called the trees. And let us say this is called the 1, 2, yes, let us say D, E, F. D, comma, E, comma, F are called the cotree, or also called as a links. Cotree are also called as a links. You can go for the subgraph also. You can take the some parts from the graphs. We can call it a subgraph. So 1, 2, 3. You can take like that. So 1, 2, 3 here nodes, and you can take that 4, 5, 6 like that. You can have a subgraphs also. Okay. Cotrees are very important. How many number of cotrees are there? So let us say cotrees or links are there. B minus of n minus 1. So this is very, very important question. What is how many number of cotrees are there? B minus of n minus 1, where B is called the number of branches, n is called the number of nodes. N is called the number of nodes. Okay. So what is meant by rank of a graph? That rank of a graph So rank of a graph is number of nodes minus 1. Rank of a graph is represented with R, and it is a n minus 1. Okay, and next we can take the incidence matrix. What is an incidence matrix? So this is used for calculation of the impedances. The bus impedance matrix in a power system, so we can use the bus incidence matrix. We are having two types of incidence matrix. Then let us say reduced incidence matrix. One is taken as the reference, that is row or column will be completely gone, and this we can say that it is a EAA, and this we can call it as A, and the reduced incidence matrix is called the A. Generally we can go for the reduced incidence matrix. Okay, reduced incidence matrix. Number of possible trees in a graph. It's a very important. A into A transpose. Number of possible trees in a graph is called the A into A transpose determinant. So determinant of A into A transpose will represent the number of possible. So what is A, sir? Reduced incidence matrix. What is A transpose of A, right? So then this is about the graph theory, and you have a cut set matrix and as well as the tie set matrix also. Now, so this is about the graph theory, and the most important part is the installation. I will tell you what is the installation now. Electrical installation. Low voltage switchgear. What is mean by low voltage? This is very important for an application point of view. Fuse we are using, MCB we are using, MCCB we are using, ELCB we are using. For less than 1000 volts, we can call it as a low voltage. You can protect the devices. Right? Yes or no? And fuse is previously we are using a fuse now, and repeatedly. So and now we are using MCBs and MCCBs and ELCBs and fuses also using, but MCB is a miniature circuit breaker, MCCB is called the molded gauge circuit breaker, and ELCB is called the earthly gauge circuit breaker. Fuse is whenever the excess current is flowing, overload condition and short circuit conditions, it will be melts, and fuse will have a consisting of a low melting point, and it is made up of tin and as well as the lead here. Okay, tin and lead. MCB, why we are going for the MCB over a fuse? In that fuse we are having a KitKat fuse and HRC fuse here. And MCB, miniature circuit breaker, means daily appliances in our homes we are using MCB's miniature circuit breakers. That up to, okay, so low amperes, 60 or 50 amperes we can use the MCB, and 63 amperes to 2000 amperes we can use the MCCB, which is used in substations and industries. We can use the MCCB. MCB, definitely MCB is present for the low voltage applications, which is used in our homes. And the earth leakage circuit breakers. Earth leakage circuit breakers is also used. In this we are having a voltage earth leakage circuit breaker and current earth leakage circuit breaker, voltage earth leakage circuit breaker and current earth leakage circuit breakers. Why we are going for the leakage circuit breakers means definitely some part is leaked, right, in terms of a current, leakage current is flowing. So in order to, if the leakage current is exits, what will happen? Shock will be produced. And then we are going for the earthing. Earth potential is always maintained as 0. Earth potential is also because the earth is composing of a soils and it is experienced with rain.
and so many components are there in earth, and earth potential is always zero, you have to remember. And earthing, why we are providing the earthing? If you touch the water, if you touch the fridge, and if a proper earthing is not provided at your homes, definitely you will get the shock. Why? Because whatever the current is there, and that current passes through your body to the ground. If earthing is properly provided to a particular home, even if you touch the electrical devices, there is no leakage current, right? There is no leakage current. So because if you take a motor also, motor is consisting of a winding which is placed on the core material. If a current flows through a winding, what will happen? Magnetic field is produced, and if you touch the iron material, definitely you will get the shock, right? So in order to avoid that, we can provide the earthing. And remember this earth resistance, you can maintain the below 5 ohms, and types of earthings are providing here: rod earthing, and pipe earthing, and plate earthing, and last one is called the strip or wire earthing. So, and pipe earthing, plate earthing, which is used in our at the substations, and pipe earthing is also used, rod earthing is used in our homes. Okay, so first of all, we are dig the ground below 3 meters up to depth of the above 3 meters to the ground level. Below 3 meters to the ground level, and after that you can pour the coal, and as well as the salt, again water, and alternating layers of 15 centimeters. So then you can maintain the earth resistance is below 5 ohms. And generally, if you observe in your homes, earthing is provided at the whenever the bore is there, is available at that position only, nearby only earthing is provided, because it is always maintained at the low resistance 5 ohms, because that is under a wet condition. Okay, so this is about the earthing concepts, electrical installations. These are all protecting devices, and earthing is also provided. And this is about the overall circuits. Anyway, you have a filters, L filter, C filter, and CLC filter and LCL filter. You can study in the electronic devices and circuits. We covered all the topics which are there in networks concepts. Thank you. Like, share, and subscribe to your PDF channel. All the best.